Hello everyone. Welcome to the Scaling to Petascale Institute. Hello everyone. Welcome to the Scaling to Petascale Institute for 2017. I am Scott Lathrop here at the National Center for Supercomputing Applications at the University of Illinois. And it's a pleasure to welcome all of you to the Institute. Just 2017, I am Scott Lathrop here at the National Center for Supercomputing Applications at the University of Illinois. And it's a pleasure to welcome all of you to the Institute. Just for your reference, there's a large audience out there. We have 23 sites total that are connected across those 23. For your reference, there's a large audience out there. We have 23 sites total that are connected. Across those 23 sites, over 400 people have registered to attend. And you should know by now that it's also being broadcast on YouTube Live. And we have over 200 people that are registered for that. So it's a large audience, and we're excited. Sites, over 400 people have registered to attend. And you should know by now that it's also being broadcast on YouTube Live. And we have over 200 people that are registered for that. So it's a large audience, and we're excited about the chance to reach so many people and the challenge to make it all work. About the chance to reach so many people and the challenge to make it all work. You should have access to most, if not all, of these systems on Blue Waters, NERSC, and TAC, as well as you'll be getting credits on the Amazon cloud to do some of the GPU work on Wednesday. We don't have enough accounts for everyone. You should have access to most, if not all, of these systems on Blue Waters, NERSC, and TAC, as well as you'll be getting credits on the Amazon cloud to do some of the GPU work on Wednesday. We don't have enough accounts for everyone across the TAC and NERSC systems. But our presenters are working to ensure that the exercises work on both, and that you'll all have an account on one or the other at least, so you can run the exercises. You should have support staff at your local site. We hope that they have introduced themselves to you. Raise your hand, call on them as you need help and assistance when you're going through the exercises. Teamwork has been essential for the planning for this. We've been at the planning for this for many months now. This list of individuals were the key organizers that came together to say, we think we should do this and do it at a large scale and really reach a broad national, even international audience. So I want to express deep appreciation to each of these individuals and all the staff behind them that helped pull this together to make this possible. And I particularly want to thank Randall Cotton and Michael Miller, who are in the background helping to ensure that the audio video is rock solid throughout this event. So deep appreciation to Michael and Randall. We have 23 collaborating host sites. You can see them listed here by country and by state, and the names of the individuals who are the leads at each of these sites. So we want to thank all of these sites for their participation, their help, and their support in helping to make this possible. But most of all, we really want to thank our presenters who come from multiple organizations around the country who are providing the content that hopefully you will find so valuable for your time here this week. So a big round of thanks and appreciation to all of the presenters. Communications are going to be critical. We encourage you to check the webpage for details. There's a resources page with information about getting to the systems, getting to the slides, getting to the exercises if you get lost or lose the information. Slides will be linked there, and we're doing our best to make sure you have access to all the slides before the presenters actually stand up in front of you, so you can follow along from your laptop should you decide to. Those are all being linked from a box site. The exercises are all posted to a GitLab, and so you'll be accessing that when it's time to actually do some of the exercises. We strongly encourage you to use the Slack to submit written questions at any point during the week. There'll be a number of people monitoring the Slack channel to help answer your questions as you pose them. Because of the large audience, this will help facilitate more of you getting your questions posed and hopefully getting your questions answered quickly. But at some point during the presentations, the presenters may stop and say, are there any questions? At that point, those of you at one of the 23 sites are welcome to turn on your microphone and ask your question. But we would ask the local site organizers to speak on your behalf first to say, we have a question from, say, Tufts University. And once the presenter says, go ahead, Tufts, then we'd ask you to go ahead and ask your question. So communications are essential and critical to your success in learning as much about the content as you can. And we hope through the Slack channel and the ability to verbally ask questions, you'll get most of your questions answered this week. And now, on with the show. It's my pleasure to turn this over to Marta, Argonne Leadership Computing Facility at Argonne National Lab. Marta, are you ready? Hello? Hello? It's a significant technological challenge, and we found our first flub. So let's wait here for Marta. Hello?
Hello? Scott, can you hear me?
Yes, we can hear you.
Okay.
There you are. Hello.
Hey, I was here in the podium hidden. Can you eventually, I need to share two slides, one about Argonne and one about our keynote speaker. Thank you so much. Okay, so for those who are here at Argonne and for those who are international, we are broadcasting from close to Chicago area. It's Argonne National Laboratory. It's one of the 17 national laboratories for the Department of Energy. And we are a host site and an organizing institution, as Scott was saying, with more than 3,000 and 4,000 people working here in the facilities and the centers and the institution inside Argonne. We have one of the facilities, which is the Argonne Leadership Computing Facility, which is hosting and coordinating this event, and is the home of MIRA, which is one of the top supercomputers in the world. And today I have a special mission, which is to introduce our keynote speaker. I'm really thankful for Paul Messina to be here. He has a special role. He is an Argonne Distinguished Fellow, but his role and his mission now is to help us build the machines of the future, the machines of the Petascale. So he's a director of the exascale computing project from the laboratory, and he's gonna present some of the future for us. It will be in 4 or 5 years. You will see that it's not so far. And also he will mention the motivation of this Petascale training program. But we see. Okay, so now we will pass and we will put Paul presentation. I think now I can see. Here we go. How was the user slideshow? This one? Do you want this? Or do you prefer this?
Thank you very much, Marta, and thank you to the organizers for this institute. I'm very pleased to have a chance to speak with you. And as Marta mentioned, What I'm doing these days is working on a project that was established by the Department of Energy that I will describe briefly later, and the goal of which is to create an exascale computing environment for science and engineering for the nation. And to us, it's about 4 years away. The goal is to have the first system delivered in 2021. That may seem like a long time, but to us, it's right around the corner. So when I speak of the way that I think the architectures and the software environment and the programming models will be for exascale, as you might imagine, I am relying on the planning that we're doing in the exascale computing project. Now, just to make sure that we have common terminology, although the next few slides may be very well known to you, I will go quickly through them. So, terminology, gigaflops, when I was young, that took place many years ago. We talked about gigaflops as being a big deal. Soon after that, it was teraflops. In the 1990s, the goal was teraflops and then petaflops, which is basically where we are now, and exaflops is 10 to the 18 potential operations per second. Now, as I will mention briefly later, what the hardware can do in theory is not as important as what you can do with a real application on a real computer. Nevertheless, in our community, we've been using these names and ways of planning, so you go 3 orders of magnitude each time. Now, these days, of course, all systems are highly parallel, and they're made up of nodes. Well, the node usually has cores, so you can think of it as just an execution unit. And most of them these days, within that, have more specialized hardware known as threads that are very fine-grained parallelism. Then you combine that with caches and memory, shared memory among the cores typically, and you have a node. And many nodes these days also have an accelerator like a GPU, a graphics processing unit, that you can think of as having many, again, things similar to threads to give you a lot of parallelism. And then you combine the nodes through an internal network, and you have a whole system. Now, I'll start out right away reminding you that memory access is one of the key things, always has been. It just gets to be more difficult, more challenging with the architectures that we have today, as well as the ones that are coming in a few years. Getting data to where the computation takes place nowadays can easily take thousands of cycles. To do the operation can take just a few cycles. And so that's one reason why knowing the peak speed of a system is not that useful in determining how fast you can execute a real program. And so you have caches, which are small and can help you if you have certain access patterns, but if you don't, and you only use one word every time you access a cache, you again incur great delays. So the bottom line and the bottom bullet on this slide is, knowledge of the memory system behavior is essential to getting good performance. It's always been true, but it's really true now. And what we have now is no longer systems that are only shared memory. In the good old days, many systems were that way. But now you have, within a node, typically even the cores only share part of the memory on the node. And then there are caches. And then the nodes themselves have each their own memory, so that physically memory is distributed. Therefore, you have both shared and distributed memory in essentially all the systems today. And they're getting more complex. So, today you can think of as the memory, the caches, then the main memory and DRAM, and then disk. But essentially also today, just starting and increasingly in the future, you start out at the bottom with the main memory and the caches, but then you have some fast three-dimensional memory that's often directly on the chip where the processor is, So that's really fast, but relatively small. Then you have the standard DRAM, and then non-volatile RAM is getting to be more and more common. So it can be fairly large. And one of the advantages is that being non-volatile, it doesn't consume electricity when you're not accessing it. And energy use, as I will mention briefly soon, is an issue for these systems because they're so big they can consume so much electricity. So look at all those levels of memory. Then there's a burst buffer, perhaps, which is usually non-volatile memory as well. You can think of it as a solid-state disk, and then typically also a disk. So you have to orchestrate memory usage along this hierarchy, moving data in and out. So now we'll pause because I can apparently no longer use my clicker to advance the slides. Thank you. So, and so we have to exploit multiple levels of parallelism for high performance. Now, typically between the nodes, you do message passing. You can think of it as coarse parallelism. And then you might have software threads, although nowadays you usually even have hardware threads, and then accessing main memory. So as you go from left to right, you go to finer and finer grain parallelism and concurrency. So how do you program it? Well, the message passing interface is by far the most commonly used way to do the parallelism. Although here in this diagram, I say, well, use it for distributed memory between the nodes access. In fact, MPI has gotten to be efficient enough that often one can use MPI within a node, that is, to communicate data between cores. Now, since cores do share memory, you'd think, well, isn't there a lot of overhead? Well, there could be, but MPI's implementation has been improved so that it typically is aware when shared memory is available, it doesn't send messages in a heavyweight manner. Then to access threads, OpenMP or variants of it is a programming model that's used. And of course, you'll be learning quite a bit about MPI and OpenMP and similar things. For the NVIDIA brand GPUs, the language CUDA is used very widely. OpenCL and OpenMP4 can also be used for that kind of programming. And typically you have multiple programming models for a single application because of the architecture of the systems. Now, some emerging ways of programming are PGAS, partitioned global address space, which is software that makes physically distributed memory look as if it's globally shared. And I say it's an emerging model. It has been around for quite a while, but it's emerging in the sense that there are more applications that are actually trying it, and the implementation of PGAS is getting to be more efficient, because efficiency is always an issue. So examples of languages are UPC. I think that's the most widely used PGAS language, but also Chapel, Titanium, and Core Fortran. Task-based parallelism is another one. So you can think of organizing your computation in tasks, and then there's a runtime system that takes care of scheduling what task gets executed where relative to the data and the computing pattern. The Charm++ is one example of a language that uses that. Legion is another one. So these are emerging models and are likely to be used more and more in the future. Now, with all this complexity of the architectures and with all the parallelism, you have to worry about efficiency. And a long time ago, in the days of vector machines, Gene Amdahl, who was a very distinguished computer architect, came up with a law known as Amdahl's law, strangely enough. And it's pretty straightforward. You want to decide, so how much faster can you do a calculation if you use n processors as opposed to using one? And so you can predict the theoretical maximum speed when you're using parallel computing. So the easy way to think of it is, if the speed up is limited to the serial portion, let's say that you can do 95% of the work in essentially 0 time, but that remaining 5% you have to do serially on one processor, then the most speed up you can get is a factor of 20. Now, 5% is not much, but what if you have 1%? Again, the maximum speed up is only 100. But today's systems have as much as 1 million cores or even more. So how do you deal with this? You want to be able to scale, but you want to have some efficiency. It doesn't make any sense to use 1,000 processors if you're running at the same speed as 20 processors. Well, the way that we handle that is there are 2 types of scaling. Strong scaling, which is where you're running the same problem on 1 versus 100 or 1,000 or 1 million processors. So that's strong scaling, and that's much more difficult to do. But what is often done is weak scaling. You don't run the same problem. You run a bigger problem as you're using more and more processors. So then there's a lot more computing to be done, and that way you can, in fact, use millions of cores productively. And this has been done for real complex scientific applications. So Amdahl's law is something you can't get away from. It's like the speed of light. You can't really get away from it. And as I mentioned, the parallelism, even today in your petascale systems you will be accessing, is measured in the hundreds of thousands if you take into account the hardware threads, as well as the number of cores in the GPUs, if you have some. And our best guess right now is that the exascale computers will have 100 to 1,000 times more computing units, so billion-way parallelism, if you're using the entire system. So why is it that we have that much more parallelism on the way instead of just using faster processors? Well, it has to do with something known as Dennard scaling, which deals with the physics of electricity going through the wires of a size that we now deal with, as the feature sizes are so small. And so you can see in the graph to the right of this screen that starting in about 2004, several of the curves flatten out. So the speed of the processors is no longer going up as it did for decades. So if you want more speed, you have to add more processors. You can't just rely on the processors being faster. And within the processors, of course, many units that can do work. So you use on the other hand, the Moore's law is still in effect, that the feature size of transistors and all the elements on a chip can be smaller and smaller. So that's still continuing and will at least to 5 nanometer. Right now we're at 14 or 10 nanometers. So the feature size is smaller. That means you can have quite a few billion transistors on a single chip. So how do you use the transistors? You have more cores, more threads, you have some more cache for the ones that have cache built on the chip itself. So we have to deal with the parallelism. So things are more difficult. So when we went from gigaflops to teraflops, some of the speed came from having bigger systems, factor of 32. But just as much increase of speed was if the processors were faster. When we went to peta, it was only 8 times faster from the transistor speed. Most of the parallelism, most of the increase in speed was due to parallelism, 128. And we expect that essentially all the speed up for exascale will come from more hardware working concurrently. So performance comes from parallelism. So that you have to deal with today, and you'll have to deal with more in exascale. So, I mean, why do we want to bother with such big, powerful machines when they present all these daunting challenges? Well, in science, you always have higher goals. there's an insatiable need to do things that are more complex because of the benefits to science, to society. So you can use finer grids or more atoms if you're doing chemistry or material science. Go to higher dimensional simulations that are more faithful. Have multi-physics calculations, more fidelity, the geometry more realistic, for example, to the real things that you're simulating, and time to solution. If something is going to take 6 months to simulate, you may or may not be willing to do it. If you can do it in 2 weeks, you're much more likely to do it. So time to solution matters. In some cases, such as, let's say, tropical hurricane path prediction, time to solution really matters. You don't want to predict it after the hurricane has also already landed on some landmass. And of course, some algorithms have very high complexity. So if you increase the number of atoms, you may have a factor of an exponential to the 7th more work to do. And so for many applications, and these are a couple of examples of applications that are part of the exascale computing project, we have made up slides like this, which are based on an analysis. So if you look to the right, and this is a little bit of an eye chart, but I think you'll have access to all these slides freely later. At gigaflops, you could do certain things. At teraflops, more complex things. At petaflops, you can actually validate experiments in many cases. And at exaflops, we hope to be able to essentially simulate turbulent flames and with very complex combustor chemicals that can't be simulated very well today. So this is important for efficient and clean automobiles, trucks, and gas turbines. Another one is predictive oncology, cancer treatments. And so again, you have what can be done today, in this case in 2017, which is essentially petaflops. In a couple of years, we'll be at hundreds of petaflops. And then in 4 years, we expect to be at exaflops. And you'll be able to do much more predictive models for oncology. So, given that as a background, let me say a little bit about the project. It was established in July of 2015 after 8 years of analysis of what would be the benefits to exascale, what would be the challenges. So it's Department of Energy was given the lead role for developing the first exascale system environment, but working with the National Science Foundation, Department of Defense, and in a less connected way with NASA, FBI, NIH, DHS, and NOAA. So what we work on is applications to get them ready. And so that involves, of course, a lot of work. The system software, things like the programming models, the libraries that implement them, mathematical libraries, frameworks like PETSC, and then hardware technologies and architectures to try to make those new architectures a little bit easier to use than would otherwise be the case. And of course, people are the essential thing. We also work on workforce development, and Dr. Marta Garcia leads one of the training efforts within the project, and this institute can be thought of as part of that. So we focus on these 4 key challenges. The massive parallelism I've already talked about, memory and storage I've already talked about, and both of those can be addressed by better hardware design and by better methods, better software, better algorithms. Reliability and energy consumption are primarily the purview of the companies that design and build the systems, but applications can also play a role there. Your application can be designed so that it can address faults and keep on running productively instead of having to start all over again or from the latest checkpoint, for example. Energy consumption, well, a lot of the new systems have counters or sensors that you can access in your application to see how much energy you're consuming. And you can use communication avoiding algorithms because moving data is what takes the most energy. So you can play a role as well. but much of it is up to the hardware companies. So we have these three efforts: the hardware technology that I'll describe in the next slide, and then the application development and the software technology. And all three have to work together in a co-design fashion. Applications have requirements, software tries to meet them. Software has to take into account the architecture of the systems. We try to influence the architecture of the systems, and so on. So for hardware technology, we're funding 6 contracts with companies. This was announced June 15th, and so there are public press releases on that. And these 6 companies, whose names you would probably recognize, each have 3-year research and development contracts to try to come up with better architectures for our kind of computing. For applications, we have 22 of them, and this gives just a one-line description or one-phrase description of each of them. The one on healthcare to the right is on oncology, and that's done jointly with the National Institute of Health and the National Cancer Institute. And the others you can see have to do with scientific discovery or system science, economic security, energy security, and national security. And we wanted a very broad set of applications, not only to be able to tackle all those important problems as soon as the systems are available, but also so that they have a great variety of computing needs that then guide the hardware and the software development, so that not just these 22 applications will be able to run well, but hopefully all the ones that you will be discovering and devising in the next few years. Now, one of the things that makes it easier is that a lot of scientific applications rely on about 13 basic kinds of computation, called them motifs. Now, this is due to Phil Colella of Lawrence Berkeley Lab. He initially called them the 7 dwarfs and then expanded it to 13. And so if you, the columns here, starting from column 2 to the right, are the motifs, and then the applications are the rows, and where you have a green shows that application uses that kind of motif. So for example, cosmology does use particle and cell algorithms. It uses spectral methods. It uses structured grid, and so on. So you do that for the applications, and you know what to concentrate on. And one way that we concentrate on that is by establishing co-design centers that focus on computation patterns that are used by many applications, so that one group of experts can come up with the right methods and implementation in software for the architectures of interest, instead of every application scientist having to develop his or her own. So block-structured adaptive mesh refinement is one. You have graph methods, particle and cell applications, data analysis. So will this work? Well, so I'll just give you one example. In the 9 months that the Adaptive Mesh Refinement Co-Design Center has been working, they have now convinced 5 of the applications in very different domains to use their Adaptive Mesh Refinement framework. And so you have accelerator modeling, astrophysics, combustion, cosmology, and multi-phase flow applications, all using that. So that's the kind of leverage that you can get, and the type of approach that I encourage you to take. Look for whether what you need has already been designed and implemented efficiently. Take advantage of it, if at all possible, instead of rolling your own. Okay, software, of course, is what you deal with all the time. And for Exascale, we came up with this notional diagram. This is how we organize our activities. I mentioned we have 22 application projects at present. We may increase that a little bit. We have 66 software projects that are binned into these areas. So there are tools like ones that measure performance, ones that help you find bugs, math libraries and frameworks we're investing in heavily because they can provide so much leverage to you. And I think you'll be hearing about some of those later this week. Memory and burst buffer in the middle towards the bottom there, the blue box, that's starting to address the new memory architectures, application programming interfaces for that kind of memory, which need to be developed. Data management, I/O, always important. and programming models. So that's the portfolio. It should look familiar. Well, how did we come up with that? So we looked at what the applications that have been selected for Exascale and quite a few others say they will need. And we looked at current usage to see what are people actually using. For example, at a system like NERSC, which is used by many thousands of scientists and engineers. And then we looked into the crystal ball a little bit. So when we communicated with the applications, we asked them not only what application challenge they wanted to address, but also, if you look at the top right panel here, what applications code they were planning to use, what software technologies they're planning to use. So in this case, C++, Fortran, and LLVM Clang for programming, and then MPI, OpenMP, and CUDA as part of their programming models, and Chombo for AMR, and PETSI, IDEOS for I/O, and so on. So we have information of that type from many applications, and so if you put it all together, you can see just under programming models and runtimes, there are a lot of entries there throughout. So we're not funding all of them, but it gives you an idea of the complexity and breadth of the software stack. So here, for example, what software is mentioned. So in this bar graph, if you look to the, this is for 30 applications that we talked to. Well, all 30 mention MPI. That's the far left. The next one is OpenMP. Almost all 30 did. The next one is CUDA, and that's down to 25 and so on. And there's a long tail. But this is what people are using now, and this is largely what they're planning to use. Libraries, same type of thing. You'll see PETSI and FFTW and so on in there. So we try to focus on the things that people are definitely using now and they're planning to use. And so that's guiding our investment. Oops. We also, of course, talk to the vendors because they provide a lot of the software. We don't want to duplicate it. But I will mention, which is what this slide is about, that, just taking the example of the IBM system that will be installed at Livermore, which is very similar to the one that will be installed also at Oak Ridge next calendar year. And so vendor developed is the column to the left, but in the middle, there are efforts that the project is funding that the vendors traditionally have then taken and they put it as part of their software stack. MPI, the MPitch version of MPI that was developed at Argonne 20 or so years ago, in fact, was adopted by essentially all the computer vendors. So there's a synergy between what the community develops and what the vendors provide. So I won't say bad news, good news, but the not so good news are, as you look forward to your career, there will be new features that will require extra work. Even today's are not so easy to use, but as I mentioned, especially with memory and the complexity of the nodes, things will be more difficult to use, although we're trying not to make it too bad. Lots of parallelism, of all kinds. And, one can always hope for the magic compiler to enable you to write at a very high level. And there is progress, non-trivial progress, but you can't count on that taking care of everything, especially if you care about performance. And you probably do, or you wouldn't be attending this institute. But there's a lot of good news. What you learn in the next few days in this institute is without question going to be useful for you at Exascale. Yes, you may have choices of even better things, but I assure you, in the next 4 years, you will definitely still need to know a lot about MPI, advanced MPI, OpenMP, and about some of the programming frameworks and mathematical frameworks. So what you'll be learning will pay off. It won't be just for Petascale. It'll pay off for Exascale as well. The architectures will be similar, but the nodes will be bigger and bigger in some sense. You'll see nodes with hundreds to perhaps 1,000 cores and with accelerators in these complex memory hierarchies. So a single node can be extremely powerful, but then you will still have thousands of them, if not hundreds of thousands. And again, the good news is that the programming models and languages, the libraries and frameworks that you'll be using and learning about this week will be available in an optimized fashion for Exascale 4 or 5 years from now. So as always, when one leads a project, you rely on many colleagues. So without naming them all, a lot of the people in the Exascale computing project helped me. I should have mentioned the leadership team for the project has people from 6 labs: Argonne, Oak Ridge, Berkeley, Los Alamos, Livermore, and Sandia National Laboratories. The applications and the software teams work is being done at 16 of the 17 national laboratories, 39 universities, and about 15 vendors are involved. So it's a big project. That means I rely, of course, on the project, and this is a formal acknowledgement of the funding. So now let me spend just a minute or two on what you're about to do. This institute is intended for researchers from all kinds of fields of study, so that you can explore the architectures and tools that would enable you to do computational simulation and modeling, and what alternatives you have so that you can do your research. Computers are a powerful research tool, and they're a complex tool. This institute will help you a lot. It's part of your learning process. There's a lot to be learned, but I assure you that it's worth taking the time. You can make huge improvements in how you model things and the efficiency with which you model them, make some things be within reach that previously were not. So learning is something that, that's just one step in the process, but an important one. And taking a long-term view is always useful, especially with moving technologies like computer technologies. And that, I think, is why I was asked to give this little bit of a preview on Exascale, because, as I said, it's just around the corner. So keep that in mind. And don't be afraid to think of using the biggest possible systems if that will make your scientific goals feasible. So take the time to think about what you're going to do carefully ahead of time, instead of just grabbing the first thing that comes to mind, or doing what you've been doing all along. And you'll be exposed to a lot of very important ideas. And thinking beyond your current efforts, that's something I've been fortunate to spend most of my career doing, is talking to scientists and engineers and nudging them a little bit to say, well, if you take the time to deal with a more complex system, you might be able to do things that you think today are out of reach. And so there are people who use all of the Mira system for, say, 60 hours at a time. The Mira has 750,000 cores, and they do so productively. And a lot of the work in computational science and engineering is done by teams and collaborations. So that's an important aspect of the work. Bright minds, of course, have to come up with ideas on their own, but collaborating really matters. And that's why in the Exascale Computing Project, we're collaborating across the nation. 16 national labs, 39 universities, and vendors. And this institute is a collaboration of many institutions. Thank you very much. I'll stop with this, and perhaps we have time for a few questions.
Speaker, thank you. We can take one question from the audience here, and then if someone has also from Slack.
So I wanted to ask how is it different computing on a GPU compared to on normal processors? So are there any limitations when we try scaling our codes on GPU architectures compared to the normal CPU architectures?
Well, GPUs, like many aspects of computer architecture, are a moving target. So one key thing that has been the case for GPUs for most of their existence is that they have their own memory, and that therefore to be able to use a GPU, you have to transfer data from the main memory of the normal processor that it's attached to, and typically it was a relatively slow link, and it was a bulk transfer, you can think of it. And so that was a key thing. Once you got to the GPU, then you had to think in terms of very fine-grained parallelism. But that certainly many scientific applications have. So that data transfer was a key issue that really made it different. The most recent GPUs, from NVIDIA, for example, have a much better connection between the main memory of the processor that it's attached to and the memory of the GPU itself. And so that reduces the problem. So you have to think of very fine-grained parallelism and data transfer. There are some emerging designs of other GPUs from other accelerators by other companies that may come into the market soon that have different aspects of it, but always you can think of as very fine-grained parallelism in the GPU, and then the issue of data transfer, which is becoming less of an issue.
I'm trying to find out if we have some more questions from Slack.
Energy use is, by the way, the GPUs can be very efficient in the use of energy, the way that they're designed. And so that's one of the reasons that they've gained a lot of favor. So you can have a lot of computing power with relatively small energy. The energy goals for exascale systems has been 20 to 30 megawatts. If you built an exascale system today with today's technology, it'd be several hundred megawatts. A megawatt a year costs about $1 million. So if you have to spend 300 million just for your electric bill, that's not realistic. So energy use is very important.
We don't have questions.
No questions from the Slack? Okay.
Yes, let's thank our speaker again.
Okay, thank you for your attention.
Paul, we actually have one more question from NCSA, if you don't mind.
Yes, I was looking at the general channel.
As you just mentioned, in perspective of GPUs, unified memory access, what advantage does it has any advantage on top of the ease of the programming?
Can you repeat the question, Scott?
So, in the perspective of GPUs, this unified memory access, does it has any advantage in addition to ease of programming?
I'm sorry, I couldn't catch the question. Sorry, what's the...
In the perspective of GPUs, this unified memory, does it has any other advantage in addition to the ease of programming?
The ease of programming?
Yeah. Because the code is really simple if you're you can access very easily so any other advantages that it offers?
Well, that's a very large advantage. I'm not sure that I can identify a different advantage. If you can address the GPU memory and the main memory essentially equally and not have to plan the transfer, and the transfer in the background takes place very quickly, then...
Okay. So there is a difference in the speed as well, right?
Yeah, perhaps I didn't mention that. Yeah, there are two aspects of it. One is the addressability, but certainly the physical link. Specialized ones that make that a lot faster.
Okay, thanks.
We have one more question, Paul, that came in through Slack. The question is, most scientific, there are two. Do you see HPC schedulers returning energy use alongside CPU and other job stats?
Okay, so the first question is, do I see the schedulers for jobs on the HPC systems taking into account energy use?
That's correct.
I would say probably yes. Although facilities have to make sure that they have enough electrical power to run the system, even if the system is running at full blast. Some applications use more electricity to run than others. So you have to be able to provision all that electrical power. But in order to save money, I think that definitely schedulers will, in many cases, take into account the predicted energy use of a system. Now, in some cases, in fact, in the past, some applications have essentially melted parts of chips because they used so many of the transistors simultaneously that the chip got really hot, hotter than the envisioned. So I think that will be the case. One can even postulate that perhaps some facilities will give an advantage to applications that use less energy to get their work done, and give them credit in some fashion, schedule them faster, or give them more allocation. So I think that is likely to be an issue, and that the schedulers will get smart enough to do that. Another question?
Yes, one more from Slack. What about compilers? Most scientific codes still use Fortran or C or other old compilers. Is there an effort to develop compilers for scientific computing like Julia?
Is there an effort? Well, of course, Julia exists, and so does Legion. So there are efforts to do that, absolutely. The compilers for the commonly used languages do need to continue to be developed and to have the code generation optimized for the new architectures. So Fortran, for example, which people always say it's a thing of the past, but in fact on the leadership computing facilities, easily 50% of the code that's run is Fortran. Many applications also use C or C++, but there's Fortran in there as well. So things like Julia and Legion and Chapel, are new languages, and they have compilers, and the compiler technology is certainly getting better. One of the big issues, of course, is for an application developer standpoint, is whether they can count on that language and the compiler and the associated runtime system being available, say 10 years from now. Most scientific applications have lifetimes of decades. So that's an issue. That doesn't mean it shouldn't be pursued. I'm very much in favor of languages like Julia and Legion and Chapel. It's just a matter of, how long it takes for the big application teams to decide, okay, they're willing to bet on it. Examples like Charm++, which is a different way of looking at it, certainly have made a big inroad in complex.
Okay, thank you, Paul. I think that's all the questions.
Thank you.
With that, then, we'll go ahead and take a 15-minute break at all the sites. Thank you.
So in about, 5 or 11.
Okay, welcome back from the break. Before we jump into the MPI session, I would like to introduce one more person to welcome you to the Institute. I'd like to introduce Dr. Bill Kramer, who's the project director for the Blue Waters Project here at NCSA at the University of Illinois. Bill?
Thank you, Scott. I just want to take a few minutes of time to, first of all, welcome all the participants and students of the Institute. It's very exciting for us in Blue Waters to be able to assist in putting on this institute with our staff, but also the people in Blue Waters who help coordinate this from our end, Scott, Max, and Randall, who are working here, and then some of our other staff. I see Victor and Jayhawk here helping the students. So I first of all want to thank that, but welcome all the students from all around the institutions that are joined with us to present this institute. It's quite an amazing collaboration. I would like to thank our partners at NERSC and at Argonne and Oak Ridge and at Texas for also working to put on this institute. I wanted to share a few things and then see if there's any questions. But one is what I believe is why petascale computing, why computing at scale is so important to moving forward in all different realms of research and engineering. The reason I got interested in computing, in particular, very large-scale computing, a number of years ago was because I couldn't figure out what science or engineering I wanted to specialize in. And I realized that by doing computing or helping people do computing by making systems like Blue Waters work well and helping people make systems, use those systems well, the same as the systems at NERSC and at TAC and at Oak Ridge and at Argonne, by helping people use those systems very productively, I was able to basically be involved in all fields of science and engineering. I can't think of one that somehow I didn't touch along the way. And whether you're going to stay in a discipline-specific way of doing computational science or data science in that discipline-specific, or whether you're going to be go broader and study about or understand and help about how to move forward in multiple fields. Either way, I think it's very exciting because what is done on these systems is frontier science, things that cannot be done elsewhere. And that's what we're trying to do. Eventually, they become commonplace, best of breed. If you look at the history of these very large machines going back decades, what is done on these machines within 5 or 10 years becomes more commonplace, and eventually it just is done in general. Whether it's how you look at weather forecasting, or how you look at how your cell phone is made, and the plastic in computer cases. They all started out as supercomputing applications. And now we're doing things on these machines that are well beyond what anybody else has thought of being able to do. And we're striving to do more, such as being able to simulate an entire cell, for example. So with the skills you learn in this workshop, I hope you'll be able to go on and carry out exciting new research, new investigations, and also help make your peers in your disciplines understand the importance of computational science, computing, and data analysis. So with that, I'd like to just see if there's any questions from anyone, and then let you get back to the content of your session. No? All right. Well, thank you very much. I hope you have a great time here in the Institute and learn a lot, and then take it on into the future of using what you learn here to do great stuff. Thank you.
Thank you, Bill. And with that, we'll turn it over to Marta back at Argonne to introduce the MPI team. Marta, take it away, please.
Thank you, Scott. So today we have MPI tutorial. You heard Paul Messina mentioning how it's important MPI, this impaged interface. You will see that it's going to be essential for the future also. So we have, I will introduce Ken Raffanetti, and then he will introduce the rest of the team. Ken is part of the Mathematics and Computer Science division here at Argonne, and he is a software development specialist. He joined Argonne in 2006 from UIUC, University of Illinois at Urbana-Champaign. And since 2013, he has been actively working in the development, testing, and maintenance of MPitch. Now he's going to start the presentation, and before you will see that we have also Pavan Balaji and other active members of the MPI team.
Thanks, Marta. Yeah, so I'm Ken Raffanetti. I'm going to be talking to you about MPI today. We have a full day of MPI, so I hope everybody's ready to learn about that and parallel computing in general. I want to thank the organizers for inviting us to do this presentation for the Petascale Institute. This seems like a really useful week of presentations for folks wanting to do parallel computation. So, like Marta said, I'm Ken. I'm going to be kicking off the presentation here, but I've got some other folks from the team I work on that are also going to be presenting to you today. One, Dr. Pavan Balaji, he's leads the Programming Models and Runtime Systems group here at Argonne. Also the development of the MPitch open source MPI library, and is very involved in the MPI forum. As well as my two other presenters, Halim Amer and Yanfei Guo. Along with myself, also develop MPitch in our daily work and participate in the MPI forum, which I'll talk about in future slides and what that means. But the point being that we are all kind of deeply involved in the MPI process, both in the standardization and implementation, and also working with users such as the people watching this presentation. That you know, in terms of MPI, we're some of the experts. We want to teach people to use MPI and make sure they understand how powerful it is and how useful it is for parallel computing. In terms of this tutorial, everything is practically oriented. We want you to take what you learn from here and apply it to the problems you're working on. We've got lots of example code. I think through the Petascale Institute, it's available in a Git repository on GitLab. There's also the link on the first slide if you want to download it from there. It should also be available. But there's lots of example codes we'll walk through as we go through the slides. Hopefully everybody's familiar with C. Everything in here is C examples. So for those Fortran people, I'm sorry, but C is a little bit easier for us to put together. Feel free to interrupt and ask questions along the way. I know we're taking questions over Slack from the Petascale Institute, but also within the room. We've got some students in the back who can run microphones. So just stick your hand up and make sure you have a microphone before you ask a question so that other people online can hear it as well. If we're going too fast or too slow, let us know, maybe during a break or something, just so we can try and pace the material at the right speed for everyone. In terms of what we'll cover, so like I said, we have a full day here. This first, it's broken into two presentations. We have a basic and advanced MPI presentation. So in the basic one, this is just kind of the quick breakdown. I'm going to talk about what MPI is. So we don't assume anyone, any prior knowledge for this portion. But in the advanced, there will be, some kind of newer concepts and a little bit more knowledge might be helpful in understanding what's going on there. But I'll give a quick introduction of what is MPI. We'll write our first MPI program and actually run it. I'm logged into one of the clusters made available for the Institute, so we'll actually try it out on a big machine. And then we'll get into some slightly more advanced topics in terms of collective communication, non-blocking, MPI data types, things like that. So what is MPI? So when you take a step back and think about computing and the switch from sequential computing to parallel computing, well, there was this thing, Moore's law, that folks might be pretty familiar with, that processor speeds for a long time were doubling every about 2 years. This is kind of plateaued in recent years, where instead of processor speeds doubling, the number of processing units on a chip are doubling, still at a similar rate. So now in your laptops or on your desktops and clusters, instead of a single core processor, you might have dual core or hex core, or things like as many as 18 cores on some of today's workstation CPUs, or something like a Xeon Phi that has many cores, 64 or even more. But because the processor speeds are not increasing anymore, you're not getting that default automatic increase in performance for your applications. Now you have to take advantage of these extra processing units through parallelism. So parallelism is now kind of the way forward and to get more performance for applications. And you can think about, a lot of processors in parallel connected over a network and coordinating to solve large problems. This is fairly common at this point. Things like the Postal Service use parallel computing to track and minimize the fuel routes for their deliveries. Automobile companies are simulating car crashes, things like that. Airlines are simulating, engine efficiency so these types of big problems, they're useful in all types of scientific domains, and parallelism is how they can get the performance they need to do the science they're looking to do. In terms of parallel programming, we have a couple of example models here of how you would achieve parallelism. The first one is through shared memory, where so if people are familiar with processes versus threads, this is kind of a shared memory is like what you would use if you were programming with multiple threads. Threads share an address space, and then they can share data in that memory through use of locks to coordinate, who's accessing the data, who can write to it when it's been updated. Another parallel model might be something like transparent parallelization, where the compiler automatically parallelizes your code for you. So it's just kind of magic. You would compile your program, and the compiler would identify which parts could be parallelized, and then you can run your code and see the benefit. Similar to that, but a little more, but you give the compiler more help, is a directive-based parallelization. So if folks are familiar with something like OpenMP, where you insert these little these pragmas into your code that tell the compiler, this, parallelize this section for me, that's a little more explicit about which parts of the code can be parallelized, and then you'll see the performance benefits of that as well. But what we'll focus on for most of the day is message passing, and this is explicit parallelization through the use of communication. So you have many processes running at the same time and communicating between each other in order to coordinate on how to do the computation. So the message passing model, a process, again, for the purposes of this presentation, we can assume a process is a program counter in an address space, like a traditional operating system process that folks know from their laptops or traditional computing. Processes might have multiple threads. A thread in this case would just be a program counter and an associated stack, but the bulk of the address space is still shared between threads in a process. MPI is for communicating between processes, these separate address spaces. And you can think of the inter-process communication like the diagram here. You have two processes running in parallel, and you use MPI to communicate between them. This communication consists of a synchronization, which we'll get into later, and then just the actual process of moving data from one address space to another. Just a quick example of how you could use message passing to achieve parallelism. So a simple example people should kind of understand from maybe a university course exercise or something is sorting an array of integers in a program. So you can consider, I have an array of this many integers, and I could sort it in that one process, and it would probably take something like this time, n log n notation, where to sort this array on a single process. Well, what I could do is I could actually divide the array into two halves and sort them in parallel on two different processes. Each one of these sorts would take n over 2 log n over 2 time. And then I could reassemble the array into the full sorted one back on the first process. So you could effectively shorten the time to sort the array, where these two portions would happen in parallel, but you would have the extra cost of reassembling it into the array, and you would have these communication costs, which again we'll get into more of that as we go along. But this is the kind of thing, you can apply this to any different concept in your work and how you can easily break problems into multiple smaller parts and run them in parallel. So just a little history lesson on the where MPI comes from. So in the early days, there was, many parallel machines being developed and built by vendors. And in terms of message passing, there were proprietary APIs for each vendor's machine. They weren't portable from one to another. So if you were writing for, say, Intel's machine, that wouldn't necessarily, that same code wouldn't run on IBM's machine. So that was one problem. Some researchers had kind of tried to tackle the problem of portability between machines. So there was several different packages that were trying to make portable message passing possible. But as I said, they were kind of research efforts. They didn't have the full backing of the vendors who were implementing the machines themselves. They may have not been complete in terms of addressing the full range of message passing issues that applications needed. And they may not have been implemented most efficiently either. These weren't necessarily production grade codes. So back in, I believe, the early 90s, 1992, the MPI forum was convened as a collection of these vendors and portability writers and users as well who wanted to standardize on a message passing interface so that codes that, the users could write codes once and see the benefits of that message passing interface across multiple machines, and it would perform well. So MPI, as I said, it's a message passing interface. The forum was originally organized in 1992. It had many of the big vendors at the time, including IBM, Intel, and some others that may or may not still be active today. And the portability writers at the time, so authors of PVM software and P4, which were, I believe, both lab and university efforts, and also application scientists and library writers. So MPI, the forum gathered and defined a standard interface. It took about 18 months, and it incorporated all the best ideas everyone could come up with in what we call a standard way. So there's a limited set of functions. They all take the same arguments. They all have the same semantics. So depending on which machine you use them on, they may be implemented differently, but from the user's perspective, they can always expect the same semantics, the same functionality to occur if they call one MPI function with the same arguments. So what MPI isn't, it's not necessarily a language. It's not a compiler specification. It is not necessarily the implementation you're using at the time. It's not a product. It's an interface specification. It's something that defines a set of functions and the meaning of those functions, what they actually do. So MPI 1, as we said, was standardized, was what came out of the original meeting of the MPI forum in 1992. It defines a limited set of functionality, point-to-point communication, collectives, and data types, which later on in the presentation we'll see more about. MPI 1, the finished standard, was released in 1994. It was part of this 2-year intensive process since the original convening of the forum. Soon after that, implementations appeared, and MPI was available on a lot of these vendor-supported parallel machines out in the wild. And fast forward to today, where MPI is just kind of taken for granted on parallel machines. It's just something you assume is going to be there every time you log in. So MPI has been extraordinarily successful in that regard, where almost 25 years ago, and it's still available today, and more or less the default way to get parallelism on large machines. There's free and portable implementations you can find on the internet if you just search for MPI-CH or MPitch or the OpenMPI implementation. These are widely available. You can download them and build them on your machine. and a lot of these form the basis of the vendor implementations you then use, your Intel MPI, your Cray MPI, or IBM MPI. So that was, that takes you up through the definition of MPI-1. The MPI forum continued to meet after the MPI-1 standard was released. So MPI-1 had, like I said, it had a kind of a limited set of functionality. There were a lot of ideas that were still kind of in the works, but folks weren't necessarily in agreement on which ones were ready to be included or not. So the MPI forum continued to meet, and in 1997 they released the MPI-2 standard. The MPI-2 standard just included much more functionality. It defined some semantics for using MPI in combination with OS threads. It added I/O functionality, so MPI for file reads and writes. It added remote memory access functionality, or RMA, which we'll talk about more in the advanced presentation, and some other things. And then you can see after 1997 that the MPI forum was dormant for a little while, but reactivated sometime in the mid 2000s. So two more standards were released in 2008 and 2009, MPI 2.1 and MPI 2.2. These were mostly corrections, some small feature additions to the MPI 2 standard. And then in 2012, after some number of years after the forum had reactivated, we did get another full interface release, full version release of the MPI standard with several new features. And then a couple of years after that, we have the MPI 3.1 standard with, again, some minor corrections and feature additions as well. If you're interested in the standard itself, there's a website, mpiforum.org, where you can go and get copies of the standard in PDF format. And also, I think you can, there's information on how the standardization process actually works. You can see things that are currently in discussion in the forum itself. And I think in the advanced presentation, there's some slides at the end that talk about some of the ongoing work the forum is doing to standardize new functionality. There's also this link here is just a general link about MPI materials. There's tutorials, exercises, more general MPI stuff that again, if you're looking for more material after the presentation, you can find helpful pointers and things there. So a little bit more about MPI-2. Like I said, MPI-2 came out 3 years after the MPI-1 standard. Defined these some additional features: parallel I/O, remote memory, dynamic process management. It added language bindings for C++ and Fortran 90 that were similar to the original C and Fortran 77 bindings. So I should say that MPI officially supports C and Fortran languages. And for a short time here, it supported C++, but we'll see that was deprecated later on. MPI-2 also defined how the language interoperability would work if you have an application that mixes Fortran and C together, how you can pass information from one language to the other. MPI-3, some of the bigger features that were added: non-blocking collectives, neighborhood collectives, improvements to the one-sided communication or remote memory access interface. MPI-3 added a tools interface where you can gather information about the MPI implementation, what's actually going on underneath the covers. It defined a new language binding for the Fortran 2008 language specification. And there's some other minor features here, matching probe receive for thread safety reasons, new communicator creation functions, some improvements to the interfaces for the language correctness, like cons, things like that. In MPI3, like I noted, the C++ bindings were removed. So the reason for this was they weren't, according to the forum working group, they weren't exactly correct for how, for the C++ language. But in general, people felt that the C bindings already existed and can be used from C++. So we can just push users in that direction and deprecate the C++ ones, as they weren't necessarily adding anything over C. And then just a minor note in MPI 3.1, which is the most recent version of the standard, aside from minor corrections and things, the biggest feature was non-blocking collective I/O, which I don't think we'll cover in this tutorial, but it's something you can check out if you're interested in it. This slide shows the current status of MPI implementations that you may encounter if you are going to be using MPI either on your laptop or on big machines. So these are on the left column here, I believe, are all the large features defined since the MPI 3 timeframe. I presume the assumption here is that all of these implementations support all of the MPI features from MPI 2 and before. But you can see the status of some of these features presently in these software packages. So the open source ones, MPitch and BAPitch, OpenMPI support all of the MPI 3 and 3.1 features, and then the vendor implementations like Cray and Intel and IBM are in various states of support of some of these newest features. Some more web pointers. So before we pointed you at the MPI forum website, where you can see the actual standard documents, the PDFs. The current one is about 800 pages, so don't think you're going to read it in a day or anything. Some pointers here to various implementations. So MPitch and BAPitch are open source MPI implementations. Intel MPI, Microsoft MPI are available. They're supported by the companies backing them. I believe both Intel MPI works on both Linux and Windows. Microsoft MPI works on Windows only. Another open source one is the OpenMPI package. And then there's again, if you're using any big machines like the ones provided for, say, the Petascale Institute, you may come across things like IBM MPI, Cray MPI, and others. In addition to finding the MPI standard on the web in PDF form, you can also order it as a book at this link. It looks like this. It has a blue cover, the newest version. Previous versions have different colors. But instead of reading the 800-page MPI standard, we would encourage most users to start with these books. These are tutorial-style books on using MPI. So the one on the left is kind of an introduction and how to write kind of basic MPI programs. And then the one on the right is using more of the advanced features, more modern features from the MPI standard, later versions of the standard. And in terms of parallel programming in general, there's this book that came out, I believe, last year sometime, that not only describes MPI for parallel computing, but a number of different programming models and software packages that some of them will get covered, throughout this week during the Petascale Institute. Some of them won't, but this book is a good kind of primer on all of them and shows the various strengths of the different programming models for parallel computing. So again, why is MPI, what is MPI? Why is MPI important? MPI today, it's got a lot of history behind it. Like you said, it's been around for nearly 25 years. It's widely used in most large-scale applications in science and engineering, particularly applications that run here at Argonne or at other Department of Energy laboratories. All types of science domains use MPI to write their applications and parallelize them. people smarter than me can make fancy visualizations of what's going on in those scientific simulations using MPI. So you can see things here like astrophysics or biology, or perhaps drilling for the oil and gas folks who are doing simulations of what's going on under the earth when trying to find natural gas, things like that. So obviously we keep saying MPI is important, it's widely used. Well, why should you use it? Well, the reasons we have here listed, as we've said before, MPI as a standard. It's available nearly everywhere. So if you write your application in MPI, it's going to be able to run on parallel machines. It's pretty much wiped out all of the prior message passing libraries before it. They all kind of coalesced into the single MPI standard. Your code is portable if you write it in MPI. You write it for one machine, it's going to run on almost any other one, and it's going to give you performance in almost all cases. That particularly vendor implementations, if you use Intel MPI or IBM MPI on their machines, you're going to see that that MPI is tuned to perform really well on that particular machine. MPI is it's a broad standard. It has a rich set of features that can fit most application needs in terms of communication for parallelization. It's not only message passing. Message passing is in the name of the interface, but it's not necessarily all that it's capable of, and you'll see that as we go through the slides and describe the types of things you can do. And again, it's widely available. It's open source in a lot of cases. You can download it, test it out on your laptop. You don't have to have access to a big expensive cluster to write MPI programs. An important note, though, before starting to use MPI is, when I had the four programming models up on the screen, 4 example parallel programming models up on the screen, the thing to know about MPI is that the parallelism is explicit. Nothing is done for you. That it's up to the programmer. It's their responsibility to find the parts of their code that are able to be parallelized, and then use MPI constructs to then achieve that parallelism. So it's you can't just download MPI and install it and link it with your application and expect things to run faster. That's not how it works. You have to think a little bit more about how you want to structure your application in order for it to run in parallel. So again, throughout this tutorial, we'll have lots of examples. One of the ones we'll see as we progress along, a 2D stencil code. I think that'll get introduced a little bit later on, but it's kind of a common use case where you're simulating heat on a 2D plane over time. And so we'll show how you can kind of divide up the space in that simulation amongst processes, and they can use MPI to communicate throughout the execution. We will walk through some actual code. I'll try and run some examples on not only the laptop but on a cluster as well, to show folks kind of taking through the steps of how to use MPI for the first time. So up to that point, that's more or less the introduction of MPI. After that, I'll start actually writing or showing people how to write code. But at this point, do folks have questions about MPI in general, or should I just keep going? All right, I think we can keep going then. So how does MPI work? So we have a little illustration here showing a programmer here. This is those of you in the audience sitting here and thinking about how they want to write a parallel code. So one way this could work is you have a code and you're going to launch it on 4 different machines, Each of these green bubbles is an instance of your application. So they get launched on 4 different machines, and then they use MPI to communicate between the machines in order to facilitate the parallelism. Similar to that, you may, that's one way to use MPI. Other ways, we might have specialized machines that, we might want to run, they might be multi-core machines, so we'll run more than one instance of your application on the same machine. They may have an accelerator or something that can aid in the computation process. I think later on in the afternoon, we'll talk a little bit more about how you can use accelerators with MPI to help speed up your application. But the general concept, again, like we said, is message passing. It's communicating from one process to another, again, I'll take you through the steps of how you do this. But what MPI what MPI gives you and how you tell MPI this, how to achieve this communication. I'll show you how to identify processes in a parallel job, and then how we describe data to be communicated between them. So in most cases, when you come across MPI, it's going to be in the form of a library. Like I said before, MPI is defined for C, C++, and Fortran applications. When you want to use it, you just sprinkle in the calls to MPI within your application, and MPI will handle the communication details. For compilation, most folks may be familiar with using a C compiler to build their code. MPI provides, in most cases, MPI provides a convenience wrapper that you could use to compile MPI programs. It works almost identically to the C compiler you're used to, but it takes care of the details of linking in the MPI library for you. And similarly, with compilation, in execution, again, most people are familiar with how to run a binary from the command line, say on Linux, where you just run / and the name of your binary. MPI, because you're going to be running, in most of these cases, multiple instances in parallel, provides this helper MPI exec program, and you provide it the number of processes you want to run at the same time, in this case 16, and then you can, MPI exec takes care of the launching all the processes at the same time, and helping them, under the covers, it helps them discover who else they're going to be running with. So a little more about process identification. So again, we've got multiple processes running in parallel in an MPI program. But in order to communicate, they have to be able to identify which ones, identify their peer processes in that parallel execution. So MPI processes are collected into groups. And each group can have a color. So this is just kind of an abstract description of how these processes can be grouped together. A group plus a color forms what we call a communicator in MPI. And by default, there is a predefined group and color, or a predefined communicator in MPI called MPI COM world, that for the purposes of most simple applications is enough for users to get started. So this MPI COM world is a predefined communication object with which processes can use to communicate with each other. It's not the only one. Like, you can create additional communicator objects. They can have the same group of processes. They can have different groups, but we don't have to really worry about that too much at the moment. Within a communicator, every process in a group has what we call a rank. So the rank is just a number. It's an integer identifying which process that is in the communicator. Ranks only have meanings within the communicator you're currently working with, and meaning a process can have multiple ranks, but only when paired with a communicator do they hold meaning. So going back to that MPI exec example I showed before, we can kind of conceive this visually as, okay, I've launched 16 processes of my test application, and my MPI-COM world, you can think of this box around these 16 processes. This is the communicator that I can use to communicate between all these processes. I can make a copy of that MPI-COM world through a communicator creation function. That was just it's simply an alias of the predefined communicator. I can make multiple copies of it, as you can see when the colors change. I can make a communicator that's smaller than MPI-COM world, contains only half the processes. In this case, the ranks would start from 0 with this process here on the top left, perhaps. But again, just to try and visualize this, you could also create a communicator with this group of 8 processes, and then this would be rank 0. And in fact, for this process here, where the communicators overlap, it would have rank 1 in one communicator and 2 in another. So this is just trying to, again, illustrate the concept of how you can use communicators to form different communication objects, and perhaps you can use them to divide up the types of work you're doing or something like that in your application. There's also, the communicators can be created by hand. They can also be created by tools. We're not really going to go over those topics today. But again, and for most of the simple examples, we're going to use MPI-COM world only. So it's fine if this isn't quite catching on yet. I did try and do a 3D visualization of the concept from the slide before, where you can see all these different communicators. The point being that you can use multiple communicators to build these kind of independent layers of communication, where messages on one layer won't interfere with another. So you can think about this perhaps from if you're a library writer and you want to use MPI from your library, one of the first things you might do is create a duplicate of the communicator of MPI-COM world so that the messages in your library don't interfere. I can't. Okay, I'll try not to use the laser pointer then. Will the mouse show up? Can people see the mouse? Okay. In which case, they might not be able to see me because the camera's not pointed at the podium, but. Okay, maybe it's a good time. This is a lot of information. Are folks more or less clear on the concept of communicators? If not, like I said, our examples are just going to use MPI-COM world, so not a big deal, but maybe we can. Okay, the mouse is good. Okay. So I guess at this point it might as well start writing our first MPI program. So I'm just going to go through a really basic example line by line and show people what all is necessary to write your first MPI program. So here we have a fairly minimal C program. So we have our main function, and the red lines here are highlighting the basic requirements for every MPI program. So one thing you're going to notice is you have to include a header file, mpi.h, in order to have the definitions of all the various MPI functions. And the only other requirements are that you initialize MPI and you finalize MPI. It's recommended by MPI that you do initialization as early as possible in the program's execution, and then only that you finalize, once you're done with all MPI communication, then you have to call finalize to make sure the library gets shut down cleanly. So this MPI init call here, you can see it takes 2 arguments, C and argv, which are actually passed. We just pass in from the main function definition. So the reason for this is that MPI init in the past may have been the point where parallel processes were actually launched. And so if you just ran your program as a single binary and passed in some arguments to it, MPI could take care of passing those arguments to additional processes that were launched. In practice today, that's not really the case. You typically launch your program with MPI exec, and you can pass the arguments right there on the command line. And in fact, MPI init will take null in these two parameters. So it's but this is kind of shown for compatibility's sake. In this simple example, we only make two other MPI calls in this case, a function called MPI com rank and a function called MPI com size. So what MPI com rank does is it takes a communicator input argument, in this case MPI com world, which I described before as the predefined communicator available to all MPI processes. And in the second argument, we pass in a pointer to this rank variable. So what MPI is going to do in the call to MPI com rank is write the value of that process's rank in the communicator of MPI com world. Similar in the next call, I pass in MPI com world as my input communicator, and what MPI will do is write into this size variable the size of that communicator, how many processes are actually participating in the communication. This printf here is I'm going to print these values after MPI gives them to me, and I'm going to try and drop down into a terminal and actually run this as an example. So let's see.
Just before you're on your examples, so we got some interesting questions on Slack. One of them is there some healthy number of layers to use? Which number of communicators?
Right, that's a tricky question to ask. So communicator creation can be expensive. It's a collective process, which we haven't really gotten to that part of the discussion yet. But in general, the more communicators create, the more expensive they are to use. That there's actually a limited resource within MPI that again, the more you create, the fewer become available, and the more things internally MPI has to track. So I guess my answer is be thoughtful about the number you create. Just creating them frivolously will have impact on the performance of your application, but there will probably be some number you need to create in order to achieve what you're trying to do. Another question over here.
Hi. If you duplicate the same communicator, is this going to use the same communicator, or is this going to be like the whole new communicator?
In practice, it's going to create a whole new communicator, because there needs to be something that allows that identifies communication from one versus the other, so that they don't interfere with each other. So, I mean, in practice, at least internally in MPitch, we create a whole new object, and I believe that's how most MPI implementations do it. Yep. One more.
So when you create like the same communicator, like because they will have like the same properties and everything, right? So what is the point of creating the new communicator? Why don't you use the same communicator?
So communicators can, when you create them, they can also be freed. So just because you created one that's a duplicate of another, it doesn't mean that other one is going to stay around. The user might free it, and then you go to use your instance of it. Now, potentially you could do things like reference counting and things like that to make sure objects stay around. But this is kind of getting into the details of the implementation more so. So maybe we could discuss that offline. But there's trade-offs to one approach versus the other. But in general, yeah, we just create additional objects to make it easier on the implementation. Font bigger? Okay. Let's see if I can make. Yeah. Well, there's not a lot of output, so hopefully this will work. Okay, so like I said, I'm gonna try and run that example program we showed before. So it's if you got the code from either the link on the slides or from the Git repository, the code here is the intro hello.c program. So as I showed up on the slide, where with a typical C program you might run GCC to compile it. In this case, I'm going to use MPI-CC because it's an MPI program. So I've got my intro hello code, and I'm going to name my binary intro hello. And so now I have my executable, and I'm going to run, in this case, my laptop has a couple of cores on it, but I'm going to run four instances of my hello world program. Uh-oh, and it didn't work. All right, let me move over to this cluster here, where I have the examples as well. Make font a little bigger again. Always a gamble to live code. Okay, and you can see the output of the program here. So I have four instances of programs. They print their rank and then the size of MPI com world. So just a quick note, obviously the ranks aren't in order. And if I run this program again, you'll see that, in this case, they did come out in order, but the order will change from run to run. So the reason here is that, again, we're running these processes in parallel. This is not a sequential code. Some might be faster than others, and MPI only prints the output in the order in which it completes, but it's not deterministic. So again, it's a good illustration of the fact that these are not sequential processes, that these are running in parallel, and the output is just coming as each one completes. Another thing to note, which we typically get questions on, is so I ran 4 instances of that program in that particular run. I don't know how many processes or processors, how many CPUs are actually in this machine, but it's not required that I run. These keep coming. It's not necessarily the case that I have to run as many processes as the computer has CPUs. I can run fewer. I can actually run more, and the OS will just schedule them in the order that it can. So I can run, say, 16 instances of my program. If my computer only has 2 CPUs, it'll just schedule them as it can. There's no, but it's not required that you run fewer or equal to the number of CPUs your machine has. Are any questions about the basic example? Got one in here.
In the large scale cluster case, so when I'm submitting a job, I usually request like how many nodes I want. And so you talked about like kind of a round robin scheduling thing in case of a single node and related to cores. Could you speak a little bit about like allocation in across multiple nodes, and
Right.
is that something that the developer needs to specify? Which machine am I going to use? And
so in terms of, and I think I have it detailed on a slide later, but yeah, when you're interfacing with a large scale cluster, typically there's a scheduler and a resource manager that allocates nodes for your job to use. MPI exec will actually, when you write your batch script that actually executes your job, MPI exec normally can detect which nodes have been allocated for you and will take care of placing the processes on the right nodes. You have to do a little bit of tweaking to say, that's depending on if you want to run, one process per core versus one per, socket or things of that nature. And also, you also may need to take some care to map processes to nodes in the correct order that you want. That's all kind of takes some playing around and getting used to. But in general, yeah, MPI exec, if you just run MPI exec with some number of processes, it will run them on the nodes that have been allocated for your job.
This rank and size are private variables for each of the process. When the process is large, they create their own variables.
I'm sorry, I'm not sure I got the question. These are private variables, yeah. Each of the processes. But I'm not sure if I got the question at the end of that.
Yeah, thanks.
Okay. All right. Let's see if I get back to the presentation. So that's our basic hello world. That's you know, if you've been able to run that, that's your first MPI program. Oh, and that's a reminder to go down into the terminal and run it. But what we haven't done yet is actual communication. So we've been able to identify processes in the MPI-COM world communicator, but now we have to tackle actual communication between them. So just as a kind of a high-level description, again, MPI, data communication with MPI is a little bit like an email exchange. One person sends data to another, they receive it, and they do something with it. In terms of how to describe this communication, on the sender side, you need to know who I'm sending the data to. We do this using the communicator and receiver processes rank. I need to tell MPI what kind of data I'm about to send. So in some cases, you know, maybe I have 100 integers to send. I have 200 characters, C characters or something like that. I can define what's called a tag for the message. Tag is just an extra bit of information, almost like an email subject, where you can the receiver can check it and say, oh, this is this kind of message, meaning I can do something with it based on that information. On the other side of that, with the receiver, they might have to know a couple of these things. They don't necessarily need to know them at communication time. The receiver might need to know who is sending the data, so they can specify a rank in a communicator for where they're expecting data to come from. If they don't know, they can specify this special value MPI any source, meaning anybody can send to them from in that communicator any rank. They might need to know what kind of data is going to be received, but they don't need to have 100% of the information. So I could tell MPI, you know, I can receive up to 1,000 integers, but if I get less, that's okay. If I get more, it's not, because I won't have the buffer space internally to receive all the data. So, but I can specify more. And again, I might need to know the tag of the message coming in, but it's not necessary for me to specify it. I could use another special value MPI any tag that says, I don't care what the tag is, just give me the data. A little more details on describing the data in terms of what kind of data. So in C programs, MPI data types, there's MPI predefined data types that correspond closely to the language types. So in C, if you're sending ints, you'll use MPI int. If you're using doubles, you use MPI double, chars, MPI char. There's more complex data types available. You can create user-defined data types based on the data structures in your application. You can do things as general as like a struct, where you might have some structure you've defined for your application code that contains multiple different types. If you have a large array and you want to define some vector portion of that array, you can also do that using MPI constructs. And then the count argument, I think we'll actually see the function signature on the next slide, but the count argument tells MPI how many of these individual data types you're going to send. So you have the type and you have the count to tell MPI how much data there is. So this is the basic MPI send function signature. So just to kind of go through each argument here, the buffer, the data you're sending, is described using the buffer, the count, and the data type arguments, the first three. The target process is destination and communicator. So destination would be the rank of the process you're sending data to, and the communicator in most of our simple examples will be MPI-COM world. And then tag is the type of message. When this function returns, so now we get into kind of the meaning of these functions, what happens when you actually call them. When this function returns, it means that the data has been delivered to the system, not necessarily the destination process, but it's been delivered. MPI has the data, and the buffer is ready to be reused. So if I allocated this buffer here, this buff, and I filled it up with data that I needed to send to another process, when my call to MPI send returns, that means I can modify that buffer however I want, but the data that was in it when I called MPI send will be what appears on the destination process. The next example will show a little bit more about how that works. So with MPI send, you're usually going to pair that with some sort of receive function. So we have here the basic MPI receive, very similar function signature with a couple of key differences. Again, we have some arguments here, source, tag, and com, that are used by the MPI implementation to match messages that are incoming. So if if you're expecting a message from a particular rank with a particular tag on a particular communicator, that's how these are the arguments you use to specify that. Unless, of course, you don't know and you used something like an MPI any source variable. Like I said before, you can specify receiving up to this many data elements in the count argument, but it's okay to have less if that's the case. More, again, would be an error because you wouldn't have any place to put them. And then there's this extra argument here, the status argument, which can tell you a little bit more information about the message if you're interested. So if you did use, say, MPI any source in your source argument, the status, when MPI receive completes, the status can tell you who it actually came from, if you care about that. If you specified, a large count and you thought you might get less than the number of elements you specified in count, then status can tell you how much was actually received. Similarly with the tag, if you used an any tag, the status can tell you what the actual tag was of the message you got. But if you don't care about any of that, you can also pass in this MPI status ignore value into the last argument, and you can tell the implementation, I know enough to work with this data, so I don't care about the status. Don't even bother filling one out for me. I'm not going to allocate one for you. So that's send receive, and now we can take a look at an example program that uses these constructs to actually perform communication. So on this slide, again, we kind of start from our example, our Hello World example before. In this case, everything's mostly the same. We initialize MPI here early on after declaring some variables. In this case, we have a buffer here. It's an array of 100 integers, this data argument, or this data variable here. And then down here we get into, I should use keep forgetting to use the mouse. Down here we actually get into the meat of the communication. So in this case, depending on the rank of the process, they take on a different role in this application. So rank 0 here, where'd my mouse go? Rank 0 is going to be the sender. If my rank matches 0, I'm going to send data from the data buffer, in this case 100 integers. My destination rank is rank 1. My tag is 0. And my communicator is MPI COM world. If my rank is 1, I'm going to be calling MPI receive. My arguments are almost identical at this point. I'm going to receive the data into my data buffer. Again, the data buffer is private to each process. So data that's present in rank 1 won't necessarily be present in rank 0. So in this case, we use MPI to send from one to the other. I'm going to receive up to 100 integers. They'll be of type MPI int. My source is rank 0. My tag is 0. I'm communicating using MPI COM world. And because I've specified all the arguments exactly, I can just ignore the status in this case. So I have an example. So that the example code, oh, I shouldn't have done that. The example code in this case is not 100% identical to the one on the slide. But I can open it up here and go over it really quick. Hopefully people can see this. But the key differences here, so in my case, the data, my buffer is only three elements long. It's 3 integers. Rank 0 is actually going to populate the buffer with some data before sending it. So I just initialize the values in the data array. Same thing on the receive side in rank 1, who's going to be receiving the data. I initialize the array as just some dummy values so that I'll know if data comes in that it's changed. And then you'll see when I run the application, I'll print out the values of the array before and after receive happens. Is that hard to see? Probably better on the screen share. I don't know. This is just the default Emacs highlighting. Maybe VI is better. Hopefully I don't get stuck in it. I don't know if that's easier to see or not. But anyway, we'll see what the output, and folks can check out the code from the repository if they're curious to, they want to look at it closer. Okay, so again, I'm going to compile my program, my MPI program, using the MPI compile, MPI CC compiler. Control send receive. And so I'm going to execute this. So my program requires at least 2 processes, right? I'm expecting a rank 0 and a rank 1. So in this case, I'm going to run 2 processes, 2 instances of send receive. And you can see that the prefix here is that rank 1 is printing out, before I receive the data, my array contains -1, -1, -1. And after receive completes, the array is updated and it contains the values set by rank 0. Any questions about this, this simple example? Good, fairly straightforward. If you're curious what would happen if I ran with less than 2 processes, which is not necessarily parallel, but what will probably happen is MPI will throw an error and say, there is no rank 1. I don't know what you're trying. You're telling me to communicate with a process that doesn't exist in this particular execution. So it throws an error and prints a little message here to tell you what it thinks you did wrong. If I run with more than 2 processes, my output is exactly the same. I didn't give any extra work for ranks 2 and 3 in this case to do. They just passed right over the MPI communication calls and went right to MPI finalize. But there's no harm in having more processes in this case because they didn't get any extra work to do. All right. So building on top of that simple communication example, we can think back to the parallel array sort I introduced earlier on, and how you could potentially use MPI communication to do this, to do the step here of dividing the array in 2, handing portion of it over to another process so that it can be sorted in parallel and then reassembled. And so we have this kind of mocked up in kind of pseudocode here. This example has the sort function is just assumed to exist on the system you're using. In this case, we have the full array is 1,000 elements long. We use MPI send to send the upper half of it to rank 1. Rank 1 receives it in this array B. Process 0 or rank 0 and 1 both sort the array at the same time. And then after rank 0 is done, it waits for the result from the rank 1 to come back. And then in this commented out section, it would reassemble the arrays back together as one big sorted array. So that's kind of the, again, just building on the examples prior, this is how you could, one potential way to use MPI constructs to kind of do, to identify and achieve parallelism in your code. A little bit more about the status object I talked about before. I think I covered almost all of this, but just go over it really quickly. Like I said, the status object is helpful in the case where you may not have had all of the information when calling MPI receive. So you can get things like the MPI, status is kind of like a struct, a C struct, where you can just use the dot operator here to access what the source of the message was that you received, what the tag was. If there was an error, it can tell you the error status of the message. So if your receive didn't actually complete successfully, there might be some error information you can get from here. There's also an additional API call, MPI get count, that takes the status as an input argument and tells you, it takes the status and the data type you received as input arguments, and it tells you how many you actually received. So again, if you may have specified, 1,000 integers you were going to receive and you actually got 500, then this could, you use this call to find that out. You can't just call status.count to get the number received. You have to use this API call, and that's just for portability reasons, internal implementation details, which if you're curious about, we can talk about. Not really in the scope of this. So as kind of an actual practical example of why you would use the status object, you could think of a master worker type algorithm, type parallel application, where you have one process, one rank here, distributing work to one or more processes, and each of these processes is doing the work and sending results back to the master, and then waiting for more work to come in. And so depending on the speed of computation at the various processes or how things are getting scheduled, it's not set the work you're going to be doing, so that the master is kind of distributing it ad hoc. And so if you're a worker and you get a message, you can inspect from the tag and from the source rank perhaps, or the type of data you got, and you could figure out what you're actually supposed to do with it. So that's just one example use case. Master worker is kind of an easy to understand parallel application algorithm where you have one process distributing work to others, and then they're kind of independently working and sending results back. And then this is just a quick code example again of how you might actually use the status object. So in this case, we'll just go through it quickly. My master process here is assumed to be rank 0. If I'm not rank 0, I'm sending the results of my work back up to the master. And in this case, the data, for illustrative purposes, is just some random number less than 100. But the master process in this case is always ready to receive 100 elements, 100 in this case integers, from any rank in the job, of any tag, and after the fact, it's going to say it can get the count, and it'll know that, oh, this worker of rank MPI source, which was working on this type of data, this type of tag, sent me this many elements. So it's just kind of an illustrative example, and not kind of a toy program. Doesn't have much meaning, but any questions about how you might use the status object? All right, we'll keep moving here. I know that the Institute folks encouraged us to leave some time at the end of each section. So I think, depending on how we wrap up here, people can play around with some of these example codes and they can ask questions. Myself and my other presenters can run around and try to answer questions if possible, or we'll be on Slack too to try to help folks. So, yeah, we've gotten through the point of writing our first MPI program, our Hello World, our first program that actually does communication. We've seen ways to use MPI to kind of distribute parallel work to one or more processes in an application. And doing that, we've only used these 6 functions. So the title of this slide is MPI is simple. You may or may not agree with that statement, and those of you with some prior knowledge of MPI probably don't think that. But for as just the argument we're presenting here is that for most parallel applications, these are the only 6 functions you need. That you can achieve almost any parallel application, algorithm, paradigm using these 6 functions. There's a reason we say that. And I don't know if anybody here wants to hazard a guess as to why we say that these 6 functions are all you need to write a parallel application. But if you do, feel free to pipe up. But in most cases, for performance reasons, or depending on your application and the algorithmic design you're trying to achieve, you're probably going to want to use different MPI features in order to write your application and get the best performance you can on the machines you want to run on. So I've run a couple of examples up until this point. They've been simple programs on a single machine. Now, in the next section, we're going to tell you a little bit more about MPICH or MPI-CH, which is the open source MPI library we develop here at Argonne, and how you can use that to kind of start playing around with MPI and learning how to use it. So I'll give a little background about MPI-CH. It's open source. It's widely available, high performance implementation of MPI. It supports all of the features you saw on the implementation slide, all the green check marks. It supports all the features that have been defined by the MPI forum up until this point. The development lead is done by our group here at Argonne National Laboratory, but we have various collaborators at the University of Illinois, and then also in other industry and academia groups that participate in the MPICH effort. So just a short but non-comprehensive list: IBM, Microsoft, Cray, Intel, some of these others, Ohio State, Queens. Current release of MPICH is version 3.2. You can find it at our website here, mpitch.org. You would download this, like many open source softwares you find in for use on Linux or other Unix platforms. It's you can get the gzip tarball of the code. You unzip it, you configure, make install it, and then you have you add MPICH to your path, and you have your MPI-CC, your MPI exec wrappers and executables that allow you to use MPI. Yeah, like I said, so MPICH will come with. Oh, we have a question.
Ask a question. And so, can I install and run MPICH on usual clusters or supercomputers without sudo permission? I mean, from user.
Right, that's a good question. You can, as long as you specify where to install MPICH in a place that's writable by you. You can install it in your home directory and then add it to your path. But you don't need any special permissions to use MPI to communicate. It's all done at the user space level.
I can correctly run an MPI exec or this kind of.
Correct. Yes.
Right. Thank you.
Yeah, just I know we've seen these in the past now. But MPI provides, or MPICH in particular, provides compiler wrappers for C applications, C++, and Fortran, and these work more or less exactly like the compilers you're probably used to today. If you want to, if your program requires you to link to other system libraries like the math library, you just link them at the end of the compile line as you would regular C compiler. For the purposes of MPI programs, you can just assume that MPI-CC, MPI-CXX have just replaced your regular compilers. You wouldn't use GCC, you would just use MPI-CC in replacement of it. I've showed a little bit about MPI-exec so far. MPI-exec is how you launch processes in parallel. This first line is an example of how you would launch, say, 16 processes on a single node, on the local node you're running on. We had a question before about integrating with, say, or you may be running on multiple hosts. If you don't have a job scheduler and you just have access to a bunch of nodes, say in a general purpose computing environment, you can specify a list of them on the command line. In this case, host 1, 2, 3, and 4. And then the colon notation here says run 4 processes on each of these nodes. But you don't have to specify how many you want on each node. MPI-exec will internally use some scheme, be it round robins, be it, or by default it uses round robin to map processes to a node. So in this case, if I don't specify, host number 1 will get rank 0, host number 2 will get rank 1, and it'll wrap around at the end and start over. If you have a lot of nodes, you may want to just create a file with all of them defined, one per line. Same notation as if you were specifying them on the command line, but just maybe a little easier to deal with if you have a really long file or something. As far as example problems, if you've downloaded and installed MPitch, well, you want to try it out and make sure it works. One thing that comes included in MPitch when you build it from scratch is this cpi.c executable. It's I think we actually cover it in the collective section, but it's an example program that calculates pi amongst however many processes you have running. So it's a good way to test out your installation, make sure it's working, and you can see, it prints out a lot of helpful information like what host processes are running on, what their ranks are, things like that. So typically if we get questions about, oh, I don't know if I did my installation right, so I'd try out cpi and make sure it's working. And then, yeah, once you get it working on a single host, try it out on multiple and see how it goes. If things don't work as expected, we have a mailing list, discuss@mpitch.org, where you can ask us questions. So it's free to, open to subscribe to mailing list where, and you can check back through the archives too to see if people have had the same problems as you in the past. But someone from the MPitch development community will pipe in and try and help you with your problem if you're unable to get up and running. And yeah, in terms of resource managers, so for what all that previous was assuming you just were running on kind of a loose collection of nodes. But if you're going to run on a cluster, that cluster probably has some sort of resource manager that handles scheduling and allocating nodes to jobs. MPitch will generally just automatically detect and figure out what the right thing to do is when launching processes. So this is an example script for a PBS based cluster. In this case, when I say MPI-exec, my test program, because in my job submission I told it how many processes I'm actually going to run, I don't have to specify that on the command line. MPI-exec or MPitch will detect that from the jobs environment and know exactly how many to run. And so here, yeah, this is a example job submission line for a cluster where I say I'm going to have 2 nodes and I want to run 2 processes per node. And if I just ran this, MPI-exec would know I'm going to run 4 total processes, 2 per node. I think I might even, I'll try it out on Stampede here in a second. Their system's a little different, but the concepts are generally the same. A note about debugging. So MPI programs, yeah, it's it's really easy to write them. And so far we've shown some simple examples, but as your codes get more and more complex and you're running more and more processes at the same time, debugging can become difficult. So MPI provides some things that can help you in terms of integration with common commercial debuggers you may encounter on large scale systems. So if you're familiar with something like TotalView or DDT, they have integrations with the MPI library to help you debug. I'll try and show an example of that too. We'll see how it goes, but I'll show how you can start running an MPI application under DDT and debug it further with that. If you don't have access to a commercial debugger like TotalView or DDT, you can do kind of more complex launch lines with MPI exec, this colon notation, and the details of this aren't all that important, but you can say, for instance, launch one process under a debugger while the others are not. Say you're launching 6 total processes where the 5th one would be running in a debug environment, and then you can kind of step through and use GDB as you normally would to debug what's going on with that process. So yeah, I think it drop down and try and use Stampede and see how it goes. Show a few examples. So I think for the purposes of the Petascale Institute, folks who are participating in that, they have access to a number of machines. I'm actually going to go through the full job submission batch script in this case, but what Stampede does provide is kind of a convenience script to acquire a node in interactive development mode. So in this case, you can actually acquire 1 or more nodes. So in this case, I'm going to acquire 2 nodes, and I'm going to run, let's say, 2 processes per node, kind of like our example before. Yes. And so, yeah, the resource manager is going to handle allocating the nodes for me, and it's going to automatically log me into what they call the master node or something from within the allocation. And so now I'm actually running on one of the compute nodes, and I can use MPI exec. In this case, I don't think I have to specify the number of processes. And I can say run my hello world program. And what would probably be more helpful is if I had something that told me where my processes were actually running. So let me try the CPI example as well. But you can see that internally MPI exec knew to launch exactly 4 processes because I allocated 2 nodes and said 2 tasks per node in this case. Oh, I don't need to specify. Oops. Yeah, and so now you can see from the output of CPI that I have 4 total processes. Ranks 0 and 1 are running on one node. Ranks 2 and 3 are running on a different node. So again, MPI exec kind of took care of handling all of that internally. The user didn't have to specify anything extra. Now, the next thing I'm going to try is debugging. This will be a little bit trickier. Hopefully it works. But on the Stampede cluster, DDT is available. Shoot. And let me see if I can try this. Try to get access again. Pay no attention here. Oh, that's not the one. I just need to get access really quick. Ignore this. Live demos are always a little tricky. Okay, so I'm going to try and fire up the debugger one more time. In this case, yeah, I have to load it from the modules environment. Let's see. Let's see what happens. Are any other questions while this is loading up? This might take a few seconds to come up. Okay. But anyway, yeah. So the DDT debugger provides actually mechanisms through the user interface here. Grabbed the wrong thing. To facilitate launching, running and debugging parallel applications, and it integrates directly with MPI. So in this case, yeah, I'm going to launch one of these example binaries with a set of arguments, and this is the stencil example we'll learn about more later in the tutorial. And in this case, yeah, I'm running. I want to launch four processes. I'm going to debug these all in parallel. In this case, I'll only use a single node, and yeah, so I specified all this ahead of time, and DDT is going to take this input and launch my application automatically. How can I make this go away? Yeah, I can't. And so, yeah, there's a little status box here that shows the job getting submitted, allocations granted, and it's starting to run. I apologize if this font isn't easy enough to read for folks on the screen share. I don't know if I can make it much bigger. Okay, so DDT has taken the initiative to actually launch my parallel application, and you can see in the debugger it's captured the execution and stopped all the processes right at MPI init. So there's integration between the MPI library and the debugger to know, oh, this is an MPI program, and someone's debugging it. Let me stop all the processes at MPI init, and then I can go through and individually step processes through various commands. I can make this thing go away. I can control processes individually as a group. So in this case, if I want to run to a particular line in the code, at the same time, these processes will run to say, so the middle buffer here is just the code, the source file. You can interact with interact with the processes like that. It has this is kind of more advanced than what we talked about so far, but you can actually peer into the internal state of the MPI library and see how the internal message queues are set up. I don't know if that's going to work this time, but yeah, I think something didn't work quite right when I tried. Normally, you might see arrows here showing outstanding communication between processes, but you have a visualization here of the four processes that are running, and you have information down here about various state of communication, outstanding calls to MPI, what actually is going on. So, so these tools exist on a lot of clusters you may come across, but if you don't have access to a fancy parallel debugger like this, you can still use things like GDB to try and figure out what's going on under the covers. So that's just a quick demonstration. So I think we still have, sorry, I don't know why this thing won't go away. We still have about a half hour before the next break. So before I start and hand over to my next presenter, are there any questions about, basic MPI, running basic MPI programs? All right. Well, let me see if I can get the next presentation set up then. All right, so for the next part of the next half hour before the break, the next presenter will be Yanfei Guo. He's a assistant scientist in the Programming Models and Runtime Systems group here at Argonne. And he's going to tell you about some of the more advanced topics in this basic MPI section.
Hello, can everybody hear me? Okay, so for the slightly more advanced topic in MPI, I'll be mainly focused. We have three pieces here. One is the collective communication, and then we have non-blocking communications, and at the end we have MPI data types. So I'll be covering the collective communication and the non-blocking part mostly, and if we have time, we'll talk about the MPI data types, but if we don't have time, the contents are still in the slides here. You're welcome to check them out. So first thing is collective operations. So as you already have seen, you can do send and receive communications with MPI between every processes. But the reality is, in the application, you may want some operation that every process has to participate and exchange some information. For example, if you want to have some parameters or configuration you want broadcast from your master to the slave processes, you can do individual send and receive between each pair of these processes, but it'll be hard to code them and in a clean way. So what MPI provides is a set of, we call it collective communication. So these operations are requiring all the processes in a communicator or in a group to participate, and they will exchange some information. For example, the simplest case will be MPI bcast here, which perform a broadcast, which you take one process as the root who hosts the data that need to be transmitted, and it will send the data out. And we also have some other things like MPI reduce, where you can grab data for each process and perform some computation on top of it. So the point of using collective communication is, one, it's much simpler for you to write a clean program. Imagine if you want to do with MPI bcast, you can do broadcast by one line. But if you want to do it with send receive, you have to figure out which process I should talk to first, and how maybe write a program in a loop and synchronize all the processes to make it work. But with collective communication, you only have one function cost. And the second thing is, because these are library provided functions, so the library usually have a more optimized implementation for you. For example, bcast will be done in a tree-based bcast, and even better, some hardware may support hardware accelerated collective, which the MPI library will exploit if you use collective operations. So there are, so like I said, the communication happens in a group of communicators. For individual of them, you don't really need to specify where to send and where to receive for most of the case. And also, there is no tag in each collective communication. So if you want multiple collective communication happen at the same time, and you want to differentiate, you might need to create multiple communicator, which this my answers the question of in the previous part, where when you want a different communicator or duplicate communicator. And notice that we also have some non-blocking collective communications in MPI standard right now, but that part won't be we are not going to cover those part in this tutorial, but you're welcome to check them out. So there is, if we look at all the collective communication, there are three categories. The first one is for synchronization. There's only one function for them, is MPI barrier. Basically, every process will call MPI barrier, will block on there until every one of them has called it, and they will proceed across the barrier. So it serves a simple way for you to synchronize over a bunch of processes. So if you look at it only takes one parameter, which is the communicator. So these could be MPI COM word, which essentially means you're doing barrier on all the communicators, on all the processes, or you can create sub-communicators and just to synchronize and doing barrier within that small groups. That's what the synchronization does. The second set is a much larger set, which involves data movement. Basically, examples like broadcast, where you have one data and you're trying to spread a copy across all the processes, or you have a more complex way that you have a set of data where A, B, C, D need to be distributed to each individual processes. Then you can use scatter, and it has an inverse operation called gather, where one process getting the data from each of the peer processes. And more complex, like all gather and all-to-all communication, give you all different ways depending on the need of your application. And lastly is the third set is called collective computation. So what it does is, for each process, it has a piece of data that involves this operation, and these data will be fetched together and perform some computation, which is the function f on top of here. And the result will be only one process will get this result, but we'll see some other collective function that's also distribute the result. And more complex version is scan. Basically, it gradually gather the data and calculate the results. So for all these basic examples, there are many other collective routines, such as MPI all-gather and all-gather V. The differences here is for these versions that has an all prefix, they're basically doing two things together. One is, for example, MPI gather, for one process, you fetch some data. But the all version basically will distribute the result to all the processes. So instead of one process getting the data, each of them will have the same copy of the gathered results. And the V version is related to the data size you're doing the transmission, because the basic version of collective operation, they are very symmetrical, and assuming each process is sending the same amount of data with the same type, but in reality, your application may need to distribute a data segment with a variable length. That's where you need to use the V version of collective routines, where you can provide a list of sizes to indicate how much data is being transmitted for each peer processes. And also for the collective computations, we have a different operations, a set of predefined operations that you can use. For example, you can do max min, and you can do a summation. But MPI also allow you to define your own operations. It's as simple as using you have to define a user function and use MPI op create and to create these MPI op object, and you can use them for your collective operation. So each of these user functions are very simple. Basically, you have two array as your input. One is one and one array as output. So the function essentially is looping over these each element in these two array and perform your defined operation between each pair of these elements. But notice that there is some restriction if you want to define your own operation. First thing is your function has to be associative, because the underlying algorithm for collective operation may change the order when the data, which part of the data will be evaluated first. So for example, you have like 4 process 0, 1, 2, 3, and maybe the data from rank 0 and rank 1 are evaluated together first, and then 2 and 3, and then together. So we need the operation to be associative in order to guarantee the correct result. But on the other hand, we don't require the commutative, because the overall order of these evaluation will not be changed. It's we always follow a fixed order of them in order to do that. So with all that information, let's look at an example where collective operation can be quite useful. So here's the basic algorithm of CPI, which which is an algorithm to calculate pi. So the idea is in order to calculate the area under this curve here, we cut them into small slices and allow each process to calculate the area of these individual slices, and then we sum it up. In order to make it work, the first thing is we have to tell each process which part of these area or which slices they need to calculate. So usually, what we do is we can define the total number of the slices and distribute this number to the process using MPI bcast. So everyone knows how much slice in total, and they can calculate how much I need to compute. And with the rank and size information, they can uniformly decide which process owns which segment. So then, and after that, they can do the computation. And then at the end of the computation, all we need to do is MPI reduce with a summation operation. Basically, this will add up the size of each individual slices and put the results in one of the process, which usually we choose rank 0 to do that. Then we can output the results. So here's a code snippet. Basically, see, it involves 2 collective communication. One is the bcast, which distributes the number of segments, and one is the MPI reduce, which give you the sum, of all the segments. So if we look at the slides here, I can try to show here. So if you look at the source code, there's a CPI. There's a CPI.c file. If you open it, and you see, you see here is basic example, and you see. So initially, we have a predefined number of 10,000 segments under the curve, and what we did is we broadcast them to all the process, and here is the calculation of the size of the area for these individual slice, and then there's the reduce. And at the end of it, we let the rank 0 to output the results, and then you get your pi number. So I think let's see if let's build it and see how it works. And well, as you may know, this is exactly the same program that can show you a couple minutes later, but that gives you the gist of how the collective communication. Basically, that's all I want to cover about collective communication. So is there any questions you want to ask? No? Is there any question over Slack? thing. So the plan is maybe we take a break right now, and after we come back after the lunch, I'll do the non-blocking communication part. All right. Thank you very much. Okay, everybody, welcome back. Let's continue on our discussion about the slightly more advanced topic on MPI. So here, the next thing I'm going to talk about is called non-blocking communication in MPI. So, but to understand that, why it's not working? Okay, yeah. So to understand that, let's look at what are the differences between a non-blocking and blocking communication. So first thing is we have seen MPI send and receive as examples for basic MPI communication, and here's I want to introduce them as blocking communication calls. What a blocking communication calls means it's doing the communication, yes, but it also implies a completion. By completion, I mean basically depending on you're doing a send receive, the completion may mean different things. For example, if you're doing MPI send, when your MPI send returns, it means your send operation is complete. The completion here means you can reuse your send buffer for something else. You can write the data for the next thing you want to send, or you can reuse buffer for something else. Whatever you change, whatever you did to that buffer won't affect the message that is being sent to. Although the fact that the message may be still buffered in somewhere in the system, or maybe it's on the wire for transmission, so it may not reach the destination yet. But at that point, your send operation is completed, and you're safe to reuse the buffer. Similarly, if you think about the MPI receive, the completion of receive means your receive buffer already contained the data that you're supposed to receive. Then means you can read from it, which is which is simpler for send. But on the other hand, we also in MPI we introduce these non-blocking communications, which here as we take MPI ISEN and iReceive, for example. They still do the send and receive work, but the return of this individual function doesn't provide the semantics of the completion, meaning that something is still going on, but there is something is still going on in the MPI library, but your application may have the chance to do some computation, maybe overlapping with the communication. So most of the time, you can the place you use send and receive blocking calls, you can try to use non-blocking communications in order to improve your performance and efficiency. So that, as I said, for blocking and send. However, I gave the example for the completion semantic about the buffer reusing, but the reality is the actual semantic of the completion may vary depending on what kind of machine, what kind of network you're using, and it also depends on the size of your message. So in some cases, if the completion may means a more strict may have a more strict meaning that requires the delivery of the message. In that case, if you look at this example here, where two processes trying to talk to each other, and you notice that both processes are trying to do the send at the same time, and then do the receive for the corresponding message. The reality is, if you run this code, it may actually deadlock on your system. So if we look at how the send receive is working in this diagram, you see here on the left hand side you have MPI send. At T1 time you call the MPI send, and at T2 the MPI send returns, means you can reuse the buffer, but the message is still in transmission. And on the receiver side, when you call receive, and it will block until this point when the data is received and can be read. So in this case, it probably won't block for the previous example, but in some other cases where your T2 may be delayed to a later point where T4 is, and that in that case, because both of the processes trying to do send and no one is receiving the message, you will into a occasion of deadlock. So a simple way to avoid that kind of situation is that how about we do the message transmission? We separate the message transmission from the completion semantics. That's why we introduce these non-blocking operations, where you can have MPI ISEN and iReceive doing the message passing, and you can we introduce an MPI wait call for you to decide, oh, here is, I want to wait for the completion of this operation. So between your ISEND iReceive and the MPI wait, you can do all different things, just don't change the buffer. You can do all different things, all your computation, and then maybe you want to do more computation while you're waiting for the transmission. So how it works here is if you look at the function signature for individual non-blocking operation, we have a object, we have an argument called request. So in order to track the ongoing non-blocking operation, you need a handle sort of, which is what the request represents here. Basically, you do send and receive on their request, and you can check the corresponding request to figure out whether it's done or not. And if you can even go more aggressive, because the MPI wait is still a blocking call. We also provide a MPI task, which does the same thing to check if a request or a communication is completed. But instead of blocking on that call, it will return you whether it's completed or not. So you can even write a loop to continuously check, whether the communication is done or it's not done. I'll do something else until where the point the communication is finished. So as I mentioned, with these semantics, you can replace every place you have a blocking send and receive, you can use non-blocking ISEND iReceive plus wait. So if we compare how the communication works, you see the difference is here. At T2 time, I call MPI ISEND, and this call will return pretty fast at T3 time. By this time of point, the transmission is not happened yet. Not until T5 time, the buffer can be reused. And later on, when at T6 time you call MPI wait, and the wait will return pretty soon because the completion is already happens at here. And it's similar on the receiver side. When you call MPI iReceive, it returns pretty fast. But you'll have to wait until the actual transfer happens, and then at TA time, your MPI wait would complete. So the good thing is, each of individual calls takes only a very, very little amount of time. They will finish pretty fast. And in between all this time, your application can do something useful, some computation, or even send more messages. And if you actually send more message, if you have more than one message on the fly, we also provide a convenience call where you can wait to the completion of all of them, or some of them, or maybe any of them. And each of these wait calls have a test version that is non-blocking that you can use in the loop. So since we are changing the semantic of the completion in the communication, so the one thing we have to be very careful is how the buffer can be reused. In the blocking version, if the function returns, you can reuse your buffer. If you look at the left example here, you change the content of buffer after you're doing a send. It won't affect the message that is being sent. But in the non-blocking case, if you change the content of buffer between the ISEND and MPI wait, you may end up sending 3 or 4 or some other garbage data. There's no guarantee that there's no guaranteed semantics. So you have to really be careful and track what kind of buffer is being used. And a good way to do that is maybe you can associate you can have a list of buffer that is being used and with their associated requests, and you can check and work on it. So with MPI ISEND, think about the previous example where 2 processes trying to send to each other at the same time. we said it may deadlock because both of them are trying to send and they're blocking the send. So what we can do is, how about we change the MPI send to MPI ISend. So for each of them, they won't be blocking at the send stage. And you can have all the message being issued out into the network and wait for the completion of them. So here, if you look at this example, there's 100 message going on, and for the receiver side, they can choose to still use the blocking call to receive these message one by one. So this basically gives you a benefit of overlapping of the computation and element. If we look at how the things work, this is how the block communication working. You have P0 sending and then P1 receive. That's one pair of transmission, and then it's almost happens in kind of a lockstep. But on the other hand, if we have non-blocking, because at the beginning we can try to push as many as ISend as we can, and the receiver side P1 may decide, oh, I just want to accept one at a time, and it can still going on, and P0 can be finished sending and do something else, while P1 slowly receive and process each of these message. So that is what we mean by yes, question? There's yeah, someone bring the mic.
So in this line, there's no tag, no?
There is tag. The tag is 0 here.
Oh, okay. So it's the same tag. So are you sure that they are not receiving in the wrong order?
The order is guaranteed by the MPI library. So you send them, they'll be received in the same order as you send them. Yeah. Well, the thing is, by default, all the messages are ordered in the order you're sending them. Although your application may not require that, but that's what MPI provides today. So it's a more comprehensive, it's a stronger restriction on it. So if you really want in case you don't need it, it doesn't hurt. Or should I say?
We have a question. We have a couple of questions from NERSC. Yes. One is, so you already answered the question about whether ISENs are guaranteed to send and be received in order. A follow-on question is there a limit to how many ISENs you can send before posting or receive?
Well, as I mentioned, each ISEN you need one request to represent that these ongoing operations. So potentially, if you because request is a resource that we allocate from the library, so potentially you can run to a point that you're running out of requests. But that is more depending on the actual MPI library, the actual library implementation. So I wouldn't put a fixed number, but I know some of the implementation has a fewer available requests they can use.
Thanks.
Okay, no more question? Okay, so let's see how we can actually benefit from using non-blocking communication. So here is the example where we're going to talk about a regular mesh algorithm. Basically, is you organize your data in a grid and you do some computation on it. It's very popular among scientific application where you have to calculate the dot in the space. For example, if you have a heat transfer application, you wanna know how the heat is transmitted. Then for each of the simulation point, you need to calculate the temperature from your neighborhood, right? So in this tutorial, we're going to use a 2D regular mesh algorithm with a 5D stencil. So here's what we're talking about. Here's what we mean of what we focus on in this example. Assuming we have a large 2D space where each of these mesh points represents the value of individual points. So what the computation does is it will take the value of 4 neighbor points and calculate and update the results of these individual points. So this kind of computation we call it 5D stencil, the 5-point stencil, which involves 4 input and which involve these cross structure. So when we trying to parallelize these problem onto a large system, assuming maybe your data set, your problem set is too large to fit in one machine, what we usually do is we do a domain decomposition, basically cutting the entire problem space into small subspaces and organize into this kind of 3x3 grid, for example. And in this case, we can distribute each of these subdomains to a different process. And for these individual process, they can do some computation based on their local data, and they can fetch. They will need a little bit extra data from this neighbor to perform the computation on the edge, which we'll see here. So what each process has is a 2D array in their memory for their data. And for some of the computation like this one here, you see all its 4 neighbors resides in the local memory. So the computation is easily to be done. But for the point on the edge, you see you only have 3 neighbors on the local memory, but there's one, which is this data, resides on its neighbor process's memory. So that's when the communication has to happen in order to get those data and for the computation. So what we do is we kind of added a patch around the original local data. Basically, is the yellow boundary here. Usually, these spaces are usually called the ghost cells. Basically, it's representing the data that your neighbor is holding, and in the communication, basically, you can exchange the entire edge with your neighbor, which will be something like this. The good thing is with this information, we can separate the computation and communication. So we can do the exchange with the neighbor, and then with all this data available locally, and your computation could happen. And the data exchange is what we refer to a halo exchange. Basically, for each process, it need to send its edge data to their 4 neighbors, and receive the corresponding data from their neighbors and put them into the ghost region. And then we do computation. And after the computation, in the next iteration, we'll do the same exchange again, and until the end of your simulation. So that's how this example works. But there's a few things we need to be careful. One is because each process is talking to all 4 neighbors. In this case, it actually creates a unexpected hotspot. So what do I mean by unexpected hotspots? So if you look at these 3x4 match, we have 12 processes trying to talk to each other. As you can see, some of the process, like the rank 9 here, it doesn't have a neighbor on the north and the east and the west direction. So when it's doing the communication, it's always doing two exchange with the only two neighbor it has. But if you look at the other process in the middle of the grid, you will see it has to do more communication, like 7, 4 here. Each of them have to exchange data with 4 neighbors, and 1 here is exchanging with 3 neighbors. So that introduced a problem because even assuming all the communication takes same time, you can imagine that 4 and 7 will be the last one to finish all the communication, which would. And if we write we can write a simple exchange with MPI send and receive like this. So for each of the neighbors, it do a send, and then for each of the neighbor, it trying to do a receive. But this code, as I mentioned, just like the previous example, it could deadlock in some case. So so what we can do is, how about we trying to do receive, because the previous code deadlock because no one is doing receive, everyone is doing send. How about we just say do receive with a non-blocking call? Here's an example. Basically, we're posting all the receives, and after receive has been posted, then each process is doing the send. And then after sending to all its neighbors, it will wait for all the communication to be finished. So if you look at the code example here, we have a match non-blocking up to 1.c in the code repo. I don't think I'm going to show the code here, but basically this is how it works, but it doesn't perform very well in the practice. So let's look at the figure here. If you look at, let's assume we're talking to the neighbor in this order. We talk to the south neighbor first, then east and north and west lastly. And what will happen on these 12 processes, for some processes, after posting all the MPI I receive, each of process will start to send message. So these process will send to their east neighbor because they don't have a south neighbor, and while the other process is sent to the south neighbor. So because all your send call is in a sequential order in this case because it's blocking. So after several steps, and you will see some of the process which has less neighbor to talk to already finished, while others still in the second and the third step. And if we run this program even further, you will see most of them are finished, and the middle process are still waiting, and this is the last one. So if you look at how the communication happens, you will see the blue bar here is the time that's spending on sending the message, and the red bar here is the time spent on waiting to receive to finish. You see that some of the process spend almost half of its time in waiting. That is because the process that's supposed to send its data has to do other sendings before talking to this process. So that's why you see this unbalanced performance across the process. So how we fix that? Since we already make the receive part non-blocking, how about we make the send part non-blocking? In that sense, will be more efficiently, because the send call will finish. The send call will return pretty soon. Then means you can send to all your neighbors almost in the same time, and then you wait for completion. And if you look at the situation here, you see all the sending, which you can see from as the white line here, happens almost at the same time, and there's no process. So most of the process is doing the waiting because now it's now it's waiting for the completion, but you see there is no delay due to a late issue of a message. So that's why this case you'll have much better performance than I receive combined with a blocking send. So so basically that's what we have for non-blocking communication. To summarize it, the core idea of non-blocking communication is that we trying to separate the data transfer and the synchronization, or completion, if you would. So in many cases, this would give you the flexibility to trying to do more send altogether, or trying to overlap these communication with something else, some of your communication. And you can use MPI weights to still provide these blocking-based completion semantics, or you can try MPI test. For the last thing, there's many tools that you can use, like the one I just showed. Basically, gave you an idea how the communication is happening and where the time is spent, and where are the weights. And it's always useful to check your program with the tool and figuring out where are your hotspots, and potentially choose a more appropriate MPI calls for that purpose. And there, as you may or may not notice, there's also a tutorial tomorrow focusing on scaling and profiling tools, which could provide more information about this. So,
I have a question.
Yes.
Is it always better to use non-blocking? Is it always the case? Is it always better to use non-blocking?
Well, let's say this. Functionally, using blocking and non-blocking, you get the same functionality, but the difference is with non-blocking, you have more flexibility about when it should block. So I would say if you have a blocking based implementation and it works pretty well, and maybe for your application or for your problem, that's probably enough. But if you like I said, you can use these tools to see how the communication works, especially when you're running on a large scale system where you potentially have each of process may need to send a huge amount of message. Then you may start to see there's delay due to this non-blocking, this blocking semantics, and you may start to think about maybe I should use non-blocking for better efficiency. But the functionality is the same. One more thing I would add is I just talked the collective communication before. For all the collective communications, there's also a non-blocking version for them. But I think due to the tight schedule, we probably don't have time to cover them. Okay, any more questions? Okay, so yes, let's look at some code example. So if you look at the code repo, you see there's a stencil MPI non-blocking.c file, which provides the fully non-blocking implementation with using ISEN and I receive. And if I switch to here. Now it's in the stencil examples, and if you stencil MPI non-blocking. So here's the main function. Let's fast forward to the init. So there's some basic setup, and this is basically define a 2D grid and some shorthand for how to calculate the neighbors of each process. We have north, south, and west and east. And here's how the data is being decomposed into these subdomains. And we have some initialization and buffer allocation. Now here's the actual work is going on. So we have two array here. One is called AO, and one is called A new. So if you look at, we have I send and I receive doing the communication. So it's going north, south, east, west, and the receiver side are in the same order. And you have an MPI wait all after it. So if you have, let's say, if you have more directions, let's say if you're 3D degree, you can write into a loop or something else, but could be more easier to implement. But one thing I would have to mention here is this pack data function. So and it has a pair called unpack data. So what happens is our data, the actual data for computation is in this AO array. But if you look at the communication actually have individual buffers for send and receive. Because for the receive side, it's kind of easy because this is the ghost region. But the sender side is essentially, this is the same data in the AO. But the question, the pack data here is simply moving the data or copying the data from the AO for each edge and put them into these individual send buffers. And then the receiver buffer the data in the receiver buffer will be copied back to the AO using this unpack data function. So if we go to the start, you will see the pack data. See, for pack and unpack, essentially this is just a for loop and copying the data for all the edges. So in this version of non-blocking stencil code, this is essential because some of the data is not contiguous in your memory. Although it's a 2D array, but saving to a 1D format, some of the edge is not contiguous. So, but on the other hand, MPI only handles communication with contiguous data. So that's why you have to have these pack and unpack and some extra data copy. And if we can try to build this. Oh, there's. Okay, yeah, I will just make all of them. Oh, there's OpenMP stuff. Yeah, we can, but I think our. Yeah, okay. And so MPI not blocking. Okay. All right. So let's say run is how many CPUs I have. All right. Oh yeah. Yeah, but okay. So there's example inputs. Let's look at them. Yeah. We'll just run this one. Okay. So this is basically it will run, but unfortunately it doesn't give you this fancy graph about how the communication happens. But that's basically it's kind of similar to the previous picture I showed. Okay, so is there any question regarding the non-blocking call here? Okay, I see.
I have a question, but it's a little bit different. So, for example, if you take the leftmost process and the rightmost process, right? So if you make calculations on the edges in a closed system, maybe these processes might have to exchange the data. So if you map these processes right on a cluster, like in a very big system, far away, like from each other, the latency is going to be like really big. So how do you actually manage this kind of situation?
You mean for example, for the leftmost the leftmost process talk to the rightmost process?
Yeah.
Well, actually that's application dependent. So in our stencil example, all the processes talk to the neighbors, and the leftmost process and the rightmost process, they are not neighbors. But you can imagine if these 2D spaces actually wrap around and connected on this side, then yes, they have to talk to each other. But whether it have a higher latency, that's depending on the network topology of your system. And on the MPI side, all you need to know is what is the rank of my neighbor. And let's say the left edge and the right edge, let's glue them together. As a developer, you have to figure out a way to say, given the rank of this process, how do I calculate the rank of my neighbors? And with that, you can do the communication in the same fashion. And if it doesn't map very well to your network topology, yes, you may have a higher latency on that scenario. But that's not the focus of non-blocking communication here. You can potentially do topology-aware communication, or you create topology-aware communicators for that purpose. But I think that's beyond the non-blocking part. Does that answer your question?
Yeah, thanks.
Okay. Okay, so any more questions? No? Okay. Okay, so since we still have some time, let's try to cover the MPI data type parts. So as we talked about, there's in the previous example, this halo exchange, you do data exchange with your neighbors. And depending on the architecture and the different system, these 2D grid may not these data for the row and column for these edges may not be contiguous in memory. That's why we have introduced these packed data and unpacked data to do the job. But the downside is there's in order to do that, we have a lot of memory copy, and we have to allocate extra buffers for that. That's why, in order to help the scenario where the data you're transmitting is not contiguous in the memory, MPI provides a facility called data types to help you serialize and deserialize your data layout into a sequential message string. So basically, what we have is we have some basic type, which we'll see later, and we have some declarative constructs that you can construct virtually any data layouts you may have in your local process. The goal is basically you're telling the MPI library to say what my data layout is. Is it contiguous? Is it strided? Or there's some block here, some block there? It doesn't matter. You can tell these informations to the MPI library through this data type facility. And what MPI able to do is with this information, it will get the data and put them into a contiguous way into transmission. So you don't have to worry about that. And it also further cleans up the structure of your program. although it's there's many constructs, we'll see there's some information you need to know in order to pick a good choice for your need. So there's some basic data types like MPI int and MPI float. So these data types are mapped to the plain old data types for your language, whether it's C, C++, or Fortran. And most of the time you'll be using these. If you like, you can send 10 bytes data using 10 of MPI bytes or MPI ints. You can send a contiguous serial of this data. But for more complex data layout, we're provided these constructors, like you can create vectors, index structures, or struct. And you can even combine these derived data types. That's what we call these constructs together and in a recursive fashion. Then you can create all different complex types. So which is example here is, so if you don't look at the construct down there, you're seeing we have some green data we need to transmit and have some blue data. The green part seems easy because there are kind of 3 small blocks. We can probably do a 3 send of each of them. But the blue part is kind of hard. But if we think about derived data type, we can actually create a struct type which consists of what we call a vector and the index section. And for the vectors, it has 3 contiguous sections. And so this is just a quick example of what you can do with recursively creating a derived data type. So the basic data type construct where MPI provide is called type contiguous. This essentially just taking a base type, which is the old type of variable here, and the number of contiguous element in that old type, and creates a new type. So, for example, here is a contig type of 3 struct, or a contig type of 3 base element. This could be MPI int or MPI float. But this is just a basic one. You probably don't need this in the reality, because you can always replace these with the old type and the send count in your communication function. But it's good to have it. So the second one is called vector type. So similar to the previous one, you need to provide a old type as the base building block. But what a vector allows you is that you can create a strided data layout that some of these you can have a small group of data and skip some. So in this case, you have a stride of 3, and notice that in this case, the stride is actually counting in the size of the element. So a more complex case is here. You have a struct type, and they are grouped into sub blocks where you can specify with the block length, and then you can add it up the stride here and create this vector form. So if we given that information, let's rethink about how the Halo exchange can be implemented. Now remember, we have these edge data we need to send. So assuming you're running on x86, most of the time your data in the row should be contiguous, while your data in each column are non-contiguous, but with a fixed amount of spacing of your length of row, which is bx plus 2 here. So essentially, for each row is a contiguous type, where for each column is a vector with stride equals bx plus 2. And the base type, of course, is the type for each element. In this case, will be MPI double. So instead of with the data type, what we can do is we create this contiguous and vector data type. and use it for data exchange. But beyond the contiguous and vector data type, there's also others. For example, the H vector, which is called heterogeneous vector. Essentially, the difference is with the regular vector is that we count bytes when we set the stride instead of counting the number of elements we're skipping. But other than that, it's essentially the same kind of data layouts that the vector type provides. So the next thing is we have this indexed block. So what index block does is, first, it allows you to specify the data aggregated in small blocks, seen like here. But unlike the vector type, where requiring all the blocks are spread across evenly, you can have different displacement for each of these individual blocks. So essentially, when you create a type, you need to pass an array of this displacement calculated by the size of the number of elements. And then you can create this index block, and the library will be able to know where to fetch each part of data for contiguous transmission. And more relaxed version is called MPI index, which not only you can have arbitrary displacement, now you can even have arbitrary block size. So you can have for example, here, some of the blocks are only one element, and while others are two. You can have even larger that. So instead of have one array of displacement, now you also need to pass an array of block lengths. And at the end of this, there's struct type. Essentially, this is the most general constructor you can use. Basically, allow you to use different block lengths, different placement, and even different types. So, for example, here we can combine maybe an MPI int with an MPI double, and the double could be run into a small block with at a length of 2. And maybe you have a longer data layout where these objects are spread all over the place. But since you have all this flexibility and all this information has to processed by the library, essentially you have to pay a much higher overhead related to these kind of data type. So the last one I would like to talk is the subarray. So subarray is kind of more advanced version of vectors. Basically, is if you have a 2D grid of data and you want to split a subblock, a 2D subblock from it, then you can use this subarray type. Although we didn't show how to use this, but you can imagine this if you, instead of a 2D stencil, 2D mesh exchange, you can have a 3D. So you have, for some of the neighbor, you have to exchange your edge, while some other neighbor, you need to exchange the entire surface. In that case, you can create a subarray type for that surface, which is easier than figuring out the block size and the individual and the stride for that surface. And so in order to figure out how to calculate the displacement and how to create these data type, you have to have a way to well, usually you can just put the base address of your array and the displacement of the element relatively to that base address. But the problem is there's no portability because different language may provide a different layout and the displacement could be calculated differently. So in order to provide that kind of portability on top of these different language and different platform, what MPI provides is two convenience thing. One is an MPI bottom macro. So this is basically give you the absolute zero base address for your data layout. That this is portable, and MPI will translate it to a platform specific one. And we also have a MPI get address where you can put your language specific offset into this function and give you a portable one. So with that, it will be much easier for you to create some complex type like struct or index type where displacement is required. So with all these types, it's the overall workflow of using derived data type is kind of simple. So all you need to do is you have to decide what is the base type, and you figure out what kind of construct you want to use, and then you create it, and then you have to do an MPI type commit to tell the library, oh, this is a new type, and I'm going to use it. And after using it, you need to free it because it's a dynamic located resource. And you also have the ability to duplicate a type. This is very useful for if you're developing a library where user pass you a type, and as a library you want to use this type, but you worry the user might be freeing it before you finish using it. That's why you can do a MPI type dupe and create a local copy of it. And there's if you look at the MPI standard, you will see pack on pack, and these functions are usually mainly for legacy libraries because they are old. Usually we don't suggest a developer to use them directly because the library should be doing that. And for library developers, we also have these get envelope and get contents function. What these two functions does is, if I'm given an MPI type, use these two functions, I can figure out what is the data layout in this type. Whether it's a struct or struct of indexed or something else. We can have all this information, and if you some external library like MPI types actually rely on this function to figure out how the derived data type is created. So with all these capability of derived data type, there's the most important question for the developer to ask and figuring out is what data type you want to use, or let's say you should use. I think the guideline is you have to remember that the more general a data type is, there's more overhead associated with it. For example, if you look at the predefined, that's very simple. It's just a macro. But if you go to the other end, doing something like struct, and you can imagine with all the flexibility in the block size, in the type, in the displacement, the MPI library has to do all sorts of calculation in the background in order to make it work. So the general idea is, if you don't need that kind of flexibility, you should always go conservative. Always choose the type that is just enough for your data layout, for your use case. So in that sense, in that case, you don't unintentionally pay a lot of overhead due to these derived data type. And with that, before I show the code example of the derived data type version, is there any question on the slides I just covered? Yes. Can someone pass the mic?
So I'm not sure here I understand. So do you suggest using derived data types, or do you suggest the user should do the packing unpacking? Or I mean, that's the whole point. No, what?
Yes. Well, there's let's say the user or the developer has two choices. One is whether to use derived data type or not. For that one, I would suggest you use derived data type, because first thing is it adds to the clarity of the code, because you don't have to manage all the extra send and receive buffers and pack on pack operations. So the second thing is still related to performance, because if you're doing pack on pack manually, there's extra data copy. But on the other hand, MPI could optimize how these if you're given these data layout through derived data type, the MPI library will be able to figure out what is the best way to access these data and put them together in one message.
But that can the user do that? I mean, what is MPI doing more than, or the MPI implementation doing more than the user can do? I'm still lost. Factorization.
So the MPI implementation can lay out the data in a way I can exploit vector units of the CPU. It's hard for any average user to do that, but we can optimize this. If you can do it yourself, please do it. But
I don't know how to do it. I mean, I don't know how to use derived type either. So,
I mean, yeah.
So it depends on the network. Some networks for some data types allow hardware optimization, like the InfiniBand, new InfiniBand networks. If you give a vector data type, they can send it in hardware. You don't need to do packing at all. You can do zero copy. Okay. If you do very complex data types like struct or something, the hardware can't do anything superior. The network hardware can't do any magic, so you'll have to do packing anyway. So the MPI implementation can portably figure out this hardware does this optimization, so I'll use that. In this case, I cannot use the optimization, so I'll do what the user would do, or do pipelining. I can do things of that sort. So you should always use derived data types and let MPI figure out what's the best thing to use internally for the given network, CPU, whatnot.
Question from the University of Chicago. So once derived data type is defined, you use it just as native MPI data type, right?
Yes, just like the predefined MPI data types. So for example, let's say we derive the data type MPI vector. So in the place where you do MPI send one MPI int, you can do MPI send one MPI vector, where the vector could be like 1,000 element long, something like that. Okay. So any more questions? Okay. So so then let's look at how we can use the derived data type to further improve the stencil example. Stencil MPI DDT. Yeah. Okay, so remember where we have all the communications here. We used to have a bunch of for all those MPI send and MPI receive. In the old version, we have these south buffer, north buffer, these separated extra buffer. But here, if you look at here, all we need to do is pass the address of these the base address of each edge in here. And if you look at the other part where we used to put MPI double, here we use north-south type. And these are the derived data type. And if we go up a little bit, you will see here, for example, the north and south type is created here. Basically, well, this is contiguous, so it's kind of obvious. And after you create it, you have to commit it before using. And the east-west type here is what I mentioned is the vector, where you have a block size of 1, and you have a stride of bx plus 2, which is the size of each row. And then with this east-west type, if you look at the east-west exchange here, these two lines here, right? You see, you only need to give the base address of these edge instead of copying the data. So that's basically with these. That's how the derived data type helps to evolve this code. And also, remember, at the end of the program, you remember to free them, and that's all derivative, how derived the data type works in this example here. And basically, this would covers all the advanced part, slightly advanced part of MPI. I think we'll jump this section conclusion though. And next, we'll be talking about a very advanced topics on MPH right now. And please welcome my boss, Dr. Pavan Balaji, and take the stand.
Right.
Yeah, let me open the slides. Yeah. Oh, it's not open. This is the yeah. This is the lens. Okay, there you go.
Thank you.
No problem.
All right. All right. Oh, let me get my Fitbit. Don't want to lose my steps. Yeah. All right. So we're going to shift gears a little bit over here. So far you've been going through the basic stuff in MPI. We're going to change a little bit over here. The rest of this day we're going to talk about more advanced MPI stuff. It's not too far advanced MPI. It's a medium to advanced MPI. Oh, I need to stand. People need to see me, really? They don't need to see me. It's okay. I like standing. I don't like standing in front of the laptop. Okay. All right. So a little bit advanced. It's not too far advanced because it's a full day tutorial. You can't really explain MPI in full. All right. I guess they need to see me. Hi. Okay. So I think we already talked about the speakers. Is this the same tutorial? All right. Sorry, I'm just looking at the slides for the first time, just like you guys are. So I will be covering a few topics in advanced MPI over here. We have 4 topics over here. We'll not be covering all of them. We have slides for all of them, so you can go back and look at those later at home. We'll be covering 2 topics. The first one is one-sided communication, or remote memory access, as it's called. And the second one is hybrid programming. How does MPI work with threads or shared memory accelerators, things of that sort. We have slides for non-blocking collective communication, topology-aware communication. We also have some slides for MPI 4. That's what's coming later, what's coming next year or the year after. Okay, those things will, again, if there's time, we can cover them, but those are essentially, the slides are there for you to go and refer back to them later at some point. All right, that's one thing. The second thing, as has been throughout this tutorial, the point over here is to teach you the semantics, okay, the concepts. The point is not to teach you the syntax. Okay, you can Google for the syntax, all right? And Google will probably give you a better answer than we can. Our job is to just teach you the concepts so you understand that these things exist, and then you can go back and study a little bit more to see if it is useful for your application. They're really trying to see me. All right, I'm going to stand here, sorry. Okay. All right, so anyway, so just like Ken mentioned at the start, I'll try to cover the most important concepts slowly, but if I'm too fast or too slow, feel free to let me know, shout out. If you can't understand something, we can repeat that part. Going through all the slides is not important. Understanding the concepts is important. And if you can't understand my accent, let me know. I can't change it, but let me know nevertheless. All right. Anyway, so okay, one-sided communication. I'm going to skip the slide. Why is all this there? Is it the right tutorial? There you go. All right. Thank you. So one-sided communication. So what's one-sided communication? So in the morning, or a few hours earlier, we learned two-sided communication, right? MPI send receive. So MPI send receive is like email exchange. There is a, let's say there's a process sending data, there's a process receiving data, okay? So just like email, say you have this document that you want to send. When you do MPI send, you are sending a copy of the document. You're not sending the actual document itself, you're sending a copy of the document. So when the receiver receives this document, now there are two copies, one at the sender side, one at the receiver side. Okay, that's MPI send receive, that's like email exchange. One-sided communication is like a whiteboard. All right, you have a whiteboard and different processes can read, write, or update on this whiteboard. Everyone is seeing the same whiteboard, everyone reads, writes, or updates the same whiteboard. Okay, all right. Okay, now let's go through this picture, this animation that kind of explains a little bit, a cartoon to explain a little bit of how one-sided communication works. All right, so we have, when let's say you run an MPI process, and you did MPI exec -n4 foo, right? Some application with 4 processes. And you end up with these 4 processes. So, oops, sorry, you can't see the cursor, so I'm not going to use 4 processes over here. And by default, when these processes start, all of the memory of these processes is private. Okay, each process can just see its part of the memory. Now, at some point in the program, the process can declare a part of its memory as remotely accessible. Okay, and once these processes do that, this collection of remotely accessible memory together becomes what is called as the global address space. Okay, this is your whiteboard, or more precisely, this is a set of 4 whiteboards. And all processes can read, write, or update these set of 4 whiteboards. All right, make sense? All right, so in this particular example, we have the first process reading, writing, or updating the other processes remotely accessible data. The same thing, other processes can do that too. The second process can do the same thing, third process can do the same thing, and so on. Okay, this example just shows the first process doing that. Okay, as one might expect, a process can read, write, update its local private memory. Okay, it's just private memory, it can access it, of course. It can access its remotely accessible memory, but it can also access other processes' remotely accessible memory. It cannot access other processes' private memory, but it can access other processes' remotely accessible memory. Okay, just the yellow parts over there. All right, and feel free to ask questions at any time. Okay, don't wait till the end or something. Just shout out or raise your hand or whatever it is. Okay, so some quick cartoons of how this works. So two-sided communication. So if you have two-sided communication, I have a sender and a receiver. The sender tells me where the data has to go from. The receiver tells me where the data has to go to. All right. So let's say I have a send-receive communication. In this, the receiver first posts a MPI receive or MPI receive. Now this receive or MPI receive contains information about where the data needs to go to. Okay, on the right, the memory segments on the right side, that's where the data needs to go to. The sender then does the MPI send or I send to tell me where the data needs to go from. Okay, that will be the left memory segments over here. Then the MPI implementation would see this MPI send or I send operation. It will understand where the data needs to come from. It will take the data, it will copy the data from the user buffer and send it out to the target destination buffer network adapter, destination MPI implementation. On the destination side, the MPI implementation now sees the posted receive or I receive buffer or I receive call and says, okay, now I know where the data needs to go to, and uses this information to go and place the data at the right location. Okay, so in some sense, there is this forced handshake. The sender is telling where the data is coming from, the receiver is telling where the data has to go to. So without knowing both pieces of information, I cannot do the actual data transfer. Okay, internally MPI can optimize a few things, but conceptually you need both pieces of information. Right? Without those 2 pieces of information, you cannot do anything. You cannot do the actual data transfer. That's send receive. Now, one-sided communication, it's a little different. The receive side is not telling where the data is to go to. The sender side
on the other hand, gives two pieces of information. First, it says, here is where the data needs to come from, right? Just like send receive. But it also says where the data needs to go to. Okay, selling both the sender side information and the receiver side information. So in some sense, you have an operation which says, here, do this one-sided communication with this buffer, and then the MPI implementation uses the information to see where the data is coming from, take the data, and directly go and put it on the target memory region. Okay, so all of the information is provided by the quote-unquote the sender side. All right. Okay, so before I go forward, I want to clarify some terminology over here. So in MPI send receive, the terminology we use is there's an MPI sender and there is an MPI receiver. Okay, sender and receiver. For MPI one-sided communication, in this sort of operation over here, you can say, I guess you can call the left side as a sender and the right side as a receiver. But in reality, this is not the terminology we use. For example, this is the put call. Okay, we are putting data. If I'm getting data from the target side, it becomes very confusing. Who's the sender, who's the receiver? Okay, is the left side the sender, is the right side the sender? It's confusing. So the terminology we use is the origin and the target. Okay, actually I'm going to turn this a little bit and stand here. All right, excellent. Okay, the origin and the target. Okay, the origin process is the process that is issuing the operation. So the left side over here, that's the process that's issuing the operation. That's the origin process. The target process is the process that is hosting the memory, the container that's hosting the memory. So the right side process would be the target process. So I can put to the target, I can get from the target, I can update memory on the target. Okay, the target is just the container that's hosting the memory. Okay, remember that the origin and target can be the same process. So I can target myself, I can target my remotely accessible memory. All right, okay. Just a little bit of description of how one-sided differs from two-sided. In two-sided, since the sender is conceptually, the sender is giving some piece of information, the receiver is giving some piece of information, these two need to handshake before I can move the data, because each of them only has half the information. I need both pieces of information to move the data. Okay, so there has to be some synchronization, some handshake between the two. You can defer the synchronization using I send, I receive, if you like, but eventually, at some point, they need to synchronize. With one-sided communication, since the origin is giving all of the information, in theory, I don't need anything from the target side. I can directly go and access the target side's memory. Okay. In practice, I might have to do some emulation if the network hardware is not strong enough, but in theory, I don't need any additional information. Okay. That's just conceptually how MPI one-sided or RMA works. Okay. All right. So really what we want to learn is how do we use MPI one-sided communication? How do you use MPI RMA, right? There are 4 things we need to know to use MPI RMA. The first thing is, how do I create remotely accessible memory? Okay. As I said, when you start the program, everything is private, right? No one else can see the data. It's all private to your process. You need to declare, or you need to make some part of your memory as remotely accessible. How do I do that? That's number 1. The number 2 is, after I have declared a part of my memory as remotely accessible, how do I access it? How do I get update data into that? That's the second part. The third part is data synchronization. Okay, I can move data, that's great, but at some point, I need to know what data is where. Okay, I can do a lot of data movement, but eventually, at some point, I need to know. Okay, I might need to know. So that's the data synchronization part that we'll talk about. And the fourth part is what is called as a memory model. The slides are here. I'm going to briefly talk about that, but if you don't understand the memory model part, don't worry about it. It's not that important. Actually, it's very important, but you'll be able to get away without understanding it fully. It's probably beyond an advanced MPI class. It's very complex. But we can talk over beer or something and French fries and discuss that. That's much more productive than me trying to explain that in this class. All right.
I have a question.
Conscience speaking.
So is data race is of concern here?
Yes, absolutely. But that's true for even MPI two-sided communication. Okay. So in MPI, everything is explicit. Okay, which means the first thing when you write an MPI program, the very first thing you should do is go on a whiteboard and jot down your algorithm. Okay, if your algorithm is right, you have to figure out how you deal with data races and things of that sort. If with one-sided communication, yes, it becomes a little easier to shoot yourself, but that's an algorithmic issue. MPI gives you the tools. Your algorithm has to be correct to deal with data races. Okay? Does that answer the question, my conscience? All right, excellent. All right, let's go through the 4 steps. Okay, how do I create remotely accessible memory? When you have a program, right? Okay, it's all again C programming. Sorry, Fortran should have something equivalent, but I'm not a Fortran programmer. I don't even know very well how it's spelled. But let's say you have a C program, you do a malloc. Okay, x equal to malloc some 100 bytes or whatever it is. Okay, by default, that memory is private, as in no one else can see that memory. Only I can see that memory. Okay, it's in my process. Now, at some point, we will make a call. I'll talk about what the call is. I'll make a call that will make that memory as remotely accessible. And this remotely accessible memory together, as I said, it's a global address space. In MPI terminology, that's called a window. Okay, so it's like a window into the other processes' home, right? It's a window. So you can see a little bit into the other process space. So a group of processes, 4 processes here, that together collectively create this window. And once you create that window, this group of processes can access any buffer in that window, right? Okay, so we have 4 calls to deal with window or this remote memory allocation. Okay, win allocate, win create dynamic, and win allocate shared. Of these 4 calls, I'll talk about 3 of them in this part of the tutorial. The 4th part, win allocate shared, fits better with the hybrid section. So Halim will be somewhere. We'll be covering that part in the hybrid section. All right. So I'll briefly talk about what the first 3 are. Then we'll look at examples to understand that a little better. Win allocate says that allocate a buffer and immediately make it remotely accessible. Okay, allocate a buffer and make it remotely accessible immediately. Win create says that I already have a buffer. Okay, someone else allocated a buffer for me. Let's say my math library or someone allocated a buffer for me. And given this buffer, I want to make it remotely accessible. Win create dynamic says that I don't yet have a buffer. At some point in the future, I'll have a buffer, or I'll have many buffers. I don't know how many buffers. In that case, I can create this essentially 0-byte window and attach or detach buffers to this window dynamically. So these are 3 calls we'll look at. Just for understanding purposes, win allocate is the strictest call. Okay, it's the most stringent call, which means it can be used in very specific cases. Okay, you do not already have a buffer. You are creating a buffer and making it remotely accessible at the same time. So that's the strictest call, but it's also the highest performing call. Okay, so if you can use win allocate, you should use win allocate. That'll give you the best performance. Okay, but in some cases you cannot use win allocate because someone else created the buffer for you. So you cannot allocate another buffer. Okay, like a math library created a buffer for you. In that case, you should use win create. Okay, so it gives you more flexibility than win allocate, but you lose some performance in doing that. Right? And finally, in some cases, you don't know how many buffers you need. You don't know, you might need more or less buffer depending on your data. Things might change. So you can't even use win create. So you have to use win create dynamic in that case. So win create dynamic gives you even more flexibility, but you lose even more performance. All right. So there's a performance and productivity trade-off, or use case trade-off, I guess, over here. And this sort of trade-off you'll see in a lot of places. Okay, you'll see that in the threading stuff. You'll see that in various aspects of MPI. These trade-offs always exist. MPI will give you this list of things, and you have to pick which one best matches your algorithm. All right. So let's look at MPI win allocate first. Okay, as a reminder, MPI win allocate is I'm allocating a buffer and immediately making it remotely accessible. Okay. So I go till 4 and take a break. Oh, I see. Excellent. All right. So I allocate a buffer and immediately make it remotely accessible. That's win allocate. All right. So I have a bunch of parameters over here. The first parameter is the size. These are the number of bytes that I want to allocate. to be remotely accessible. That's the first parameter. The second parameter is displacement unit. Now, in MPI, when you create this remotely accessible buffer, you treat it as an array, as a one-dimensional array, single-dimensional array. Now, you can treat it as an array of doubles or integers or just bytes, okay, or floats or whatever you want. Okay, this displacement unit is the size of your array element. So if you want to treat it as an array of doubles, you give size of double as your displacement unit. If you want to just treat it as an array of bytes, you give 1 as your displacement unit. Okay, MPI info. I'll get back to MPI info in a second. MPI com, the communicator, is the group of processes on which you are creating this remotely accessible memory. This can be MPI com world if you want the global address space to cover all processes, or it can be a smaller communicator. I can say that these group of processes create this window, which means only these group of processes can access this remotely accessible buffer. Now, once you give these parameters, you get a base pointer. That's a return from the MPI implementation saying, okay, I have allocated a buffer. Here is your buffer. Okay, it'll give that back to me, and it'll give a handle called as the MPI window, win handle, using which I can do my communication operations. Okay, window is like a communicator. It's a handle that I can use for my communication. All right, make sense? Questions?
Yeah, for displacement unit, why do you use displacement unit instead of MPI data type?
So yes, so that's a good question. And when MPI 3 was being discussed, but that was one of the proposals to say, why can't you just use an MPI data type directly? It became a little complicated with how this is used, because if I want to treat this as a structure, if I want to use my buffer as a structure of like a C struct or something, I should still be able to do put-get operations on individual data type elements, but I'm not allowed to give a full structure as a displacement unit. I can't give something bigger than a basic data type.
Oh, so you can expose not the whole structure, but only part of it?
Let me explain it a different way. MPI allows you to treat this as an array of basic data types. Okay, so if you have something like all doubles, you can use it as an array of doubles. If you have something more complex, like a structure of an integer and a double, MPI doesn't allow you to expose it that way. So you need to expose it as a structure, as an array of bytes. Does that make sense? Yeah, you should use the mic.
Yes. And another question. So this is essentially collective operation. You need to execute it on the whole communication world that you are using.
Not world, but on the communicator, yes. So it is a collective operation on the entire communicator.
So, and instead of the variable itself, you now refer it by window?
So let's get to the actual communication calls before we figure out how to access each of the elements in the window. Okay. So here right now we are just allocating. I'm saying allocate so many bytes for me. All right. To the access, let's hold on for a little bit before we get to the access part.
I have another question. Yeah. So the size, basically all the sizes have to be the same. Each processor. Oh, they can have different local
That's correct. Sizes. They can all have different sizes. In fact, it's a very common practice for one process to allocate a bunch of bytes and all other processes to give 0. Okay, that is totally valid, and it is. I don't like it, but that's a common practice. Some applications do that. Right? Other questions? Remote participants, maybe? All right. So we've covered all the parameters. There's one parameter that we missed. That is the info part, MPI info part. So MPI info is a hinting mechanism in MPI. That's not specific to MPI one-sided communication. There are various parts of MPI. They use info arguments for hinting. Why do we need these hints? All right. So if you use MPI out of the box, okay, just run your application with MPI. MPI has to assume the strictest semantics. It has to assume that you're allowed to do basically anything that the standard says you can do. Okay, and in practice, most users don't need the full feature set of the standard. Okay, most users only use a subset of the capabilities of the standard. So this info hints are essentially hints to say, tell the MPI implementation, I will not use, or I do not need this guarantee that's provided by the MPI standard. My application does not need this guarantee. So a good MPI implementation will take the hint and say, oh, if the user doesn't need this guarantee, I can implement it this other way, which is faster. Okay, so I'll show some examples later in the code. But there are some cases, if the user gives an appropriate hint, I can improve the performance by an order of magnitude. Okay, just because by default, I had to assume that you would do that. If you tell me I will not do that, I can optimize some cases. So I'll give some hints where this performance can be an order of magnitude higher. Okay, that's win allocate. So let's look at a quick example of how to use MPI win allocates. Okay, we have this main function. We learned MPI init and finalize, right? How many of you know MPI init and finalize? One person knows MPI init and finalize? Oh God. All right, wake up guys. All right, so MPI init and finalize, right? So I'm going to assume that you know that even though you're not raising your hand. After initialize MPI, you do this call MPI win allocate. This is a collective call, so all processes are calling it. And each process is giving this 1,000 integers. And my displacement unit is size of int. So I'm treating it as an array of integers. Okay? And MPI info null, I did not give any hints in this particular case, but for a good program, you should try to give hints to help with performance. MPI com world, so I'm using all processes in my world. And once I call this int pointer A is the buffer that got allocated. So MPI allocated A and gave it back to me and gave me this window handle that got allocated. All right. So let's say I'm running it with 4 processes. What's my total global address space size? What's my size? How many bytes did I allocate totally? 1,000 times size of int times number of processes. So if I have 4 processes, I allocated a total of 16,000 bytes. Okay, each process contributed 4,000 bytes, but if I have 4 processes on an aggregate, I allocated 16,000 bytes. All right, make sense? All right, excellent. And after you're done using this window, you free it at the bottom over here, MPI win free. Okay, to free the window, just like all types. Anytime you create an object in MPI, you have to free the object at the end of your program. All right. Now, between this allocate and win free, between these 2 calls, your buffer, this A buffer, is remotely accessible. So all processes in MPI com world can access this buffer, this remotely accessible buffer. Okay, we're not doing any accessing right now, but this is how we allocate it for future access. All right, make sense? Excellent. So let's move to the next call, MPI win create. Now, MPI win allocate was, I wanted to allocate a buffer and immediately make it remotely accessible. Okay. Now, let's say the math library gave me a buffer. So I already have a buffer. Now I need to make it remotely accessible. So I use this call called win create, which is, it's very much like win allocate. The only difference is that the int pointer, the base pointer over here, it's an input parameter, not an output parameter. Okay, no laser pointer from here on. sorry guys. MPI win create is like win allocate, but the base pointer is an input argument, not an output argument. So the user is providing the base pointer. Okay, and everything else apart from that is the same as win allocate. Now let's look at this example over here. Yes.
So is the buffer has to be the same size, like the entire buffer? You're gonna make it remotely accessible?
Right.
I mean, like, can we do just like half of the buffer?
Right. That's the size. The size is the parameter you're saying how much of the buffer is remotely accessible. So you can have a 1,000 integer array. You can make the first 500 integers remotely accessible by saying buffer pointer 500 times size of int. Okay. Yeah. Other questions? All right. So let's look at this example modified, the previous example modified to use MPI win create. Now in this example, I have to do my own memory allocation. Okay, I used MPI alloc mem. You can use malloc if you like, okay, or POSIX memalign or whatever your favorite memory allocation call is. You allocate your memory, and once you allocate the memory, the buffer is private. Okay, so you can access it just like you would access your regular buffer, right? A0 equal 1, A1 equal to 2, whatnot. You'll just access it like your regular buffer. Once you're done accessing it in the private manner, you make it remotely accessible at some point. Okay, and you use this call MPI win create and say, here is my array A, it's 1,000 integers, and make it remotely accessible for all of MPI com world. Okay, it's collective over MPI com world, and all processes at that point after win create, all processes have access to that buffer A. Okay, it's no longer private; it became remotely accessible now. Then you can access that, and at the end you free the window. All right. The difference over here is that since you allocated the buffer, you also have to free the buffer. In win allocate, MPI allocated the window and the buffer at the same time. So when you freed the window, it freed the buffer too. In MPI win create, it's your buffer. You allocated the buffer, so you have to free it yourself as well, right? But that's just a minor thing to remember.
Do you have to use MPI allocate, or can you just use malloc?
You can use malloc. Malloc is just fine, or you can use your favorite memory allocation call. Okay. In MPI 2, there was a requirement that said if you want to use MPI in some way, you have to use MPI alloc mem. But in MPI 3, we got rid of that restriction. So today, you can use malloc or whatever you want. All right. Okay, so that's MPI win create. Now let's look at the next call, which is MPI win create dynamic. MPI win create dynamic is, again, as a reminder, I do not have a buffer yet. I will at some point have one or more buffers. I don't know how many buffers, I don't know how much size, but at some point I'll have some buffers that I need to make remotely accessible. All right. So MPI win create dynamic essentially allows me to collectively create an empty window, 0-byte window. Okay. Once I create the 0-byte window, at a later point, I can locally add buffers to this window. Not collectively, but locally, I can add buffers to this window. So here's an example. So initially I created MPI win create dynamic. Okay, I don't need a buffer. It's an empty window. So I just create MPI win create dynamic at the very start. Then I do my malloc. Oh, here I use malloc. So yeah, you can use either one. I use malloc of some number of integers. And when you malloc, of course, it's private memory. So I would access it just like I would access any other buffer. When I'm done accessing it as a private buffer, at some point I say, okay, now I need to make it remotely accessible. So I go and attach this buffer to my window that I created with win create dynamic. And once I attach my buffer, now it becomes remotely accessible. Okay, other processes can access that buffer. Now, win attach is a local call. It's not a collective call, which means I can attach a buffer without anyone else knowing about it. All right. Similarly, I can detach buffer. I can attach more than one buffer. I can attach like 3 buffers. I can attach buffer 1, buffer 2, buffer 3, detach buffer 2, attach buffer 4. I can do all sorts of stuff. All right. So it's very dynamic in nature. All right. One small thing you should be aware of. Now, I said I can attach buffers locally without coordination with other processes. Okay. So the question is, how will the other processes know? Right. They need to access that buffer remotely. So how will the other processes know? Now that's your algorithmic stuff. Now algorithmically, you need to figure out how to convey this information to the other processes. One simple way is you convey it using MPI send receive. Okay, but potentially a more complex way of doing it is if you're doing something like linked list. Okay, your next pointer will point to the next buffer anyway. Okay, so you could create a buffer, attach it, and in your linked list, the last element can have a next pointer pointing to this new buffer. So if someone is remotely parsing through your linked list, when they see that the next pointer is set, they already know that a buffer has been allocated and attached. Okay, so that's your algorithmic stuff. That's how you design your algorithm. So, but it's local. You need to figure out algorithmically figure out how you'll convey this information to the other processes. All right, make sense?
So the user needs to know the address or the variable name to use it remotely?
Well, not exactly. You don't need to know the variable name. You need to know the address, the virtual address to target.
Address with respect to the window from the MPI bottom?
Good point. So I was trying to hide those details under the rug over here, but that obviously didn't work out very well. So let me answer that question. So MPI win create, win allocate, it is the offset you access it based on an offset from the start of the window, okay, from the start of the window. So array index, let's say. In MPI win create dynamic, you access it from the start of your memory, So basically null, in C, from start of null, you're accessing it. So essentially a virtual address. In Fortran, there is something called MPI bottom. You base the offset based on MPI bottom. But let's just say from the start of your memory, you're accessing it as an array from your start of your memory. Okay, does that make sense?
Kind of.
All right. We can give you more details on Slack if that's useful. But the idea is when you use MPI win create dynamic, you give you a virtual address. You stick in your virtual address over there. Okay, directly the virtual address. The right way to do it is using an MPI call called MPI get address, but I guess that's too much detail. Yeah, there's a way to do that, and we can work out the syntax with you if you like. All right.
In your last slide, can you go to the last slide?
Mm-hmm.
Yeah. So this free A frees the allocated memory. So if I forget to free the window, how does it affect the performance, or what does it mean actually?
To free the window. So once the window is free, none of the memory in that window is accessible remotely. Okay. So the free will essentially make the memory no longer remotely accessible.
I mean when you free the already allocated memory, like free A has already freed the memory, right? So if I forget or I don't write this win free, how it's going to be like? What is the difference?
If you forget win free, you are essentially leaking resources, handles. So at the end of your program, it will automatically get freed. So it's not that bad, but it's a memory resource. So you're wasting memory in your program. Okay, that's for MPI win free. The free of your A is the same thing, right? You allocated a buffer, you malloc the buffer, you need to free the buffer. So these are essentially resource cleanup. If you don't do that, I guess nothing correctness wise, it's okay.
But isn't it freed already? The buffer itself, the memory at free A.
Correct. The buffer is freed, but the window handle. So MPI internally will create some resources to keep track of your accessees. Okay. So MPI has to free that as well. So you need to tell MPI, I no longer need this window. So free all the internal resources that you created. So that's the MPI win free call. So, but this is not just true for Windows. This is true for communicators. This is true for data types. Basically, any object that you create in MPI, you should free it.
Okay, thanks.
Yeah. All right. So far, what did we learn? We learned how to allocate or create a remotely accessible buffer. Okay. That in itself is not very useful, right? I mean, we created a buffer, we got access, we put some data in that, right? Otherwise, it's not, what's the point of creating this remotely accessible buffer? So we have a few calls to do that, create this remotely accessible buffer. There are a lot of calls in the MPI standard. I'll not go through all the calls. Here are some examples of it. MPI put, get, and accumulate, get, accumulate, compare and swap, and fetch and op. Okay. The first two are regular operations. The remaining four are what are called as atomic operations. I'll talk a little bit about those as well. So just to be clear, in the MPI standard, the terminology used is accumulate style operations. We just call it atomic operations over here for simplicity of understanding. Right. So as you might have noticed, I'm speeding up a little bit over here. Hopefully that's all right. But if you don't understand something, stop me, slow me down, and we can go over the details. Okay. I'm just speeding up because I want to go cover as many concepts as I can before I have to hand over to Halam, I guess, next. All right. MPI put. MPI put is a simple the communication data type where you're moving data from the origin buffer to the target window. All right. So we have two sets of calls over here. The green set of parameters over here are the origin side buffer. So I have an origin address from which buffer should I send it from? This many count, this data type. Okay. So count and data type. So those three green parameters essentially tell me the description of the data that I'm communicating, from how much data am I sending. Target rank, as I said, these are whiteboards, right? So when I created 4 processes, there are 4 whiteboards. I need to tell which whiteboard I'm accessing. That's a target rank. And target displacement is the offset inside. When I created a window, I have a start of the window and some number of array elements. So what's my array index? What's my offset into this target window that I'm writing to? What's the location, all right? And target count, target data type, basically the same thing. And the MPI window, the window handle for doing this communication, all right? So why do I need the origin count, origin data type, and target count, target data type? Why do I need both? Any takers? We need to give out gifts, okay? Whenever someone answers a question, we throw out a penguin or whatever, some gifts. We need to get some of those. Soda over there. All right, any takers? Why do we need these two different sets of counts and data types? Feel free to say some answer. I'll tell you you're wrong, but it's okay.
I'll take a guess.
So, sorry, go ahead.
Push my button. The source data and data types might not have to necessarily map to the target. So I could be the target pulling some data and store it where I choose to. I just need to get the right number of bytes or bits.
That's right. That's exactly right. So it might not, it has to be the same number of bytes on both sides, but it doesn't have to be the exact same layout. Okay. So for example, it is totally possible if I have a matrix, let's say, I'm sending the row, which is a contiguous 100 integers. And on the target side, I might put it as a column, which is a vector, a strided vector of 1,000 integers. Now, both sides is 1,000 integers, but the layout is different. So on the origin side, I'll say origin count 1,000 or 100. What number did I say? 100. I didn't sleep much, so I can't remember very well. 100 integers or whatever it is. On the target side, it's one vector of 100 integers. Okay, so that allows me to change the layout of the data that is being transmitted. Okay. Here, this picture over here, I'm sending the origin from my origin private buffer to this target remotely accessible window, right? The green blob thingy, right? So I'm sending from this pink buffer to this green buffer. Starting MPI 3, you're allowed to send even or put from my local green blob. I can also put from my remotely accessible buffer to a remotely accessible buffer. Okay, so I can either send from the origin pink buffer to the target green buffer or the origin green buffer to the target green buffer. I cannot send to the target pink buffer, obviously. That's a private memory. I can't touch that. But I can access the target green buffer from either the pink or the green buffer from the origin side. All right?
Question.
Yeah.
On one hand, you are creating window in a collective operation. So it sounds like we are talking about shared variable. On the other hand, now you are talking about put, get, origin, target. So obviously it is not shared variable. So how to reconcile this?
It's not a shared variable at all. Okay. It's shared variables are more PGAS sort of communication. That's not what this is. This is only allowing a buffer to become remotely accessible. And once the buffer is remotely accessible, you have to explicitly say, go and write to this virtual address. It's nothing, the variable names are not shared, they're not global, there's no global namespace, nothing of that sort. All right? So there's no concept of shared variables over here.
But window declares some variable on simultaneously on all nodes, no?
No. The window handle is also not a shared variable. There is no concept of shared variables in MPI. Okay, so when you get a window handle, the window handle is local only. So the window handle is only valid on your process. Every process gets a window handle pointing to the same global address space, but they're all different window handles. They all just point to the same global address space. All right? Make sense?
But when you create window, do you create some remote access memory on each node participating in the call or only on one node?
Each process is participating in the collective call. So each process is creating a buffer that other processes can access.
Okay, but when you are using put and get, you still specify the rank of the
That's correct.
Target.
That's exactly right. So every process is contributing a buffer region. So you need to tell which process's contribution you want trying to access. That's why you have to give the target rank.
But why do you have to do this creation of window collectively if you are not using it like collectively as a shared operation, shared memory?
It's an access thing. Not all processes have to access it, and also it's useful with respect to the group of processes that need to synchronize and so on. So the window is useful. The group of processes is useful in other ways. If you're not going to do any collective synchronization, you can do MPI convert. That's fine. Right? But that's a little bit more detail. I don't think we should go into that much detail over here just yet. All right. Okay, so I have 30 seconds. So let me see if I can get one more function in before that 30 seconds are up. So we talked about put, right, with the data going from one side to another side. There's also a get operation where it's just the opposite. All the parameters are the same, kind of the same. This should be a const void pointer for the put, and on the get side it's a void pointer, but more or less the same parameters. The only difference is the transfer of data is in the other direction. So I'm getting data from the target remotely accessible buffer to my local either public or private buffer. Okay, that's the only difference between MPI put and get. All right, 0 seconds. So I'm taking a break now. Is that 15-minute break? So we'll come back at 4 o'clock. All right, thanks.
Okay, yeah.
After the break, we'll do questions after the break.
No question.
I need to go and drink some Coke.
Okay.
I don't. I want to be able to see the monitor. All right. Yeah, we got to have that motion sensitive thingy to move around. All right, so let's get started again. So hopefully you got some drinks, some caffeine, whatnot. So any questions before we get started? You know, caffeine trigger neurons and questions pop up. So I'll give you a minute to ask any questions. So there was a question on the remote side before the break.
Yeah, actually, I was just thinking that, for example, in your application where we are exchanging halos, so one way is send and receive, and the other way is like, as you mentioned, that we can just peek in the memory of the other process. So should I do, what way should I follow? Like, do the send and receive or like this window? Peeking.
So actually, the true answer would be neither. There is a thing called MPI neighborhood collectors, which is the best way to do the stencil computations. But we're not going to discuss that in this tutorial. But let me answer the question in a more generic manner. So which one should I use for a given application? Should I use MPI send receive, or should I use MPI one-sided communication or MPI collective communication? That depends on your algorithm. Okay, you should never force fit a model for a given algorithm. So if you're looking at a stencil computation sort of thing, if you are comparing just send receive and put get, in stencil computation you have a strict producer-consumer relationship. So there is a producer, you send the data, there is a consumer of the data. In that sort of model, send receive is just natural to use. If you have a model where you are accessing, you have this address space and different processes want to access this buffer asynchronously, different processes want to access it without having to coordinate with other processes. In those sort of applications, in that sort of algorithm, MPI one-sided would make better sense. I have a few examples that show how MPI one-sided would be more appropriate than two-sided in some cases. But again, don't force fit MPI one-sided if the algorithm naturally is more two-sided oriented. Okay. For the stencil computation itself, two-sided would be better than one-sided, but neighborhood collectives would be even better than two-sided. So that's the right algorithm to use over there. Okay,
thanks.
So once you declare window in a collective call, you are basically declaring that the same variable on different nodes can be accessible remotely.
No, that's not what we are doing with MPI window. It's nothing to do with shared variables. There are no shared variables in MPI. Okay, just basically there's no shared variables. All it's saying is that a process is telling that this virtual address location or this buffer is accessible by other processes. That's all it is saying. Okay, it is a variable name itself. There's no variable name sharing.
Sure, but you are kind of so each rank has like the same pointer and it is shared, but in this global address space it will have different addresses.
I'm not sure.
Well, when you create the window, you expose some variable, and since this is collective fall, the same variable is exposed on each rank, although it might contain different information, right?
Well, you're actually not exposing the variable, you're exposing the address. Okay,
Okay, but you expose an address on all the nodes.
Each process exposes a virtual address. Each process exposes a local virtual address to be accessible by other processes. Okay, so that's a buffer. So every process says that process 0 might say, starting from address 1000 to address 2000 is remotely accessible. Process 2 might say, starting from address 5000 to 6000 is remotely accessible. Process 3 might say, starting from address 10,000 to 15,000 is remotely accessible. Anyone can give any part of their virtual address space to be remotely accessible.
So when you use get address on different ranks for the same window, you would get different addresses?
Right, you can give different addresses. You can give the same address, you can give different addresses. MPI, it's irrelevant for MPI. Okay? All right, let's move forward. So one small thing, big thing that I kind of forgot to mention, put get operations are non-blocking. All right, so when the put operation completes, you have started the data transfer, but you might not have completed it. Okay, which means just like I send, if you go and write to your origin buffer, bad things can happen. You might send out garbage data. Okay, so be careful, it's a non-blocking operation. All right. Let's move on to the next call, which is MPI accumulate. All right, MPI accumulate is like MPI put. All right, so we have the same green parameters, which are for the origin side. We have the same blue parameters for the target side, but we have one extra parameter, which is called the MPI op. Okay, so it's like put, but when it takes the data from the origin side, and instead of directly putting the data, it will do some operation that uses this data from the origin side and the data from the target side that is already present. Okay, for example, a summation. So you can do a accumulate as a summation, which means it will add up my origin process data to the data that is already present on the target side. All right, so it's a summation. So you can do different types of operations. There's a min, max, bitwise OR, logical OR, bitwise and product, whatnot, a lot of operations. There are two special operations. One of them is called MPI replace. Okay, with MPI replace, it will essentially, the MPI accumulate call will essentially replace the target side buffer with the origin side buffer. Okay. I usually hope for a question over here, but I'm going to ask the question myself because I'm in the interest of time over here. So if I'm just replacing the target side buffer with the origin side buffer, why am I not using MPI put? Okay, that sounds very much like MPI put, right? I'm just putting a data. So why am I using MPI accumulate with this op called MPI replace? The reason for that is atomicity. MPI put is not atomic. MPI put and get are not atomic, which means if I have a process, I have a value 0 over there, and origin 1 does a put of a value 1 to that memory location. Origin 2 does a put of a value 2 at that memory location. The result could be any value. It can be 0, 1, 2, 25, it can be anything. Okay, so there's no atomicity, so it can essentially, the data can get corrupted if you're writing to the same memory location. So same target, same memory location. If you're writing to that, data might get corrupted if you do two puts. With MPI accumulate, it's atomic in nature, which means that it is guaranteed that they will not corrupt each other. Depending on what order they came in, it'll either be 1 or 2, but it can't be 25. All right, so it's atomic in that sense. It's very useful for MPI replace itself might not be that useful, but things like MPI summation are very useful because when I'm adding data, I need these additions to be atomic. Okay, I don't want two additions to the same memory locations to corrupt the data. I might do simultaneous additions. So these are all atomic operations that MPI accumulate provides. Okay, one small thing to notice is that the atomicity in these operations is at the granularity of a basic data type element. A basic data type element. So if you have a vector, if you have an array of 1,000 integers, and you're doing replace of 1,000 zeros with 1,000 ones or 1,000 twos, it's atomic per data type. So you might end up with a few ones and a few twos. Okay, but each element will be either a 1 or a 2. It can't be 25, but the vector itself need not be atomically modified. Okay, make sense? Questions?
So you can't guarantee the with using MPI replace as your operation, you can't guarantee which will be the last one to do the atomic put into the window.
You can guarantee it by doing external synchronization, but if you're doing simultaneously, two origins are simultaneously doing an accumulate on a target process, well, they're happening simultaneously. So there's a race of which one will go first.
So then if you're putting multiple elements into an array and you can't predetermine, using the accumulation, you can't predetermine which one will end up on top at the end of all the atomic puts, what's the point of using an MPI replace with accumulate?
It is useful if you want atomicity with other operations. So let's ignore replace for a second. Let's talk about summation. Okay. So suppose you are doing summations at an array, and you're trying to sum up 1,000 arrays from one process and 1,000 integers from one process, 1,000 integers from another process. You don't care in some sense which order these summations happen. You might care for consistency reasons, but let's say you don't care. They're all integers, they're all small integers, whatnot. In that case, you can just use MPI accumulate with sum, and each data type is atomic. That's sufficient for you. If you want to use a stronger level of atomicity, like you want atomicity on the entire vector, for example, then there are other operations in MPI that you can use, for example, locks and so on, that you can implement that. But those are expensive. By default, this operation itself gives you per data type atomicity. So it might be useful in some cases, might not be, but many of the applications that we use, like the quantum chemistry applications, this level of atomicity is sufficient to go with. You should wait for the mic.
So what's the difference between this MPI accumulate and MPI reduce?
MPI reduce is a collective call. MPI accumulate is a point-to-point one-sided call. Okay, I'm just doing accumulate on that target process. I'm not coordinating with all the other processes. Okay. All right. So we'll see an example also for doing this sort of accumulate sort of operation. All right, the other operation is the MPI get accumulate operation. So MPI get accumulate is a combination. It's like MPI accumulate, so it's atomic, but it allows me to get the data before the operation got executed. So if I do a summation with the get accumulate, it will do the summation, but it will get the data before the summation happened. So it will get me the original data and then sum up the data on the target side. Okay, that's how the MPI get accumulate works. Just like MPI replace, there's another op called MPI no op. So MPI accumulate with MPI replace would be an atomic put. MPI get accumulate with the MPI no op would be an atomic get. Okay, you're not actually doing any op, but you're atomically just getting the data from the target side. You can also use MPI replace with MPI get accumulate, which will essentially do a swap. It's a swap operation. If you do MPI replace with get accumulate, it's a swap operation. So you can do lots of intelligent algorithms based on these sort of operations, or swap and adding numbers, whatnot. All right. Questions on accumulate or get accumulate? All right. We have two other operations, compare and swap and fetch and op. Compare and swap is basically what you would expect. You would compare two values, and if they are the same, you'll replace it with a third value. Okay, it's just a regular compare and swap processor, compare and swap sort of atomic, and it works on remote target memory. Fetch and op is very much like get accumulate, but it's a simplified version of get accumulate. So it does an op, but it allows only basic data types and a count of 1. So since it's a simplified version of get accumulate, the assumption is that the MPI implementers can optimize this better than get accumulate. So if you want the full generality, you should use MPI get accumulate. If you want a very special case, you can use MPI fetch and op for better performance. And all of these are atomic operations. Just as a small note, atomic operations are only atomic between each other. Okay, so accumulate, get accumulate, fetch and op, compare and swap, they are all atomic with respect to each other. But they're not atomic with respect to a put or get operation. Okay, put and get are non-atomic. So if you mix a put and an accumulate, you will still get garbage. All right. Just remember that. So atomic operations are only atomic with respect to each other, and they're only atomic for a basic data type. All right. Okay. So we talked about the atomicity of operations, but all these quote-unquote atomic operations also have this capability of or feature of ordering. Right. So now let's say I have multiple operations from the same origin to the same target and to the same memory location on that target. Okay, so I have multiple operations from the same origin to the same target to the same memory location of that target. All right. In that case, if I do multiple put operations to that memory location, of course, they are not atomic, so garbage data will, there'll be garbage data. But let's say if you're doing multiple accumulate operations, same origin, same target, same memory location, multiple accumulate operations, now they're atomic, yes, but they're also ordered. Okay, this means that if I have two operations from the same origin, same target, same memory locations, they will appear in the order in which they have been issued. So if I did an MPI replace, MPI accumulate with replace of 1 and followed by MPI accumulate replace of 2, these are non-blocking operations, but I'm guaranteed that when both operations complete, I will see the value 2 on the target side. Okay, that's the ordering guarantee. And the ordering, again, is only from the same origin, same target, same memory location. All right? Make sense? Questions? Questions remotely? All right, excellent. The ordering thing, it's a nice feature to have. It's useful for applications, but you should remember that ordering is extremely expensive. Okay, for most network hardware, ordering, some of the ordering comes for free, like write after write or read after write. Write after write and read after write are most hardware provides this by default to you. But write after read and read after read ordering is extremely expensive. In fact, no network hardware gives this to you by default. And since no network hardware gives to you by default, since the MPI semantics say you get forced ordering, every time you do operations, you get forced ordering, I have to emulate all my operations in software because I cannot use the network hardware's ordering capabilities. I have to emulate everything in software. All right. Now, we talked about, when we're creating the window, we talked about this hinting mechanism called MPI info. So I can give hints to the MPI implementation saying, here are some of the guarantees that MPI gives that I do not need for my application. Here is one place that you can use those hints. Like, for example, for your application, suppose you never need read after read or write after read guarantees. Suppose you never need that. You can give an info hint to the MPI implementation to say, I don't need all these guarantees that you're providing. I only need write after write and read after write. Okay, suppose you give that hint. Now the MPI implementation can see those hints and say, oh, since you don't need those guarantees, I'm just going to ignore my software emulation and do everything in hardware. So suddenly my performance goes up like tenfold. All right. So these hints are very useful in such cases. So in general, okay, if you don't need some feature in MPI, not just in one-sided communication, in any part of MPI, if you do not need some feature in MPI, give a hint. Give a hint to the MPI implementation saying, I do not need this feature. All right. If the MPI implementation can optimize for that hint, it will optimize it. If it cannot optimize for that hint, well, you didn't lose anything. You just gave the hint and MPI implementation ignored it. Nothing to lose. You're not losing anything. So you might as well give a hint. A future MPI implementation or a different MPI implementation might be able to use that hint and give you better performance on some platforms. All right. So you should always give the hint. If you don't need a feature, tell MPI, okay, that you don't need it. Whether it optimizes right now or not is more or less irrelevant because it's free, right? You're not using it. Why not just tell MPI that you won't use it, all right? Okay, so some pretty pictures of how this ordering works. So if you have multiple puts happening to the same process, same target location on the process, then the concurrent puts are undefined. Okay, so you might get garbage data. Put and get also undefined because they are not atomic operations. But if you have get, accumulate, and accumulate, get accumulate is a read, accumulate is a write. You have write after read ordering guarantee by default, which means MPI implementation has to make sure internally to make sure that it has to make sure that these operations happen in order on the target side. All right. Questions? We should have a quiz at the end of it, right? Every time I ask for questions, if no one asks the questions, I ask everyone a question. And if you don't answer, you're out of the room. Right? Anyway. Okay, so that's just a data communication. So that's the second part. So far, what did we learn so far? We know how to create a remotely accessible buffer. That's the first part we learned. And we know how to get data into this buffer. All right? So far, we don't know how to complete this data transfer. Okay, we can move data, but we don't know when the data transfer has completed. Okay, so that's the third part, which is the data synchronization. So let's talk about the RMA synchronization models. Now, RMA has two broad classes, let's say, of synchronization. One is called the epoch. RMA has a bunch of epochs that you can use. Then there is another part which is just communication completion or synchronization operations. So these are two parts. So first, let's talk about the epochs that are allowed. Now, in MPI, you have 3 or 4 different types of epochs depending on how you view it. The first one is called MPI win-fence, which is a collective synchronization. Second is post-start complete wait, which is a little bit optimized win-fence, let's say. And the third is called win-lock and win-unlock. Okay. There's the fourth one, which is win-lock all and win-unlock all, but it's sometimes combined into this win-lock-unlock model. So that's why it's 3 or 4 depending on how you view it. Apart from these epochs, we also have additional completion functions called flush local, whatnot, which is a different class. I'll talk about those separately. All right, let's talk about these epochs. So I mentioned that all of these RMA, put, get, accumulate, all these operations, they're all non-blocking. All right. So when you issued the operation, you don't know, it might not have completed. It will complete at some point in the future, it will complete. But you need to know when it has completed, when you can use the data and so on. So that's where these epochs come into play. And the data transfer themselves is one-sided, right? If you do a put, it's one-sided. But the synchronization might be one-sided or might not be one-sided. So we'll talk about the different models over here. So the first synchronization model is win-fence. The way it works, it's very simple. It's not very scalable, but it's very simple. Okay. So you have a bunch of processes on the window. You do a win-fence, a collective call. Win-fence, everyone does a win-fence. Then everyone does non-blocking put-get operations. And then everyone does a win-fence. Okay, it's bulk synchronous in nature. So everyone collectively does win-fence, lots of put-gets, and win-fence. It's not exactly, but it's like a barrier for memory, let's say. It's a little weird, but it's a collective call. So the second win-fence guarantees that all the operations that were issued before my win-fence call have completed when this win-fence returns. Okay. So in this example over here, when process 1's win-fence returns, I'm guaranteed that all the operations that process 1 issued have completed. They have all gone out of my memory. And all the operations that were issued to process 1, if other processes are targeting me, they have all entered my memory. Okay? So everything I have issued is out of my memory, and everything issued to me is inside my memory. Okay? That's what MPI win-fence guarantees. Okay? Make sense? Yes?
Why do you need the first fence?
Why do I need the first fence? That's a good point. So the first fence is actually needed if I'm doing some computation before by doing my communication calls. Like for example, if I'm modifying buffer A, okay, then I do a win fence. If I'm doing buffer, like modifying as in like locally modifying x equal to 1, right? Then I do a win fence, and then I do a put or get operation, or someone is getting the data from my location, getting variable X from my location. I need to make sure that the get doesn't touch variable X till my X equal to 1 has completed. Okay, so if I touch the buffer, if I'm touching my buffer, I will not let anyone else access my buffer till the win fence has been called. All right. So it's a little bit of a trick that we have to play, but it's needed. It's also needed for memory synchronization, memory barrier stuff, but that's a little too detailed stuff. I don't think we need to go into those details. All right. So that's MPI win fence. So now let's look at an example, quick example. Now we have been studying the stencil computation with send, receive, whatnot. We've been doing all that stuff. Let's do the same example is MPI one-sided communication with win fence. All right. Now MPI win fence. Now, first of all, I have to create this remotely accessible memory. Okay, so in this example, I will create my entire buffer, all of my stencil, all of my grid points that I have as my remotely accessible buffer. Everything is remotely accessible, even though in reality, I will not be communicating my center cells, right? Center cells are not communicating, but just for convenience reasons, I will declare everything as remotely accessible, right? So this is HPC, we pay fast and loose with no security, whatnot. So anyone can access anything. Now, once I do that, I can, instead of doing send receive with my neighboring processes, I can do put get. So I can use those red, orange-ish, weird colored buffers as my origin buffers and put them to my neighboring processes ghost regions. Okay, so I can do the, oops, I don't have animation, I can put my buffers to the target side. So I do a win fence, I do my 4 puts and do a win fence. So after the second win fence, all my puts have completed, I can use that data. All right, make sense? Okay, so there is a code example in the examples that we give, but I'm not going to go into that. It's a little running short of time, so I don't want to go into that detail. But you can look through the code. It's not too hard. It's very much like send receive, but it's one-sided in nature. So you can look through that example if you like.
Is there any extra cost associated for exposing more memory for remote access, or it doesn't matter?
It doesn't matter. On most systems, you're allowed to expose like 90 or 95% of your memory as remotely accessible. So practically, it makes no difference. Right? But that's a good question. Okay. So now WinFence, one of the problems with WinFence is that it's a collective call. Okay. So all processes have to coordinate in the WinFence call. So now if you go back to the example with the stencil computation, now each process is only communicating with its neighbors. Each process is communicating with 4 other processes. But my WinFence is synchronizing, potentially synchronizing all my processes. So if I'm running this with 100,000 processes, my WinFence is synchronizing all 100,000 processes, even though I am only communicating with 4 processes. Okay, that seems a little wasteful. So there's another call, another synchronization epoch called as post-start complete wait, where each process can essentially specify that I will only communicate with these 4 processes. Okay, so it's essentially limiting the synchronization needed to these 4 processes. And when you have these sort of limiting, your synchronization is limited, so you can potentially get better performance. Okay, so you have this post, so you have a target and an origin. The target says, I'm opening my window to be accessible by these group of 4 processes. Okay, and then the origin says, I am starting my communication to these group of target processes. Okay, then I can communicate. So in the case of the stencil, now I can specify that I will coordinate with exactly 4 processes and not 100,000 processes that you have in your system. So it can potentially be more efficient. Okay. In practice, however, if your number of processes that you're coordinating with, the group, is much smaller than the total number of processes, then you get better performance. But as this group increases in size, eventually at some point, WinFence will start doing better than post-start complete. Okay,
MPI group is different from communicator?
Yes, it is different from communicator. So in some sense, a communicator is a group plus a color. Okay, so the same group of processes can have many communicators that cover all the processes. Okay, and are you going to ask me a question of why I need multiple communicators? I'm going to answer it anyway. So why do we need multiple communicators for the same group of processes? A communicator is essentially a virtualization layer. Okay, so if I have communication on one communicator, it will not interfere with communication on a different communicator. That's the virtualization layer that MPI provides. So you can have, for example, if I'm using a library, a math library, and I want to use MPI, the math library wants to use MPI, and I want to use some other FFT library or whatever, that also wants to use MPI. We can all create our own communicators so we don't interfere with each other's communication. That's the reason why you can have multiple communicators, even though they are over the same group of processes. Anyway, so group is in some sense a subset of a communicator. All right. Okay, so we talked about these two synchronization modes, win fence and post start complete wait. So as I said, the put get RMA calls themselves are one-sided, but win fence is collective. Okay, and post start complete wait is coordinating over a group of processes. Now there is another epoch model called the lock unlock model, or sometimes we call it as a passive target model, which is one-sided in both put get or data communication as well as synchronization. It's one-sided in both parts. Okay, it's fully one-sided in some sense. So let's go to the example. So the way the win lock unlock mode works is that an origin process opens an epoch on a target. It says, I'm going to access this target process. Then it will do a bunch of put get operations, and it'll say, I will unlock. That is, I'm done with all my operations to that target. Okay, so all of the operations happen only on the origin side. The target basically does nothing. Okay, and just to clarify, the name MPI win lock is not the best name. It's actually a terrible name. A better name would have been MPI start epoch and MPI end epoch. That would have been a better name. Unfortunately, this got its name before my time, so I did not get an opportunity to influence that. But that's what we have. That's what we are stuck with. But it's not doing an actual lock. It's not doing an actual mutex. Okay, it's essentially starting an epoch, allowing you to do a bunch of operations, and ending an epoch. You can also call it transaction start if that's more friendly for you. Okay, now you have two types of lock modes. There is an exclusive lock mode and a shared lock mode. Okay, exclusive lock mode means that I want to open an exclusive epoch on a target process. Okay, when I open an exclusive epoch, as the name suggests, no other process can open an epoch on the same target at the same time. No other origin can open an exclusive epoch at the same target. If I do a shared epoch, then other origins can also create a shared epoch on the same target at the same time. Right? It's shared. But an exclusive cannot concurrently happen with a shared or an exclusive. A shared can happen concurrently with a shared. All right? The naming should be fairly obvious for that part. All right. So I can do a lock, bunch of put gets, and unlock. When I finish my unlock, all my communication, all my put get accumulate operations have completed both locally and at the target. So I know when my win lock has completed, I know that my data is available on the target window. Okay, that's the win unlock guarantee. All right. Okay. Win flush is slightly different. So you can do a bunch of put get operations, and you can do a win flush. Win flush essentially says that all of my operations have locally and remotely completed, just like win unlock, but I am not closing my epoch yet. Okay, so unlock says all operations get flushed, plus I close my epoch, and flush just completes the operations. It doesn't give up the epoch. All right, that's the difference between flush and win unlock. Sorry. There's another called flush local, which says that all my operations have locally completed. They're out of my buffer, but I don't know yet whether they have reached the target memory. Okay, just local completion versus remote completion. Right. There is another thing called lock all, unlock all, which is just like lock, but instead of giving one target, it says lock all my targets. Okay, so I can do communication with anyone. Unlock all is the same thing. So I'm not going to go too much detail into that. All right, let's look at a quick example of how this will work. So we have, so Halim, I'm going to take 10 minutes of your time. So, so let's look at one example that uses MPI one-sided communication. So this is this large quantum chemistry application, NWChem. It's huge. It's like 4 million lines of code, and it has about the amount of direct investment in that code is about $200 million, though in some estimates, with including the indirect estimates and so on, it's more close to like $400 million. So it's a huge application, very expensive application, and it naturally fits this kind of one-sided communication paradigm. So let's look at how this example works. So this application has to store all these large data sets. These data sets it stores on this global address space. It creates this multi-dimensional global array. Okay, several terabytes, several hundreds of terabytes large array it creates and puts all its data in this gigantic array. Okay, so that's how it views it. It views it as this huge 100 terabyte array, but internally, of course, no process has that much memory. So internally, it's split across all these different processes, different physical processes, and a part of the data is stored on each of these processes. Okay, and when you access a location in this global address space at the top, that red blob over there, internally, someone translates this to a communication to the appropriate process, to the appropriate memory location. Okay. So then it goes through multiple layers. There's a layer called global arrays, which gives this semantics of this large multidimensional array. Internally, it translates to this thing called ARMC MPI, which internally translates to this MPI one-sided communication. So it goes through multiple layers of the software stack, but eventually it comes down to MPI to say, move this data onto that target to that location. Okay. Now, conceptually, this is a very simplified version of how the application works. For one, the application deals with 6-dimensional tensors. Okay, but since my slide is not 6-dimensional, I simplified that to a 2-dimensional matrix of what it is trying to do. Okay, and in this matrix, in some sense, okay, very roughly speaking, it's trying to do a dgem. Okay, that's all it's doing, a dgem for one of the core computations. But the dgem is not your traditional dense dgem. It's a block sparse dgem. Okay, so you have a bunch of these blocks, which are the dark colored blocks are the blocks that have data, and the light colored ones are ones that don't have data, zeros basically. So if you do a dense dgem, you're essentially doing a lot of useless computation. So they do this block sparse dgems. The way this block sparse dgems work is that you fetch a tile from array A, fetch a tile from array B, you do a local dgem on these tiles, and the resultant value you accumulate into this global matrix C. Okay, and you do this for all the tiles that are there, the entire combination of tiles, and you finally get this answer C. Okay, that's the general model that is used. It does a little bit more complicated stuff internally. It uses this thing called nextval for doing load balancing and whatnot, but we'll ignore all that stuff here. All right. So we have a code example in your examples directory that you can look at. Again, I'm not going to those the example itself, but when you're doing these sort of communication, when you're accessing chunks of the tiles of this array, different processes are asynchronously accessing chunks of the array. It makes it more natural to look at this as MPI one-sided communication, rather than using MPI two-sided or collective operations, because you only care about fetching the data. You don't want to coordinate with other processes. You're just trying to interact with the data. Okay, so that kind of naturally fits with MPI one-sided communication. All right, so the last part I just want to spend like 2 minutes is the MPI RMA memory model. Okay, so this is easily the hardest part in the MPI one-sided communication chapter, or entire MPI standard maybe, apart from Fortran, that's very hard. But this memory model is one of the hardest pieces. But I'll try to give you some description of how that works, but if you don't understand it, don't worry too much about it. For most MPI one-sided applications, you will be just fine without understanding this piece. Okay. All right. So let's see how this will work. All right. So I said that every process exposes this buffer, right? That is remotely accessible. Okay. But logically speaking, MPI treats this as two different buffers. Okay. One is a public buffer. Second is a private buffer. Okay. For every buffer that you exposed in MPI, MPI treats it as two buffers, public buffer and a private buffer. Now, when processes are reading or writing into memory, they're touching the public buffer. When they're doing put-get, they're touching the public buffer. When you directly access your local memory that you exposed, you are touching the private buffer. Okay. Now, in some implementations, MPI implementations, depending on the hardware, this public buffer and private buffer are disjoint, and you need to poke it in software for them to merge. Okay? For some MPI implementations, depending on the hardware, this public and private buffers automatically get synchronized by hardware. Okay? That's the difference. So roughly speaking, the MPI standard doesn't say this, but just for your understanding, roughly speaking, you can think of it as the left side picture is a non-cache coherent hardware. Okay? Non-cache coherent hardware, like the NEC machines, NEC SX machines, right? They are non-cache coherent. The right side is cache coherent hardware, like your Cray machines or Intel machines or whatever. Okay? So left side is non-cache coherent, right side is cache coherent. Roughly speaking, okay, the MPI standard doesn't say this, but just for your understanding. Now, if I have non-cache coherent hardware, when I'm doing RDMA, RMA accesses from remote put-get operations, they go directly to memory. They don't go to cache, they're going to memory. However, when I access it with directly local buffer, I'm accessing cache, not memory. So it has to be fetched into cache. That's really the distinction that is happening here. Okay. I also want to emphasize that these are logically two different copies. It's not actual two copies of the data. You're not blowing up your memory usage. They're logically two different copies of the data. Okay. So this complication of having this two sort of buffers, public buffer and private buffer, makes this a little complicated, especially when you mix MPI put-get operations with your direct access operations. If you mix these two, you have to be careful about how that will happen. The most important case for you to think about is the last case on the right over here. So let's say some process is doing a put to variable X in my remotely accessible memory. And I'm doing a store to variable Y, a different variable in my local access, in my remotely accessible memory. Now, these two can corrupt each other, okay, because of how the cache coherence for weakly coherent systems works. So that's one thing that, again, if you didn't follow that part entirely, you shouldn't worry about it. For cache coherent systems or unified memory model systems, this works much better, much more similar to what you would expect. If you're touching different variables, there is no problem. One thing I should point out is that all of this memory model semantics are only important if you are mixing put-get operations with load-store operations, like direct access operations. If you only use put-get, you can ignore this memory models. MPI will take care of all this for you. Okay, if you're mixing direct access and put-get operations, only then you have to worry about the memory model semantics. All right, so I'll skip. There is a tables over here. You can look through these tables later to see what is allowed, what is not allowed. But I'm not going to go over all these tables. All right, before I hand off to Harlem, any questions on MPI one-sided communication? No questions? Should I ask questions? How many of you know MPI one-sided communication? 3 people. Excellent. All right. Thanks, guys.
Hi. Can you hear me clearly? All right, awesome. So up until now, we've been talking only about MPI. So I'm sure all of you are sick of MPI by now because it's the whole day about it. So this time, for the last chapter, I'm going to talk about how MPI interacts with other programming models, especially shared memory programming models. So I'm pretty sure many of you have heard of
MPI plus X, where X is usually, it could be any programming model, but usually it is a programming model used on within a node, for example, of a computing cluster. So so far in the morning and this afternoon, we've been talking about the MPI only. MPI only. All right, so I'm gonna use the mouse because the people online, I keep complaining about the laser pointer. So in this model, I call it MPI plus 0 because there is actually nothing else other than MPI. So MPI plus 0 equals MPI. So what happens here is that when you have a single node here, only isolate the system to a single node. You have multiple cores, and usually the model is to spawn one MPI process per core. The other resources on the node, these processes see them as belonging to them. The whole memory is accessible to the process. The whole network is accessible to the process. Performance-wise, usually these computation for resources are not very efficient. And usually when you use a shared memory programming model, you can manage these resources in a better way. So the most popular model is when mixing MPI with threads. For example, you probably heard of MPI plus OpenMP. But also you can use other threading models like Silk or TBB or whichever you are comfortable with. In this case, usually you spawn one or a few MPI processes. Each process has multiple threads, and these threads are running on cores or hardware threads. Another model to use is it's still pure MPI, which doesn't use a different programming model completely, but it exposes some memory, the shared memory on the node, visible to all the processes on that node. Those processes can access that memory with load stores instead of put-get as previously discussed. The last one form that we will discuss will be MPI plus accelerators, like GPUs and so on. So in this case, it's a bit different, but we will be discussing how the MPI, even though the MPI standard doesn't say anything about GPUs or accelerators, we will see how MPI implementations are trying to move data efficiently from GPU to other GPUs, memories, or from GPU to a CPU main memory. So let's start with MPI plus threads. So the first thing is I would like to motivate a little bit the case. MPI plus X is usually harder than pure MPI because you have to manage two programming systems. So the reason why people are interested in moving to a hybrid programming is not because of programmability simplicity, but it's because of the resource constraints. One of the biggest motivation is memory capacity. Here you can see the evolution of the amount of memory per core on the top 500 list of machines. We'll see that in the past, the amount of memory per core keeps increasing. At some point when we hit the memory wall, it stagnated. And then now it's going actually down. For example, the number one machine in the world right now on the top 500 has only 128 megabytes data per core, which is less than the flash disk or the USB stick you are carrying with you. It's very tiny amount of memory. What does this mean? This means that applications have to utilize efficiently this memory scarce resource because there is just a little bit of it. And this needs to be managed efficiently in two ways. One is in terms of memory footprint. You don't want to spawn many processes, MPI processes, because each process will have its own buffers and all runtime data. But instead, fewer processes will consume less of that scarce memory resource. The other is that usually load stores are more efficient on the node, so you would like to use load stores instead of message passing within the node. There are other advantages, but I'm not going to go through the full list. Here I give two examples, real examples where applications are faced with these problems and they use hybrid programming within a node. For example, Monte Carlo simulations, they usually have a lot of data, which is actually read-only. And in this case, it's perfect for sharing within a node instead of replicating across processes. So usually what they do is they use OpenMP for shared memory programming so that threads can share all this read-only data and avoid wasting memory. So how does it work with MPI plus threads? So given a multi-core machine with multiple nodes, each node has multiple cores, the traditional model on the left, we spawn one MPI process, and each MPI process has, halo zones or ghost zones for when you do domain decomposition. Oh, it's speeding up. Okay. So instead of doing that, we spawn fewer processes in the hybrid model, and each process will have many threads to perform computation and even communication if necessary. So how does it work? So the usual model is to use a domain decomposition through MPI by having coarse-grained parallelism. And within MPI, we do more fine-grained parallelism using other shared memory programming models like OpenMP. The most dominant threaded models that we encounter in practice is OpenMP because it's pretty simple for parallel loops and now with more asynchronous parallelism with tasks. But pthreads also gives you more flexibility where you can implement exactly the code the way you want it. And the biggest problem when talking about MPI plus threads programming, it's not about MPI or threads separately, but it's in the plus. The plus means interoperability, which means how do the MPI talk with application threads and what kind of issues can arise. There are two major issues that can arise. One is correctness and the other is performance. I'm gonna go through them later, one by one. But here I show how the applications basically commit to the MPI implementation on which threading level users they would like. So basically at initialization time, the application tells the MPI implementation what is my threading model that I'm following, essentially which threads are calling MPI or not. Here I'm gonna go through each level separately. In the MPI thread single, which is the one that everybody knows, when you call MPI init, by default, it's called MPI thread single. Essentially, there are no threads. There is no notion of threads. And only processes are doing both computation and communication. The next level is MPI thread funneled. We basically, in this case, the application guarantees that only the master thread is doing communication. The other threads only do computation. So here, the changes that you need for your program is to ask for thread funneled from the MPI implementation and check if it's actually provided because this is optional, not mandatory. So the MPI implementation might actually not provide the funneled level or the other higher levels. And here I give an example with pthreads. So with pthreads, I'm gonna create a function, thread that executes a function which does the computation instead of doing it sequentially in a process like before. And then I will join the threads, and now I can do MPI stuff. And the MPI stuff is done by the master thread. So this is a correct MPI thread funneled program. Now the next level, which is kind of more flexible, is we can allow one of the threads to perform any of the threads as long as only one at a time is calling MPI. We basically serialize the MPI calls. So here again, we pass the serialized level to the MPI thread init thread actually, and the typical way to serialize the calls is using locks or mutexes. So here the function is the same, but the MPI stuff, instead of being in the master thread, now it's moved into the function, and this function can be executed by multiple threads concurrently. So to serialize the calls, I basically first acquire the lock, do the MPI stuff, and then relinquish the lock. And this way, I serialize all the MPI calls. You can do the same with OpenMP with critical sections or with locks as well. So the final one has no restrictions. Basically, any thread can call MPI. This one has more tricky problems that we will discuss later. But the general model is that I ask for thread multiple, again, check if it's provided by the MPI implementation, create threads, do computation, do communication, do whatever you want, no restrictions. So a little bit more about these threading levels.
So thread single is mandatory for MPI implementations to support, which is basically normal behavior. If you want to provide thread multiple, the MPI implementation has to provide thread safety, plus other progress guarantees that we will discuss soon. And if you have threads in your application, but you call MPI in it, that's actually an incorrect program. You have to specify at least a thread funnel depending on your usage. So from now on, we'll discuss a lot about thread multiple because that's the one that gives a lot of, that needs to be carefully used by the user. So there are two semantics that the MPI thread multiple, the MPI standard defines for MPI thread multiple. One is ordering. Basically, since we know that thread execution is non-deterministic, they can execute at different speeds, then it might result in some ordering that might violate the MPI standard. A typical case is when calling collectives on the same communicator. It is forbidden for, basically the standard says that collectives on the same communicator have to be issued in the same order. Otherwise, it's not an MPI, correct MPI program. Typically, it will lead to a deadlock or maybe even worse. The other property is progress. This one is one of the most important. So you cannot simply provide thread safety if your threads call blocking calls and then they just block all of the other threads. So the MPI standard says if a thread is blocked in a blocking call, it should not block the progress of other threads so that everybody can make progress. So from now on, I will go through a series of examples that are incorrect by the previous definitions I just gave. So here, I give an example with collective operations. If you forget about these threads and you look at this from a single-threaded perspective, this is actually a correct program because both broadcast operations are issued in the same order on both processes and they get matched properly. Now, if I execute these operations in a multi-threading way, these threads can run at arbitrary speeds, and the order might be different on the processes. And then a possible matching that will happen is that a broadcast will try to be matched with a barrier, and this violates the MPI standard, and it can lead to a lot of problems. So how do you, as a user, solve this problem? You have to ensure the correct order by yourself. For example, by using locks or using some thread synchronization to make sure that the order of these threads calling the collectives are called in the right order. A similar ordering problem is when I do a collective or an operation on a communicator, and another thread frees the communicator. So obviously, if you try to do a broadcast operation on a communicator that got freed previously by another thread, then you will result in corruptions and segmentation faults and so on. So the same way as before, if you want this to work correctly, you need to synchronize them properly with proper thread synchronization mechanisms. This one, if you look at it from a single-threaded perspective, it's the opposite situation. If you do this from a single-threaded perspective, it's actually incorrect because both processes issue the receive, waiting for each other, and then deadlock happens. But if we introduce threads this way, it's actually a correct MPI program. Because what I said before is that the progress requirement of MPI says that like a thread blocked in a blocking operation should not block the progress of other threads, which means thread 1 is blocked on a receive. It should not block the thread 2 that does a send, which means both of them can actually progress simultaneously. And there should be no deadlock because at some point these two operations can match each other. So basically, a correct MPI implementation that gives thread multiple should make sure that this example passes. So what's the current situation? So all MPI implementations support MPI thread single because they have to. So many of them support MPI thread funnel, even though they are not saying it explicitly, because thread funnel is easy to support because by default we pass the right when you build the binary, the user code. We usually pass the, for example, pthread flag, and it makes sure that
the thread-safe versions of system calls, for example, like allocation and error checking and all that stuff is done in thread-safe manner, and it actually satisfies the thread funnel requirements, even though they don't admit it. So many of these implementations, because thread multiple is becoming more and more important for applications, these implementations support thread multiple, and the efficiency still needs more work, but it's a lot of codes are actually using it. So I have no idea what it is. So now I will give an example that we usually give to the audience, even though all you guys have the slides and you can cheat, which means I'm not gonna ask you, but I would like you to think about this example, whether it's correct or incorrect. If it's incorrect, then try to think of what is broken in this program. Why is it not MPI standard compliant? So basically the red part is executed by one thread and the green part is executed by another thread, and something might happen. So I will give you just 30 seconds, 1 minute to think about it while I grab something to drink. All right. Anybody who didn't cheat and knows the answer? That means it's either you don't know the answer or you are cheated. So, anyway, so if you look at it from a single-threaded perspective, on one process I'm issuing sends and receives, and the other process issues receives and then sends, which means I'm alternating sends and receives, and deadlock should not happen. But in multi-threaded, this program might hang. It's actually, deadlocks might happen. So why is that? So when you write this program, what you think would happen is that the alternation of send and receive will happen this way. One thread is issuing the receives and sends, and then it will match these send and receive this way, right? But sometimes it works actually this way, but sometimes it doesn't because of different speeds of and non-deterministic execution of threads, you get something a little bit not like that. At some point, all threads issue a receive operation, and then a deadlock happens. So that's what happens in this example. So thread multiple can be tricky, but if you do it properly, it can give you a lot of benefits. All right. So from now on, I will stop talking about pthreads, but I'll talk about OpenMP. Even though from a thread multiple perspective, the requirements are similar because from this picture, MPI interoperates with other threading programming models through usually pthreads or other threading packages. But pthreads is the most used threading package. That's why I'm using it here as in this graph. So which means is that if you take an OpenMP thread or Silk worker or something, these are usually translated to pthreads, and all the progress and thread safety requirement I talked about before applies to these threads as well. Which means if two OpenMP threads are issuing some blocking operations, they should allow each other to make progress. So one important thing is that OpenMP tasks, in the current standard, an OpenMP task that does a blocking operation also blocks the whole thread that is executing it, which means you don't actually get the asynchrony you are looking for. This problem, we are trying to address it in the OpenMP standard, but there is nothing in the standard yet. So here I'm going to go through a series of examples also, and I will show things to avoid and erroneous programs that you will run into if you use MPI plus OpenMP with thread multiple. A typical example is you have a parallel loop and you do a bunch of blocking point-to-point operations. So now in this case, this program will hang for the same reasons as the previous example I showed. Essentially because since here I am letting OpenMP distribute the iteration space among threads, the threads can issue the same type of operation at the same time. For example, they can both do a send operation, and then a deadlock will happen. So let's take an example to be more concrete. We have an iteration space of 100 iterations. I will divide it by 2 threads. Now, threads here, even threads would do a send, and odd iterations would do a receive. So if I divide it equally between the 2, which corresponds to static scheduling in OpenMP with chunk size, the default size is usually the maximum size you can, which means each thread will get 50 iterations. The first thread will start from 0, and the second thread will start from 50. Both of these iterations are even, which means they're going to go through the send path. Both threads issue send, deadlock. So how would you solve this type of problem? So to solve this, the user has to distribute carefully the iteration space between threads to avoid this. One way is to, first, for this program to work, it has to have at least 2 threads. And the second condition is that one way to do it is use a static scheduling with chunk size equals 1. Chunk size essentially says how many iterations I give to each thread. And what does this do is that it forces threads to alternate like iterations between them, so that if 2 threads are concurrently executing 2 iterations, one of them is, for example, 2 threads, one of them is doing a retrieve, one is doing a send, and that way a deadlock is prevented. So how about tasks? In tasks, we cannot do the same thing with parallel loops. And the reason is that tasks can be executed in arbitrary order. It's not like an loop iteration where we know that these iterations will be executed one after the other. A task will be spawned and then will be executed in any order. What's the consequences of this is that we cannot assign these iterations in a way that will prevent the deadlock, since they will be executed in any order. So how do you fix a program like this? So I'm just giving an example with different syntax from OpenMP. So for those that are not familiar with OpenMP, the rest of the institute has, and also other programming models, the rest of the institute has OpenMP and I think GPU programming, where you can catch up to this. But for now, I'm just using basic concepts. So task loop is essentially the same thing as a task, where I spawn tasks within a loop iteration. So one way to avoid a deadlock is using non-blocking operations. Essentially, doing an I send and I receive, which is non-blocking. But the issue is that if I do it inside a task, if I wait for them, the problem remains, because wait is a blocking operation. I'm waiting for it until it completes, which means it's the same as doing a blocking send or a blocking receive. So this solution, actually, this is not the proper solution. So one way that the user might think to fix this is using a task yield. What task yield means is that when I cannot make progress, I will yield so that another task executes. This is actually what the MPI implementation is doing inside when you use thread multiple with, for example, pthreads. When I do a blocking call inside, I yield to the other threads when I do a blocking operation so that other threads can make progress. So it's basically the same model. However, there is a gotcha. This program is still incorrect. The reason is that the OpenMP standard says that a task yield does not guarantee a task context switch, which means it could be a no up, which means there's no guarantee that I'm actually yielding to other thread to make progress, in which case this loop becomes just an infinite loop and a deadlock happens again. So are we running out of solutions? Well, not yet. So we can still do it, use non-blocking operations, but the blocking property will be done outside these concurrent threads. So what I will do is I will have an array of requests, issue a bunch of non-blocking operations concurrently. This is good like for pipelining messages, for example. And the master thread is going to wait for them, which means all these tasks are not going to be doing blocking calls, in which case you don't worry about progress or other problems. So one final example is using RMA. This is a case where if it's a sequential problem, you don't need to worry, but if it's multi-threaded, you have to worry again. So what happens here is that I have an RMA window, and I do a lock operation on a target process on the same window. So this looks innocent from a perspective of single-threaded, but if I do, if two threads are doing these operations concurrently, what will happen is that the lock operation will be executed on the same target twice from the same process. And this is forbidden by the MPI standard. You cannot lock twice the same target. It's similar to a mutex lock. You cannot try to lock it twice. Otherwise, you will just basically wait for yourself to give up the lock, and that's erroneous. So this is, I think, so far for the OpenMP examples. If you have questions before we can study a stencil code, we'll walk you through the stencil code. Maybe the people online, I'm not sure. If you have questions, let me know. Go ahead.
Is there any MPI wing dry lock or something? A dry lock, not lock or unlock, but dry lock.
Oh, we on the window?
Yes. No. Okay.
All right, so I'm gonna try to figure out how to load the examples. So I'm gonna show a funneled and thread multiple versions of the code. Where is it? All right, so you're familiar with the example, I guess, so I don't need to walk you through the individual details, but I will just highlight basically the lines where we have to change it to make it work properly. So first I need to request thread funneled from the MPI implementation and test if it's actually provided. If it's not, I will just abort because I need it. Here it will pass fine. And then now if we jump into the communication part, we will see that it's exactly the same as before. I'm doing communication, and then I wait for the completion. Now the changes inside the update grid, which is the computation part, and this update grid is multi-threaded using OpenMP. So the inner loop is parallelized with OpenMP4, and I'm using the reduction on the heat because multiple threads will contribute to the heat value. So it's very simple. Thread funneled is pretty popular because you don't need to worry about many things. The only gotcha is that only one thread is driving the communication, and usually and in the future it's going to be a problem because you might want to use multiple threads to drive your communication because it's faster. So now we look into the thread multiple case. In this case, threads will do communication and computation at the same time. This one requires a little bit more work. So the way we do it is by splitting. We have a 2D domain, and then between threads we will split it by columns, and many columns will belong to one thread, and so on. And each column, each thread will be responsible to send data that it owns to the right process. So these macros define the boundaries of the domains depending on the thread ID. So here, the change that is required, the change is that I created a parallel region, and for each thread, I get first the thread ID, and then I check where from which columns I'm responsible for in the computation and communication as well. And then I do the communication, but this time I need to I only send my portion of the data. I also needed changes to the data type creation, because I don't need to send. Oh, never mind. I don't think we changed that. Anyway, and now each thread does both communication, as you see here, but also does the computation. So they do computation on their portion of the grid and the communication as well. So you can play with this code, and so that you learn what basically you need to do in order to make it work correctly. Just one last detail. In the previous case, I didn't need to worry about the tag value. Where is the tag value? So I'm using here in this example the thread ID as the tag value. The reason is that if I go to this case, so these basically indicate the so these lines indicate basically which portions of the subdomain each thread owns, and then each thread will send data like the small chunks that it owns. The problem is that if I don't use tags, because the communication needs the communicator, which is shared among all threads, the processes, target and source of the processes, which are basically also shared by all the threads. For example, all these small chunks will be communicated to the upper part of to the upper process, and the data could be misplaced in the buffers, because they use both the same rank, same communicator, and same tag. The data from this, for example, process could from this chunk could go to this one, and it will result in erroneous execution. To solve this, we need to use tags, basically to mark these chunks with different tags so that they don't mismatch. So the easiest way here is to use thread IDs as the tags, because each thread ID indicates a separate chunk that it owns, and it's sufficient to make sure that mismatch doesn't happen. So that's all for the examples. If you don't have questions, I can move to the MPI shared memory. Maybe from the online folks, nobody, nothing. Right.
The question on Slack here about, is there a method to resolve the memory race problem when multiple threads try to access the same memory at the same time? Basically, does MPI provide anything?
Not MPI, but you can use something like thread sanitizer, some tools that are, this is a general problem, not MPI problem. So you can always use, for example, thread sanitizer, I think, works with Clang, and you can run your application. It tells you that there might be some races. Yeah. Other questions? So I'm going to move away from threads and move to the MPI shared memory. It's basically the same concept in a sense. You want to access the memory with load stores, but you don't need a different program model. You can use a few calls from MPI to achieve that. So how does it work? Let me just move to the example directly. So assume that you have 3 nodes. Each node has few processes. What we want to do is the processes on each node to know that they are sharing that node. We want to know that these processes that they are running on the same node instead of being separate on different nodes. Once we know this information, we can expose some memory so that these processes can access it. The way to get this information is to use the MPI comp split type. What this operation does is, from some communicator, a bigger communicator, you want to divide it into smaller communicator by clustering processes that run on shared memory. And then you create each subgroup of processes have a shared memory communicator. Once you obtain that shared memory communicator, you will do the same thing as RMA. You will create a shared memory window, but you use different call because this shared memory, because this window is gonna be shared on shared memory. It's like a shared memory segment that can be accessed by all processes with just load stores. Once you have that, instead of doing put get, you will just do load stores, and you can access it as if you were running with threads. So this is the basic difference between a normal window and a shared window. In a normal window, the local memory of a process is accessed by a load store because the process owns the memory. And when accessing remote data, it has to use put, get, accumulate, and other operations. In a shared memory window, because we are running on a shared memory, we can do load stores on our own memory. That's a given. But also the remote memory, as in the memory that is owned by another process, is on shared memory. I can just do load stores on it. And that way I can achieve basically kind of a behavior similar to threads without the shared address space problem. So here a little bit more details about the signature of the functions needed for this. So MPI comp split type takes a parent communicator and outputs a new communicator which contains the processes belonging to the same shared memory node. So the most important argument is the split type. You need to pass the MPI com type shared so that this is a hint to tell it what is the criteria that MPI is going to use to divide this big communicator smaller one. And it's going to use the shared memory information for this. And the second call is using MPI when allocated shared. So it works the same way as when allocate. Each process contributes some memory, and this memory does not need to be contiguous, belonging to all processes. But you can pass a hint to this function through the MPI info to tell it, give me a contiguous chunk of memory so that I can access it as if it was local. So this is an example how what is the flow of getting MPI shared memory. So you have your init and you split. For example, here we are using MPI com world, even though we don't actually explicitly say it. But we pass the com type shared as the split type to get the new shared memory communicator. Then we use MPI allocate shared to get the window. Now I can use. I need to also open epoch similar to RMA, so that I can signal to the other processes. Now I'm starting to access your data. So here I use local to signal that I'm accessing the memory of all processes on the node, and then I can start doing load stores. MPI WinSync is used like memory barrier, so that it updates, it flushes caches and so on, so that the data local changes will be visible to other processes on the node. You can think of it as an OpenMP flash or something like that. And then when I'm done with these load stores, I can unlock the window and do some other stuff. So as I said before, the memory allocation does not need to be uniform. Processes can contribute the amount they can. Some processes might not contribute anything if they want. And so there is no, basically the MPI standard doesn't doesn't force to allocate the memory. Like there's no way to control where the memory will be allocated. But the general idea is that the MPI implementation will try to allocate it where it is closest to the owner of the memory, the process owner of the memory. So by default, if you call the when allocate shared, it's going to give you a contiguous chunk of memory segment. But if you want something non-contiguous for alignment purposes, for example, to avoid false sharing or things of that sort, you can pass hints and say, give me a non-contiguous memory, and so on. We have also a standard example with MPI shared memory. Do we have time to do it? I think we do. So I will show a little bit there are more functions that I think I missed I will cover them in the example. If you have questions, meanwhile, please let me know.
So how do you compare this MPI plus threads model with the present one? I mean, can you give examples where we would prefer the MPI plus threads model compared to this one?
I have a slide that gives a general rule of thumb.
Okay.
But generally, it depends on the amount of sharing you want. When you have few data structures that don't need too much synchronization, but you want to share them, you can start with this so that it gives you private address spaces, and only expose the little things you want, the few data structures you want. But if most of the data structures you want to share them, then better to use threads, because by default it gives you shared address space, and then just use that. That's the general rule of thumb I give to people. But some people are not comfortable using more than one programming model. If they want to do, for example, everything with MPI, then maybe they can do it with the MPI shared memory. One last detail is that when MPI doesn't give you any ways to synchronize accesses. For example, it doesn't give you mutexes, or it lets you basically use whatever programming language synchronization you need. For example, atomic operations, compare and swap, and things of that sort, to synchronize processes when they access the window. It's kind of less convenient than using threads. For example, with OpenMP, you can do critical sections easily, while with MPI you have to do your own thing. So usually, if you have data structures that are read-only, that's MPI shared memory is better. You just read from that, right? A good example is QMC Pack. I think they have some read-only big data structures they can share between processes. So what's that?
Use share memory window instead of a share memory API as pthreads or OpenMP. What are the advantages of use share memory window instead of a share memory API as pthreads or OpenMP? Which one is?
The question is, when is better to use an actual RMA window versus a shared memory window? It's the same question that was asked, I think. I just give the answer, but I will give the answer a second time with pretty figures. So as I said before, the first thing you do is you take the parent communicator. In this case is MPI com world. Then you pass it com type shared, so that it gives you shared. Here we call it the shmem com, which means basically the communicator that contains processes within each shared memory. So this step is pretty simple, and the rest is similar. Here we have we do the win allocate shared. Essentially, we allocate the whole domain, I think, as a shared memory. The whole stencil domain is allocated as shared memory within one node. And our next step is a little bit trickier, which is to the MPI win shared query. Basically, each process needs to query which part of the domain belongs to it. It needs to get basically in addresses, offsets, I think, displacement with respect to the beginning, so that they know which segment belongs to which process. Here it passes the process that is situated on the north side, south side, east, and west. It wants to get the displacement so that it knows which part of the memory it needs to access. After that, the computation is rather simple. So mostly this part is doing the computation. it needs to use the displacement that was computed before to know which part of the grid is going to update. The only gotcha is that here it needs to use MPI wincing so that it makes sure that these local changes gets reflected in other process memories as well. That's the basic change. If you have any questions, let me know. I also forgot to mention that we need to open and close the epoch after you are done. That's basically it. So I'm going to move on the slides unless you have questions about the example. So I was just asked before a question about which shared memory programming model I should use. So it really depends on your application, on the needs of your application. So the rule of thumbs I usually, basically, the rule of thumb I just give to one of the people in the audience is when you have only few objects that needs to be exposed to the other processes for shared accesses, I would use MPI shared memory because you would like to have private address space and the few objects you want to expose them. The other way around, if you want most of your address space to be visible to everybody, then it's better to use threads because by default you get it. And then if you want some private data to be private to your thread, then use private constructs like OpenMP private. That's the general rule of thumb. So the other aspect, I think that kind of covers most of it. So I also mentioned the case where you need synchronization. You need really little synchronization or a lot of synchronization. So you have a shared object. If this object needs a lot of synchronization for accesses, where you need locks or atomic operations, usually it's better to use threads because they give their threading models usually give you means to achieve that easily with critical sections, locks, and atomic support. But if you use MPI shared memory, MPI doesn't give you anything apart from wincing, and wincing is a basic memory barrier. It doesn't do anything else, which means you have to use something like atomic operations of the language, for example, C11, to achieve that, or use some pthread mutex lock or something like that and expose that across multiple processes. It's kind of tedious. So if you have a lot of sharing and a lot of synchronization, it's better to use threads because it's more, it fits better the threading model. Here I give an example with QMCPack. So QMCPack has big basically data structures that are read-only. These are kind of the application scale depends on these data structures because they want to run as much as the biggest program they can fit into memory. And if this data is replicated across processes on the same node, it chews up all the memory, and the problem size they can run is reduced a lot. So one way to do it is to share these data structures, is to share it either through shared memory. Here you expose this big data structures through shared memory, and the rest of the code can use threads or single-threaded, it doesn't matter. Or you can use threads. Threads also allows you to do this easily because it's read-only, no synchronization. So it really depends on your needs and your preference. So that's it for MPI shared memory and threads. If you have additional questions, otherwise I will start tackling the GPU part. Are there any questions on Slack, maybe? All right. So now I'm going to move to GPUs. So the MPI standard says nothing about GPUs or accelerators. It's all about the MPI implementation, whether it can do some optimizations in data movements. So what are GPUs? As you all know, those are throughput-oriented architectures, and a lot of applications are offloading like computation to those GPUs when they are suitable. And usually MPI is running on the CPU while the GPU is responsible for heavy computation. You can program these GPUs through different models, such as CUDA or OpenACC or OpenCL. And when we are talking about MPI plus accelerators, it's usually MPI plus one of these programming models. So there are a lot of GPUs are quite successful in the community. Many top machines are using GPUs to achieve the highest tops, and a lot of top-ranked machines are using GPUs. So what are we interested in this tutorial is how to move data from GPU memory to somewhere else. It could be to a CPU memory, because the buffer for the communication is in the GPU memory, and I might move it to a CPU memory, or I can move it to a different GPU. So how can we do this efficiently? First is the simple way. Here I give CUDA and OpenACC as examples to achieve this. And the most straightforward way, which is not optimized, and it's that's the model followed by old GPUs and old MPI implementations. If you have some data on the GPU, you do some computation on the GPU, and now you want to send the data to a remote process. You first have to copy the data to the host memory, and then send that data. On the receive side, you are waiting for the data to come. So on the host memory, once you get it, you send that data to the GPU memory with a memcopy, and you start computation on the GPU. So this is the typical model. To achieve the same thing with OpenACC, which is just the simpler version of doing that. First, you need to create a copy on the GPU, because both data structures need to be present on the GPU and the CPU, and then you do the updates accordingly. You do the computation on the GPU, you update the data on the host before sending the data, because the MPI is only aware of CPU memory. It has nothing, it knows nothing about the GPU memory in this case. So what's the problem with this model is that it's not quite efficient. So if you look at how I can send data from one GPU to the other, I have to send this data first to the CPU, and then from the CPU, I will use the CPU buffer to another CPU buffer, go through the network, and then I will copy that data to the target GPU. So this operations involves a lot of memcopies, a lot of DMA operations, and a lot of buffering. For example, these buffers might be used by the MPI implementations. So usually this method is not the optimal. So with newer versions of GPUs, we can do better. The biggest problem to achieve efficient data movements when involving GPUs is that when I do an MPI send, for example, the pointer to the address of the buffer, I have no idea where it is sitting. Is it on the CPU side or is it on the GPU side? So to solve this, recent GPUs have something, for example, this is a terminology from CUDA, the unified virtual addressing. What does this mean is that the GPU and CPU see a unified address space, and then a void pointer or pointer to some data can be pointing to any of this, or either the GPU memory or the CPU memory. And also it offers ways to query that pointer to know where the data is. Is it on the GPU or the CPU? Depending on where it is, I can do something more intelligent. This is an example of what you could do. If the data was on the GPU, instead of moving it to the CPU, to the host memory, I don't need to update the host copy, because here I just need to copy it to a different GPU. I can directly use it internally inside MPI to buffer it internally and then send it through the network. And I reduce the number of memcopies and number of DMA operations. And usually this gives you a lot of benefits already. So how can we program this? Assuming you allocated your data and everything, and your programming environment supports unified virtual addressing, you can pass directly a pointer to the data in the GPU. Internally, the MPI implementation, which is called GPU aware or accelerator aware MPI, for example, OpenMPI and MVAPitch have versions that are aware of this. Query, and then they know where the data is sitting. They detect that it's sitting in the GPU memory, and then they can do a more optimized path. Another thing that so in OpenACC to achieve the same thing, you can essentially do some. You can have one variable, and the user directive which says for this pointer use the device version, basically to say that this in this block, in this structure block, buff points to the data in GPU, and then the MPI implementation can query it again and then do the same optimizations. Another optimization that we could do is if we were transferring data to CPU memory, I could detect that the other process is on the same node. I can just do directly a mem copy from the GPU memory to the target process instead of moving it back and forth from one GPU memory to the host memory, then from the host memory to another processor's address. So to do even better, we could avoid even these mem copies directly if the architecture supports GPU direct with RDMA. So how can you do that? So if the MPI implementation knows that the data is on the GPU memory and the target is on the other side, I can just do directly an RDMA operation in order to move the data without moving it to the host, without any buffering or anything. So this gives you usually the highest performance as long as the architecture supports GPU direct with RDMA. So these are the different optimizations that can be obtained when the MPI implementation is aware of accelerator programming, such as CUDA. I will give an example how it looks like. The example with updates, this one is still with old GPUs and old MPI implementations. I leave it as an exercise for you to implement something which is with GPU-aware MPIs.
Which MPI implementations are GPU aware besides MVI-Pitch2?
So I know MVI-Pitch2 and OpenMPI. I don't know if there are others. IBM Cray, according to Pavan. So there's a bunch. So the code will look very similar to the non-blocking version, the very basic. The only difference is that the update grid, which is the computation part, is done on the GPU. If we look at how it is executed, we have the Pragma ACC with OpenACC here, and we just do a basic parallel loop similar to OpenMP. The only difference is that this code will be offloaded on the GPU, as long as you compile it properly. Otherwise, it's just going to run on the CPU. But the most important part is using the right, good version of the data. The way you do it is once you do the Halo exchange communication in this part, you need to update the copy on the device, on the GPU, so that it uses a fresh version by using the update device call. Once it's updated, then you can do the computation. Now for the next iteration, I need to update the host copy by using the same pragma, but with the host as the argument. And now the data on the host is up to date, and the next send operation is gonna pick up the good version. So this obviously does not use any MPI like GPU-aware MPI implementation because it's managing everything manually. Performance-wise, it might not be good depending on your application, on the problem size, and so on, because of the mem copies and DMA operations. So that's basically it. I think I covered all the hybrid stuff. We have 15 minutes left. We can do either questions, or I will leave Pavan to discuss a little bit other topics.
GPU-aware MPI implementation, does it have some extra syntax, some extra operations, or it is all transparent to the user?
It's all transparent. You just need to pass. Basically, you pass a pointer. In the worst case, it's going to pick up the host version as long as it's up to date. But usually, you pass the pointer, which for the data that is on the GPU, and automatically everything is done transparently for the user. The only thing you do is the compilation time. You need to compile it properly for the right flags and everything.
And by compiling properly, you mean that GPU-aware MPI implementation has special flags for this?
Yes, so far I remember. So each MPI implementation has documentation on how to properly enable this GPU-aware capability. So whichever system you are using, either NVPitch, like if you are using NVPitch or OpenMPI or Cray or IBM versions, just check the documentation or ask the people, the admins, and they will tell you how to properly compile your applications to enable this capability. Other questions? All right, then I'm going to let Pavan pick up. MPI form or which one do you
All right, so we are in unplanned territory over here. So let's see which part we should focus on. We only have about 15 minutes, 12 minutes or so. So I'm not going to pick up a new big topic. We have some slides on non-blocking collectives, topology, neighborhood collectives, and so on. They're all very interesting topics. I strongly encourage you to look through the slides that we have for those, but I'm not going to try to cover that over here. I'll spend, it's the other way around. I'll spend some time talking about future topics in MPI that the MPI forum is considering for MPI 4. So let's see the slides for that. Even in that, I'll cover just a few topics for MPI 4. Okay, so just so all of you are aware, the latest version of the MPI standard today is MPI 3.1. Okay, if you download most MPI implementations, you get MPI 3.1. All right, that's what you get on most supercomputers. If you're running on with a Cray supercomputer, an IBM supercomputer, and so on, most of them are at MPI 3.1. The only exception is the Blue Gene machine. The vendor-supported MPI implementation for the Blue Gene is still MPI 2.1, pretty old, but it's essentially at end of life, at least the architecture. So that's not going to get upgraded. But all future machines are going to have MPI 3.1 or higher. Now, there are always some shortcomings in MPI that we continuously try to fix for different MPI versions. So the one we are working on right now is MPI 4. Okay. The target date for that is end of 2018, but it looks like we're going to slip that and we might end up in 2019 or something. We'll see. It's not concrete. But here are some of the proposals that are being considered for MPI 4. Okay, now just to put this in perspective, these are proposals. These are not a part of the MPI standard yet. Okay, there are, for some of these, there are implementations you can try out if you are very brave. And if you would like to give feedback to the MPI forum, please try it out. But remember that these functions, when MPI 4 comes out, these functions might not exist. They might not be voted in, or they might be voted in with a changed different semantics. Okay, so be aware of that. But if you are, brave and would like to help us out, please try this out. Okay, so I'll talk about some of the proposals that are being considered for MPI 4. We meet every 3 months or so to discuss these topics, and it's very intense discussion. Sometimes we go from like 8 in the morning to 8 at night talking about this, then we go have dinner and discuss over beer, and then come back again to discuss some more. So it's a very intense process. It's a very important effort because anything we define shows up on the latest supercomputer. So we have to be very thorough and very deliberate in how we define the MPI standard. Okay, so there are a lot of working groups. The MPI forum, the group of people who work on the MPI forum, it's divided into a lot of smaller subgroups, what we call working groups. And each working group discusses and tries to propose changes to a certain subset of the MPI standard. Here are the working groups. There are a lot of working groups that are working on a lot of proposals. I'll not go into all of these, but I'll give you a few topics. I'll hint upon these. Okay, so the first topic I'll talk about is MPI point-to-point communication. So MPI one-sided communication, we noticed that if you look at put-get operations very closely, you will notice that I can do a lot of put-get operations, a billion put-get operations, and complete all of them with a flush call or an unlock call or something of that sort. Okay, which means it's very resource efficient because I can have a million calls, and each of these operations I do not have to track each one separately. On the other hand, if you look at MPI ISEND sort of operations, each ISEND has to give a request, MPI request back. Okay, so you can track each ISEND separately, which means there is more resource usage for each ISEND. So if you look at some of the applications like genome assembly applications, you have lots of small messages that are being sent out. It becomes very hard for MPI to keep track of these millions of operations that the application might generate. So there is a proposal to make MPI ISEND IReceive more closer to MPI put-get, where you can issue a lot of ISEND-like operations, but instead of keeping track of each ISEND, we can complete all of them at once using the MPI com wait all or some equivalent function of that sort. That's one of the proposals. Now, the other proposal is, I think this was mentioned earlier, I think Yanpei had mentioned this morning, that MPI has a lot of semantics that are sometimes not necessary. Like if you do ISEND operations, they're ordered as long as you're on the same communicator, same tag, same source destination, they're all ordered. They're strictly ordered, one after the other. So if you send two messages, MPI guarantees that the first message will go into the first buffer. The second message will go into the second buffer. Okay, they might not complete in order, but it will go into the right buffers. Sometimes, if I'm doing message communication, especially with threads, and they all could go into any buffer, all buffers are the same size, you can go into any buffer, it's this forced ordering is making it hard for MPI to optimize, MPI implementation to optimize that. For example, I cannot send data over different routes. I have to send them over the same route because of the ordering requirement. So we have some hints which says, I don't need ordering. If the application gives MPI info hint that says, I don't need ordering, I can send over different connections, over different routes. Or if the MPI user says, I'm never going to use any source or any tag, MPI any source or any tag, I can do some hash table lookups instead of sequential queues to optimize performance. Same thing with exact lengths. If the MPI receive is allowed to give a buffer larger than MPI send, right? If I say I will never give a larger buffer, always give the exact size buffer, because algorithmically I know the buffer size, then I can do some more. So these are the hints. I just gave 4 examples over here, but there are like 25 different hints that the MPI forum is considering for inclusion in MPI forum. Fault tolerance working group. With MPI, one of the big questions that comes up with MPI all the time is, what happens when there's an error? Okay, when you do an MPI send, there's an error, what happens? Okay, today the way MPI is defined is that the behavior of the MPI implementation is undefined. Okay, which means the MPI implementation can do whatever it likes. In most cases, the default behavior is, if an error happens, MPI will go and clean up all of your application. Okay, all your processes get cleaned up. Now, some MPI implementations give you better semantics, which say that the remaining MPI processes will be alive. Some processes you can retry or whatever it is. But that's not well defined in the MPI standard. So there is a working group called the fault tolerance working group that is trying to define what will happen in these sort of situations. There are some, not going to the details, but there are some proposals that say, for some errors, for simple errors, okay, if I did a ISEND and I don't have requests available, I'm out of requests. So I can just give an error saying that you can't do ISEND right now because I don't have any requests, but it's not a catastrophic error, which means you can pretend like you never issued the ISEND operations. You can finish some of your existing ISENDs, pre-pending ISENDs, and try the ISEND again as if nothing, as if you didn't do any of that. So these are called non-catastrophic errors. And each MPI implementation can define what these simple errors are. For some implementations, simple errors are a bigger set than others, but each implementation is defined. So that's one of the things. We are doing some stuff with error handlers. I'll ignore this stuff. And the big proposals for fault tolerance is what happens when a process dies. Process dies, can the rest of the process survive? This is a very hard problem because MPI does not standardize fault detection, which is extremely hard. But MPI is trying to do other parts of fault like failure notification or propagation or recovery. It's trying to see how we can define it in a better format that applications can use. There are several proposals for the hybrid working group. One of the things that we assume in MPI is that if I have global variables inside MPI processes, two MPI processes, global variables are different. Okay, so if I update my global variable on process 1, it should not affect the global variables of process 2. That is actually not true for the MPI standard. Technically, global variables could be shared. For example, if MPI processes are implemented as threads rather than operating system processes. So we have some proposals that define and make this explicit for the user. And we also have a proposal that allows each thread in your, loosely speaking, each thread in your MPI application to get a different MPI rank. Okay, so there's a proposal to do that called MPI endpoints and so on. I'll skip the persistence working group aspects. For one-sided communication, there are a lot of enhancements being added for MPI 4. The biggest enhancements are coming in terms of atomic operations, how MPI atomics work. So right now, MPI atomics are a little hard to optimize and also hard to use. Those are being enhanced for MPI 4. And the second big change that is coming is with respect to RMA synchronization, like your WinFence, WinLock, unlock sort of stuff. They need not be non-blocking. MPI put-get is non-blocking, but the fence and lock unlock might not be non-blocking. So there are some enhancements coming in those aspects to make those non-blocking as well. Skip the tools working group. I'll skip the sessions too. It's a little too hard to explain. The last thing I want to talk about is the large counts working group. One of the things that people have complained about MPI is when you do an MPI send, okay, you send some integers, let's say a bunch of integers, the number of integers that you can send is defined as an int. The parameter in MPI send is an int count of the number of data types. And earlier it was fine because you can send int is up to 2 billion integers, so you can send about 8 gigabytes if you're sending in integers. Okay, but nowadays 8 gigabytes is not much. Okay, there are a lot of machines that have more than 8 gigabytes memory. Okay, especially if each core can use all of the memory on the system. So there is a push to say, well, how will MPI work in this era where each node has 64 gigabytes or 128 gigabytes or a terabyte of memory? Okay, how does it work in those cases? So you can do this even with MPI 3 by creating derived data types. So you can take 2 gigabytes of integers and call that one derived data type. Then you can create larger data by larger descriptions by using derived data type. You can do that today, but it's inconvenient. So there is a working group, or the large count working group, that is looking at essentially duplicating most of the MPI functions by using MPI count instead of integer for your data types. And there is a big effort to see how this can be done with the C11 semantics. So I don't know how many of you are aware of C11 generic semantics. So you can essentially be macro style. You can create with the same function name, MPI send. It's like C++ in some sense. You can have the same function MPI send, but you can have two prototypes: one that uses MPI int, one that uses int for the data type count, just like earlier, and a new one that uses MPI count for the number of data types. So there are some enhancements being looked at for those sort of things. Anyway, so that's roughly, very quickly, the kind of stuff that is being considered for MPI4. Again, as a reminder, nothing is standardized. None of this is standardized. These are just our thought process to give you an idea of the kind of stuff we are looking at for MPI4. So anyway, so that's all we have with respect to the MPI tutorial itself. I think I have like 40 seconds left. But anyway, so to conclude, so MPI is awesome. So you should all use MPI and not any other programming model. But if you really want it, you can mix MPI with other programming models using hybrid MPI programming and so on. But MPI has to be in the picture. It's very, very important that you do that. But if there are any quick questions that we can help answer, any of us from the morning, if we can help answer for you respect to details of MPI or specific thoughts that you had, we can try to answer that quickly before moving on. So questions from anyone here or on the online on the call?
We have a question at NERSC.
Hi, so I have a general question about the hybrid MPI, OpenMP, and threads. And it's about how you bind your processes to the cores on a node and how that's going to be affected or not needed, or what the relationship is to the threads hybrid model that you guys were talking about today.
Should I just take that since I have the mic? Should I just take the question since I have the mic, or do you want to answer it?
So Halim here. It's true that when mixing MPI and threads, binding them properly is a bit tedious. But I think there are some implementations that offer the good way, like environment variables, to achieve that. Just if you run on a generic cluster, for example, Xeon multi-core plus MPH or something like this, there is a decent way to achieve the binding you want. You just need to use MPI exec or MPI run to tell it use X number of MPI processes per node. Each process is going to get a CPU mask, and that CPU mask, the OpenMP, can use it to bind threads wherever they want. For example, you can scatter them or compact them or whatever. But if you run on a machine, for example, like Xeon Phi, the people who, for example, attack, they have their own way to bind the threads because you have more combinations, and they have environment variables where it combines both MPI and OpenMP binding so that you achieve exactly the thread embracement you want. But there is no standard way. It's all up to the implementations, either the OpenMP runtime or the MPI runtime. Does it answer your question?
Yeah, it does. Thank you.
All right. Any other questions? All right. Thank you very much, and thank you for listening in. I think we are done for the day, right? All right, thanks,
You have a
guys.
question? One more question. Push
There
the
is one
button.
more question. Oh, sorry. Go ahead, please.
In MPI put and get calls, you cannot transfer the non-contiguous data, right?
You can transfer non-contiguous data both on the origin and the target. You can have non-contiguous data because there's the data type argument that put and get and all these calls take.
Oh, okay. Okay. I'll look. Thank you.
Yeah. Any other questions? All right. Excellent. Thanks all. Thanks for coming.
Let's thank our MPI team. Thank you, everybody, for staying till 6 p.m. And I hope to see you tomorrow at 10 a.m. Chicago.
you.